Hi, I'm Bo with FreeCodeCamp. This network engineering course was developed by Brian Farrell, an instructor with Edmonds College. It will prepare you to configure, manage, and troubleshoot computer networks. Also, the course is a great way to prepare for CompTIA's Network Plus exam. So let's start.
Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to Network Devices, Part 1. Today we're going to be talking about Layer 1 devices, Layer 2 devices, and then we're going to conclude with Layer 3 devices. There's a fair amount of information to cover, so let's go ahead and dive into this session. Of course, I'm going to begin with Layer 1 devices. Well, before I start talking about the Layer 1 devices, we need to talk about the Open System Interconnection model, the OSI model. It was developed as a way to help disparate computing systems to communicate with each other. The OSI reference model has 7 layers. Layer 1 is the physical layer, Layer 2 is data link, Layer 3 is network, Layer 4 is transport, Layer 5 is session, Layer 6 is presentation, and Layer 7 is application. We're going to be discussing the bottom 3 layers, layers 1, 2, and 3 today. Now, most devices do function at more than one layer of the OSI reference model. But when it comes time to determining where they fit into the model, you must first determine the highest level at which they operate, because that's where they fit into the OSI model. To do that, you must know what they do and how that relates to the OSI model. And with that, let's talk about analog modems. The word modem is actually derived from a contraction of modulator, demodulator. Modems were developed to take a digital signal coming from a digital node and convert it to an analog signal, modulating the signal, and placing it on a wire. In return, it would accept an analog signal from the wire and convert it, demodulating the signal, back to a digital signal that the node can understand. Modems were developed to create a connection between network segments via the public switched telephone network using the plain old telephone system. Now, modems provide for a single connection to a network, and they're only concerned about the wire. And the wire resides on the physical layer, layer 1 of the OSI model. It doesn't care where the signal comes from, it just does its job. Then there's the hub. A hub functions as a concentrator or repeater in that it doesn't care where the signal comes from or where the signal is going, kind of like the modem. It takes an electrical signal that arrives on a port and replicates that signal out all of its other ports. A hub may have just a few ports or it may have many ports. And for a variety of reasons, the hub is not very common anymore in the modern network. So now let's move on to Layer 2 devices. The first Layer 2 device that we're going to talk about is the switch. A switch utilizes an application-specific integrated circuit chip, an ASIC chip. The ASIC chip has specific programming that allows the switch to learn when a device is on the network and which ports it is connected to via that device's Layer 2 MAC address. That's what makes a switch a Layer 2 device. A switch may have just a few ports or it may have many ports, kind of like the hub. And although a switch is smarter than a hub, it can still be very simple or it can be highly complex and programmable. A switch can only communicate with local network devices. Another Layer 2 device that we need to talk about are wireless access points, the WAP. A WAP is a specific type of network bridge that connects or bridges wireless network segments with wired network segments. The most common type of WAP bridges an 802.11 wireless network segment with an 802.3 Ethernet network segment. Just like a switch, a wireless access point will only communicate with local network devices. Now let's move on to layer 3 devices. And first up is the multi-layer switch. A multi-layer switch provides normal layer 2 network switching services, but it will also provide layer 3 or higher OSI model services. The most common multi-layer switch is a layer 3 switch. It not only utilizes an ASIC chip for switching, but that ASIC chip is also programmed to handle routing functions. This allows the device to communicate and pass data to non-local network devices. A multi-layer switch is a highly programmable and complex network device. A multi-layer switch may have just a few ports, or it may have a lot of ports. They're not very common in the small office, home office network because they're really, really expensive. You're more likely to find them in an enterprise local area network. Now let's move on to the router. A router is the most common network device for connecting different networks together utilizing the OSI model's layer 3 logical network information. That's what makes a router a layer 3 device. The router uses software programming for decision making as compared to the switch's use of an ASIC chip. The router uses this programming to keep track of different networks and what it considers to be the best possible route to reach those networks. A router can communicate with both local and non-local network devices. In most cases, a router will have fewer ports than a switch. Now that concludes this session on the Introduction to Network Devices Part 1. We talked about Layer 1 devices, we talked about Layer 2 devices, and we concluded with a couple of Layer 3 devices. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Introduction to Network Devices Part 2. Today we're going to discuss some security network devices, and then we'll move on to some optimization and performance devices. And with that, let's go ahead and begin this session. And we will begin by talking about security devices. First up is the firewall. Now, a firewall can be placed on routers or hosts in that it can be software-based, or it can be its own device. A firewall functions at multiple layers of the OSI model, specifically at layers 2, 3, 4, and 7. A firewall can block packets from entering or leaving the network, and it does this through one of two methods. It can do it through stateless inspection, in which the firewall will examine every packet that enters or leaves the networks against a set of rules. Once the packet matches a rule, the rule is enforced and the specified action is taken. Or it may use stateful inspection. This is when a firewall will only examine the state of a connection between networks. Specifically, when a connection is made from an internal network to an external network, the firewall will not examine any packets returning from the external connection. It only cares about the state of the connection. As a general rule, external connections are not allowed to be initiated with the internal network. Now, firewalls are the first line of defense in protecting the internal network from outside threats. You can consider the firewall to be the police force of the network. Then there is the Intrusion Detection System, the IDS. An IDS is a passive system designed to identify when a network breach or attack against the network is occurring. They're usually designed to inform a network administrator when a breach or attack has occurred, and it does this through log files, text messages, and/or through email notifications. An IDS cannot prevent or stop a breach or attack on its own. The IDS receives a copy of all traffic and evaluates it against a set of standards. The standards that it used may be signature-based. This is when it evaluates network traffic for known malware or attack signatures. Or the standard may be anomaly-based. This is where it evaluates network traffic for suspicious changes. Or it may be policy-based. This is where it evaluates network traffic against a specific declared security policy. An IDS may be deployed at the host level. When it's deployed at the host level, it's called a host-based intrusion detection system, or HIDS. More potent than the intrusion detection system is the intrusion prevention system, the IPS. An IPS is an active system designed to stop a breach or attack from succeeding in damaging the network. They're usually designed to perform an action or set of actions to stop the malicious activity. They will also inform a network administrator through the use of log files, SMS, text messaging, and or through email notification. For an IPS to work, all traffic on the network segment needs to flow through the IPS as it enters and leaves the network segment. Like the IDS, all of the traffic is evaluated against a set of standards, and they're the same standards that are used on the IDS. The best placement on the network segment is between a router, with a firewall hopefully, and the destination network segment. That way all the traffic flows through the IPS. IPSs are programmed to make an active response to the situation. They can block the offending IP address, they can close down vulnerable interfaces, they can terminate network sessions, they can redirect the attack, plus there are more actions that an IPS can take. The main thing is that they are designed to be active, to stop the breach or attack from succeeding in damaging your network. Let's move on to the Virtual Private Network Concentrator, the VPN concentrator. Now this will allow for many secure VPN connections to a network. The concentrator will provide proper tunneling and encryption depending upon the type of VPN connection that is allowed to the network. Most concentrators can function at multiple layers of the OSI model. Specifically, they can operate at layer 2, layer 3, and layer 7. Now, outside of internet transactions, which use an SSL VPN connection at layer 7, most concentrators will function at the network layer, or layer 3 of the OSI model, providing IPsec encryption through a secure tunnel. Now let's talk about optimization and performance devices. We will begin by talking about the load balancer. A load balancer may also be called a content switch or content filter. It's a network appliance that is used to load balance between multiple hosts that contain the same data. This spreads out the workload for greater efficiency. They're commonly used to distribute the requests or workload to a server farm among the various servers in the farm, helping to ensure that no single server gets overloaded with work requests. Then there's the proxy server. A proxy server is an appliance that requests resources on behalf of a client machine. It's often used to retrieve resources from outside untrusted networks on behalf of the requesting client. It hides and protects that requesting client from the outside untrusted network. It can also be utilized to filter allowed content back into the trusted network. It can also increase network performance by caching or saving commonly requested web pages. Now that concludes this session on the Introduction to Network Devices, Part 2. We talked about some security devices that you may find on your network, and we concluded with optimization and performance devices that may also be present. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Networking Services and Applications Part 1. Today I'm going to be discussing the basics of the virtual private network, and then I'm going to move on to protocols used by virtual private networks. Now there's a whole lot of stuff to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about the basics of the virtual private network. A virtual private network, or VPN, is used by remote hosts to access a private network through an encrypted tunnel through a public network. Once the VPN connection is made, the remote host is no longer considered remote. It's actually seen by the private network as being a local host. There are many advantages to that, but I'm not going to cover them right now. Even though the network traffic may pass through many different routes or systems, it's seen by both ends as being a direct connection. The use of the VPN can help to reduce networking costs for organizations and business. The cost reduction is partially achieved because the VPN doesn't require the use of a dedicated leased line to create that direct connection. There are several different types of VPNs. There is the site-to-site VPN, which allows a remote site's network to connect to the main site's network and be seen as a local network segment. VPN concentrators on both ends of the VPN will manage that connection. Then there's the remote access VPN, which is also called a host-to-site VPN. It allows select remote users to connect to the local network. A VPN concentrator on the local network will manage the connection coming in from the remote users. The remote system making the connection uses special software called VPN client software to make that connection. The third type of VPN is the host-to-host VPN, which is often called an SSL VPN. It allows a secure connection between two systems without the use of VPN client software. A VPN concentrator on the local network manages the connection. The host seeking to connect uses a web browser that supports the correct encryption technology, which is either SSL or more likely TLS, to make the connection to the VPN concentrator. It's time to discuss some protocols used by the virtual private network. The big protocol for VPNs is called Internet Protocol Security, IPsec, which isn't actually a protocol in itself, but a whole set of protocols. IPsec works at layer 3 of the OSI model or above. It's the most common suite of protocols used to secure a VPN connection. IPsec can be used with the Authentication Header Protocol, or the AH protocol. AH only offers authentication services but no encryption. So it authenticates the user, but there is no encryption of the session. Or IPsec can be used with Encapsulating Security Payload Protocol, or the ESP protocol. ESP both authenticates and encrypts the packets. It is the most popular method of securing a VPN connection. Both AH and ESP will operate in one of two modes. The first mode is transparent mode. That is between two devices, as in a host-to-host VPN. Or they can be used in tunnel mode, which is between two endpoints, as in a site-to-site VPN. IPsec implements Internet Security Association and Key Management, ISACAMP, by default. ISACAMP provides a method for transferring security key and authentication data between systems outside of the security key generating process. It is a much more secure process. Then we have Generic Routing Encapsulation, GRE. GRE is a tunneling protocol that is capable of encapsulating a wide variety of other network layer protocols. It's often used to create a subtunnel within an IPsec connection. Why is that? Well, IPsec will only transmit unicast packets. That's one-to-one communication. In many cases, there's a need to transmit multicast, which is one-to-some communication, or broadcast, which is one-to-many communication, packets across an IPsec connection. By using GRE, we can get that accomplished. Then there's point-to-point tunneling protocol, PPTP. This is an older VPN technology that supports dial-up VPN connections. On its own, it lacked native security features, so it wasn't very secure. But Microsoft's implementation included additional security by adding GRE to point-to-point tunneling protocol. Transport layer security is another common VPN protocol. TLS is a cryptographic protocol used to create a secure encrypted connection between two end devices or applications. It uses asymmetrical cryptography to authenticate endpoints and then negotiates a symmetrical security key, which is used to encrypt the session. TLS has largely replaced its cousin, Secure Socket Layer Protocol, and TLS works at layer 5 and above of the OSI model. Its most common usage is in creating a secure encrypted internet session, or SSL VPN. All modern web browsers support TLS. Now, I just mentioned Secure Socket Layer, or SSL. SSL is an older cryptographic protocol that is very similar to TLS. The most common use is in internet transactions. Why? Because all modern web browsers support SSL. But due to issues with earlier versions of the protocol, it has largely been replaced by TLS. SSL version 3.3 has been developed to address the weaknesses of earlier versions, but it may never again catch up to its cousin, the TLS protocol. Now that concludes this session on Networking Services and Applications Part 1. I talked about the basics of the virtual private network, and then I talked about the protocols used by the VPN network. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Networking Services and Applications Part 2. Today we're going to be discussing network access services, and then we're going to move on to other services and applications. As always, there's a fair amount of ground to cover, so let's go ahead and dive into this session. I will begin with network access services. The first network access service that I'm going to discuss is actually a piece of hardware, the Network Interface Controller, or NIC. It can also be called the Network Interface Card. The NIC is how a device connects to a network. The Network Interface Controller works at two layers of the OSI model. At layer 2, which is the data link layer, it provides the functional means of network communication by determining which networking protocols will be used, as in a NIC that will provide Ethernet communication or a NIC that will provide point-to-point protocol. It also provides the local network node address through its burned-in physical media access control address. At layer 1, the physical layer, the network interface controller determines how the network data traffic will be converted, a bit at a time, into an electrical signal that can traverse the network media being used, i.e., it provides the connection to the network. Most modern computers come with at least one built-in Ethernet NIC. Routers and other network devices may use separate modules that can be inserted into the device to provide the proper network interface controller for the type of media they're connecting to, and the networking protocols that are being used. Another network access service is Radius, Remote Authentication Dial-In User Service. Radius is a remote access service that is used to authenticate remote users and grant them access to authorized network resources. It is a popular AAA protocol. That's Authentication, Authorization, and Accounting Protocol. It's used to help ensure that only authenticated end users are using the network resources they are authorized to use. The accounting services of Radius are very robust. The only drawback to Radius is only the requesters, the end users, password is encrypted. Everything else gets sent in the clear. Terminal Access Controller, Access Control System Plus, or TACACS Plus. Terminal Access Controller, Access Control System Plus. Boy, what a mouthful. It sure is easier to say TACACS Plus. Is a remote access service that is used to authenticate remote devices and grant them access to authorized network resources. It is also a popular AAA protocol used to help ensure that only authenticated remote network devices are using the network resources that they are authorized to use. With TACACS Plus, the accounting features are not as robust as those found in Radius, but all network transmissions between devices are encrypted with TACACS Plus. Let's move on to other services and applications. First up is RAS, Remote Access Services. Now, RAS is not a protocol, but a roadmap. RAS is a description of the combination of software and hardware required for a remote access connection. A client requests access from an RAS server, which either grants or rejects that access. Then we have web services, creating a means of cross-communication. Web services provides the means for communication between software packages or disparate platforms. It's usually achieved by translating the communication into an XML format, or Extensible Markup Language format. It is becoming more popular as systems diverge. Last up is Unified Voice Services. This is creating a better voice communication system. It's a description of the combination of software and hardware required to integrate voice communication channels into a network, as in voice over IP. That concludes this session on Networking Services and Applications Part 2. I began by talking about network access services, and I concluded with other services and applications. Hello, I'm Brian Farrell, and welcome to PACE IT's session on DHCP in the network. Today we're going to be talking about static versus dynamic IP addressing. Then we're going to move on to how DHCP works, and then we will conclude with components and processes of DHCP. And with that, let's go ahead and begin this session. And of course, we begin by talking about static versus dynamic IP addressing. So how does a computer know what its IP configuration is? Well, more than likely, a computer received its IP configuration from a dynamic host configuration protocol server. Not only did the server give the PC an IP address, but it also told the PC where the default gateway was, and more than likely, how to find a DNS server. A computer will receive its IP configuration in one of two ways, either statically, which means manually set, or dynamically, which means through a service like DHCP. Static IP address assignment works fine for very small and stable networks. but quickly becomes unwieldy and error-prone as the network grows and more nodes come onto the network. So let's talk a little bit more about static IP addressing. The administrator assigns an IP number and subnet mask to each host in the network, whether it be a PC, router, or some other piece of electronic equipment. Each network interface that is going to be available to connect to the network requires this information. The administrator also assigns a default gateway location and DNS server location to each host in the network. Now, these settings are required if access to outside networks is going to be allowed. That would be through the default gateway. And if human-friendly naming conventions are going to be allowed. And that way you can more easily find network resources, and that would be through a DNS server. Now, each time a change is made, as in a new default gateway is established, each IP configuration on each host must be updated. That's why it becomes rather cumbersome and complicated as the network grows. Now, with dynamic IP addressing, the administrator configures a DHCP server to handle the assignment process, which actually automates the process and eases management. The DHCP server listens on a specific port for IP information requests. Once it receives a request, the DHCP server responds with the required information. Now let's move on to how DHCP works. Here is the typical DHCP process. Upon boot up, a PC that is configured to request an IP configuration sends a DHCP discovery packet. Now the discovery packet is sent to the broadcast address 255.255.255.255 on UDP port 67. The DHCP server is listening to that port. It's listening for that discovery packet. When the DHCP server receives the discovery packet, it responds with an offer packet, basically saying, hey, I'm here to help. Now the offer packet is sent back to the MAC address of the computer requesting help, and it's sent on port 68. Once the computer receives that offer packet from the DHCP server, if it's going to use that DHCP server, it returns a request packet. That means it's requesting the proper IP configuration from that specific DHCP server. Once the DHCP server receives the request packet, it sends back an acknowledgement packet. Now this acknowledgement packet contains all of the required IP configuration information. Once the PC receives the acknowledgement packet, the PC changes its IP configuration to reflect the information that it received from the DHCP server. And that's the typical DHCP process in a nutshell. Now let's talk about components and the process of DHCP. We're going to begin by talking about the ports used. Now I already mentioned this once, but I'm going to mention it again because you need to know this. The PC sends its discovery packet out on the broadcast address 255.255.255.255 on port 67. That's UDP port 67. When the DHCP server responds, it responds to the PC's MAC address, Media Access Control address, on UDP port 68. That's important to remember. The PC uses UDP port 67. The DHCP server responds on UDP port 68. Then there's the address scope. The address scope is the IP address range that the administrator configures on the DHCP server. It is the range of addresses that the DHCP server can hand out to individual nodes. There's also what are called address reservations. Now these are administrator configured reserved IP addresses. The administrator reserves specific IP addresses to be handed out to specific MAC addresses. Now, these are used for devices that should always have the same IP address, as in servers and routers. If you didn't do that, there is the possibility that your default gateway's IP address might change. Now, the reason we use address reservation is this allows these addresses to be changed from a central location instead of having to log into each device and change the IP configuration separately. Now, part of the DHCP process are what are called leases. The DHCP server hands out that IP configuration information, but it sets a time limit for how long that IP configuration is good. This is called the lease. So the parameters are only good for a specified amount of time. Now, the administrator can configure how long the leases are. There are also options that the administrator can configure. The first one that's pretty obvious is the default gateway location. There's also the DNS server address, and the administrator can configure more than one DNS server location. An administrator can also configure an option for the PC to synchronize with a time server, so the administrator can configure a time server address. There are many more additional options, but those are the big three that you should remember. Now, when a PC boots up, it does have a preferred IP address. That would be the IP address that it had the last time it booted up. Now, it can request that same IP configuration from the DHCP server. Now, the administrator can configure the DHCP server to either honor that preference or to ignore it. Now, under the right circumstances, a DHCP server isn't required to reside on the local network segment. Now, as a general rule, broadcast transmissions cannot pass through a router. But if there is not a DHCP server on the local network segment, the router can be configured to be a DHCP relay. When a DHCP relay, also called an IP helper, receives a discovery packet from a node, it will forward that packet to the network segment on which the DHCP server resides. This allows for there to be fewer configured DHCP servers in any given network, reducing the amount of maintenance that an administrator needs to perform. Now, that concludes this session on DHCP in the network. We started with static versus dynamic IP addressing, and then we moved on to how DHCP works, and we concluded with components and processes of DHCP. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the introduction to the DNS service. Today we're going to be talking about DNS servers, DNS records, and we will conclude with a brief discussion on dynamic DNS. And with that, let's go ahead and begin this session. We're going to begin this session with a talk about DNS servers. Now, DNS is the process that maps human-friendly names, as in www.google.com, to their appropriate IP addresses. Without DNS, we would have to memorize all of the IP addresses that we wished to visit. Now, DNS stands for Domain Name System, and it's very structured in nature. If the local DNS server apparatus doesn't contain the needed record, it sends the request up the DNS chain until a positive response is received back. Now, this positive response gets passed back down to the original requester. Now, DNS does require that an FQDN, fully qualified domain name, is used in order for it to function properly. Now, an FQDN is the www.google.com. It's that naming convention right there. The www is the specific service that's being requested. The Google portion is the local domain that contains the specific service, and the com is the top level that contains the Google that contains the specific service. That is an FQDN. Now that we've got that covered, let's talk about the different levels of DNS servers. First off, there can be a local DNS server. This is the server on the local network that contains the hosts file that maps all of the FQDNs to their specific IP addresses in the local subdomain. It may be present or it may not be present. Then there are top-level domain servers, the TLD server. Now these are the servers that contain the records for the top-level domains. Examples of top-level domains are .com, .org, .net, .edu, so on and so forth. Now each of these servers contains all of their information for their respective domains, kind of. And what do I mean by kind of? Well, the TLD servers do delegate down to second-level servers their information. They do that to ease the load so that the TLD server is not overloaded. But the TLD server is the server that is responsible for maintaining the record. Then there's the root server. This is the server that contains all of the records for the TLD servers. So if you're looking for a TLD that is kind of unknown, you will actually go to the root server, which will then pass you onto the appropriate TLD. Then there are authoritative servers and non-authoritative servers. An authoritative DNS server is one that responds to a request, and that authoritative server has been specifically configured to contain the requested information. An authoritative response comes from a DNS server that actually holds the original record. So an authoritative response comes from the name server that's been specifically configured to contain that record. Then there are non-authoritative DNS servers. Now, a non-authoritative DNS server is one that responds to a request with DNS information that it received from another DNS server. A non-authoritative response is not a response from the official name server for the domain. Instead, it is a second or third-hand response that's given back to the requester. In most cases, when we send a DNS request, we get a non-authoritative response back. Now let's move on to the various DNS record types. The first record that we're going to talk about is the A record. Now the A record maps host names, or FQDNs, to their respective IPv4 addresses. Closely associated with the A record is the AAAA record, or quadruple A record. This maps the FQDN to its respective IPv6 address. Then there's the CNAME record. Now this maps a canonical name, or alias, to a host name. What that means is that you can have edcc.edu be the same as edc.org without having to maintain two sites. The edcc.org can be the canonical name for edcc.edu. This works in part because of the pointer record, the PTR record. It's a pointer record that points out to DNS that there is a canonical name. And finally, we have the MS record. Now, this record maps to the email server that is specified for a specific domain. It is the record that determines how email travels from sender to recipient. And now let's move on to dynamic DNS. Now, dynamic DNS, or DDNS, permits lightweight and immediate updates to a local DNS database. This is very useful for when the FQDN or host name remains the same, but the IP address is able to change on a regular basis. Dynamic DNS is implemented as an additional service to DNS, and it's implemented through DDNS updating. Now, this is a method of updating traditional name servers without the intervention of an administrator. So there's no manual editing or inputting of the configuration files required. A DDNS provider supplies software that will monitor the IP address of the referenced system. Once the IP address changes, the software sends an update to the proper DNS server. DDNS is useful for when access is needed to a domain whose IP address is being supplied dynamically by an ISP or Internet Service Provider. That way the IP address can change, but people can still get to the service that they're looking for. Now that concludes this session on the introduction to the DNS service. We talked about DNS servers, we moved on to DNS records, and then we concluded with a very brief discussion about dynamic DNS. Hello, I'm Brian Farrell, and welcome to PACE IT session introducing network address translation. Today we're going to be talking about the purpose of network address translation, and then we're going to discuss how network address translation works. And with that, let's go ahead and begin this discussion. Of course, we're going to begin by talking about the purpose of network address translation. Network address translation, or NAT, solves a very serious problem of how to route non-routable IP addresses. As a partial effort to conserve the IPv4 address space, the private IPv4 addressing spaces were developed. These address spaces were removed from the public IPv4 address space and made non-routable across public IPv4 networks. And this led to the problem. Being non-routable prevents that private IPv4 address from communicating with remote public networks. NAT very simply solves this problem. A router with NAT enabled will translate a private IP address into a routable public IP address. When the response returns to the router, it passes the response back to the device that requested it. So now that we've covered the purpose, let's talk about how network address translation works. And first off, we get to talk about the fact that there are two categories of NAT. First up is static NAT. With static NAT, each private IP address is assigned to a specific routable public IP address. This relationship is kept and maintained by the NAT-enabled router. When a device needs access outside of the local network, the router translates the local IP address to the assigned public IP address. And when the response comes back, the router will translate the public IP address back into a local one. Static NAT is not flexible and leads to some scalability issues. An individual routable IP address must be kept for every device that requires access outside of the local network. So as the network grows, you need to increase the amount of public IP addresses that are under your control. That gets kind of expensive and kind of complicated. They developed dynamic NAT to resolve some of that issue. With dynamic NAT, the NAT-enabled router dynamically assigns a routable IP address to devices from a pool of available IP addresses. When a device needs access outside of the local network, The router performs the NAT function, only the public IP address comes from a reusable pool of public IP addresses. That private IP address is assigned the public IP address from the pool, and once outside access is stopped, the routable IP address goes back into the pool to be reused. As initially designed, dynamic NAT was more flexible than static NAT, but it still led to some scalability issues. As more network traffic required access to outside networks, the pool of available public IP addresses needs to increase, or outside access cannot be achieved. But thankfully, there is a solution to this. And that solution is called port address translation, or in Cisco terms, that would be NAT with PAT. PAT is a type of dynamic NAT that was developed to increase the scalability of network address translation. When a local network device requires access to a public network, the NAT-enabled router dynamically assigns the public IP address to the device with the addition of dynamically assigning a port number to the end of the public IP address. The router tracks the IP addresses and port numbers to ensure that network traffic is routed to and from the proper devices. PAT still requires a pool of public IP addresses, but the pool may only contain one public IP address, or it may contain several for a large private network. This is the preferred method of implementing network address translation for two reasons. First off, there's less public IP addresses that are required, and it makes it easier for an administrator to maintain. Now let's talk about NAT terminology, specifically about the types of addresses. And we begin with the inside local address, which is a private IP address on the local network. It is the private IP address assigned to a specific device. Then there's the inside global address, a public address referencing an inside device. The inside global address is the public IP address assigned to the inside device by the NAT-enabled router, allowing access outside of the network. Then there's the outside global address, which is a public IP address referencing an outside device. It is the public IP address assigned to a device outside of the local network. Then there's the outside local address, which is a private IP address assigned to an outside device. This is the private IP address assigned to the outside device by the NAT-enabled router on the interior of the local network, so that the inside device can communicate correctly with the outside device. Now that concludes this session on introducing network address translation. We talked about the purpose of network address translation, and then we talked about how network address translation works. Good day, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 1. Today I'm going to be talking about the public switched telephone network, then I'm going to move on to broadband cable, and I'm going to conclude with a brief section on fiber optics. And with that, let's go ahead and begin this session. Of course, we begin with the public switched telephone network. Before I begin with the public switched telephone network, let's talk about what makes a WAN as opposed to a LAN. Well, as a general rule, if you own and control the line that the data is using to get from one place to another, you are not using a wide area network or WAN technology. On the other hand, if you are using a form of transmission that you don't own, as in you're leasing a line or you're paying for the use of it, then you are likely using WAN technology. One of the most common physical infrastructures used in WAN technology is the public switched telephone network, the PSTN, due to its widespread availability. Just about everybody has a telephone line being run to their house or to their building. An older technology, but still somewhat valid today for WAN technology, is dial-up. Now, dial-up utilizes the PSTN to transmit network traffic as an analog signal. Dial-up does require an analog modem to format the network traffic correctly so it can be transmitted. Your maximum theoretical speed on dial-up is 56 kilobits per second. It's not very fast. Then there's ISDN, Integrated Service Digital Network. ISDN is a digital point-to-point WAN technology that utilizes the PSTN. It's a completely digital service. It requires the use of a terminal adapter, or TA, to make the connection to the end nodes. This TA is often called a digital modem, but it's not. It's a terminal adapter. ISDN can use a primary rate interface, or PRI. Now, the PRI is composed of 23 64 kilobit per second B channels and one 64 kilobit per second D channel. That D channel is used for call setup and link management. A PRI can achieve 1.544 megabits per second speed, and that is commonly referred to as a T1 leased line. The most commonly implemented form of an ISDN, though, is the BRI, the Basic Rate Interface. It uses only 2 B channels and 1 D channel, and the BRI can achieve speeds of up to 128 kilobits per second. Now, ISDN is not as capable as a digital subscriber line, or DSL, but it can often be implemented where DSL cannot be installed. Speaking about DSL, let's move on to it. XDSL is the term for generic DSL. DSL is a digital WAN technology that utilizes the PSTN. DSL does require the use of a digital modem. It uses a dedicated digital line between the endpoint and a Class 5 central office, or CO. Now, in order for the most basic forms of DSL to be installed, you have to be within 18,000 feet of the CO. DSL is capable of carrying voice and data. When it does carry both, filters are put in place in order for the voice signal to come through without any interference. Now let's move on to the different types of DSL. And first up is symmetric DSL, or SDSL. Symmetric DSL is synchronous in nature. That means that the upload and download speeds are the same. SDSL does not carry voice communication. So if you need voice service, an additional line is going to be needed. SDSL is used by businesses that don't quite need the performance of a T1 leased line, but they do require the symmetrical upload and download speeds. More common than SDSL is ADSL, or asymmetric DSL. It's asynchronous in nature. That means that the upload speed is slower than the download speed. ADSL can carry data and voice. Common upload speeds for ADSL are 768 kilobits per second, with download speeds of up to 9 megabits per second. It is the most common implementation of DSL in the small office, home office environment. Last up for DSL is VDSL, or Very High Bitrate DSL. It's asynchronous in nature as well. It's used when high-quality video and voice over IP is necessary. VDSL is commonly limited to download speeds of 52 megabits per second with an upload speed of 12 megabits per second. That's a whole lot faster than ADSL. But VDSL is only possible when you're located within 4,000 feet of a central office. There is an exception to what I just told you, though. The current standards do allow for up to 100 megabits per second speed over the PSTN using VDSL, but in order to achieve that, you must be within 300 meters of the central office. Now that the PSTN is out of the way, let's move on to broadband cable. Broadband cable is coaxial cable networking. It's a broadband connection to a location delivered by the cable company. Broadband cable can deliver voice, data, and television all through the same connection. And the way it works is the digital signal is delivered to the head-end. This is where all the cable signals are received. The signal is then processed and formatted and then transmitted to the distribution network. The distribution network is a smaller service area served by the cable company. The distribution network architecture can be composed of fiber optic cabling or coaxial cabling and or a hybrid fiber coaxial cabling or HFC. Unlike DSL, the bandwidth of the distribution network is shared by all of those who connect to it. This can lead to increased latency and congestion during busy times. The final distribution to the premise is usually through a coaxial cable. The other thing that you need to know about broadband cable is that all cable modems and similar devices must measure up to the ISP's required Data over Cable Service Interface specification or DOCSIS specification. If it doesn't measure up, you're not going to achieve the speeds that you expect. Now let's conclude with fiber. Fiber optic networking is using light to transmit data and voice. This allows for more bandwidth over greater distances. Fiber optic networking is more expensive to install, but is also less susceptible to line noise. The fiber synchronous data transmission standard in the United States is called the Synchronous Optical Network, or SONET standard. The international standard is called the Synchronous Digital Hierarchy, or SDH. Both SONET and SDH define the base rates of transmission over fiber optic cabling, which are known as optical carrier levels. Dense wavelength division multiplexing is a method of multiplexing several optical carrier levels together, up to 32 of them, into a single fiber optic cable, effectively increasing the bandwidth of that single optical fiber. Instead of DWDM, you could use CWDM, coarse wavelength division multiplexing. It's similar to DWDM, but it only allows for up to 8 channels on a single fiber. When fiber optic is delivered to the premise, it's usually delivered over a passive optical network, or PON. A PON is a point-to-multipoint technology that uses a single optical fiber that's used to connect multiple locations to the internet. The passive optical network uses unpowered optical splitters. Now that concludes this session on WAN technologies part 1. I talked about the public switched telephone network, then we moved on to broadband cable, and I briefly ran through fiber optic networking. Good day, I'm Brian Farrell, and welcome to PACE IT's session on WAN technologies part 2. Today we're going to be discussing GSM and CDMA WAN connections. Then we're going to move on to WiMAX WAN connections, and we're going to conclude with satellite wide area network connections. There's a fair amount of information to cover, so let's go ahead and begin this session. And of course, I'm going to begin with the GSM and CDMA wide area network connections. All cellular carriers use one of two methods for connecting devices to their networks, and those methods are not compatible. Currently in the United States, AT&T and T-Mobile use the Global System for Mobile, or GSM standard, to connect their devices to their networks. Both Sprint and Verizon use Code Division Multiple Access, also known as CDMA, as their method of connecting to networks. And those two standards are not compatible. The majority of the rest of the world utilizes GSM as the method for cellular network access. Let me speak briefly about cellular networking. Cellular networking involves using the cellular phone system for more than just phone calls. Cellular networking has been around for a while, and it originally wasn't known as this, but the first version of it is First G or 1G cellular, and it was only capable of voice transmissions. As improvements came along, we got 2G. That is cellular with simple data transmission capabilities, as in text messaging. 2G Edge offered some basic cellular networking connectivity and was a stopgap measure between 2G and third generation cellular. 3G cellular is the beginning of cellular WAN networking. It's giving way to 4G cellular, which is still an emerging technology. 4G currently consists of both LTE and WiMAX. As a special mention, we need to talk about Evolved High-Speed Packet Access, which is HSPA+. It was a stopgap between 3G and 4G networking. It's still available today. The current standard for HSPA+ allows for up to a maximum data rate of 84 megabits per second. Now, it's not quite as good as LTE, which is long-term evolution. LTE uses an all IP-based core with high data rates. Now, LTE is compatible with both 3G and WiMAX. The current standard for LTE allows for up to 300 megabits per second in download speeds and up to 75 megabits per second in upload speeds. Now let me introduce you to WiMAX WAN connections. WiMAX stands for Worldwide Interoperability for Microwave Access. That's a mouthful. That's why we say WiMAX. WiMAX was originally developed as a last-mile alternative to use when DSL or cable was not available. It can provide an alternative broadband connection to a fixed location. It uses microwave transmissions as an over-the-air method to transmit voice and data. It does require line of sight between relay stations. But WiMAX can be used to cover significant geographic distances. Also, many municipalities are exploring the use of WiMAX as a means of providing reasonably priced broadband to their citizens without having to wire every household. WiMAX is often considered to be a type of 4G technology because it is compatible with LTE networks. But WiMAX is not compatible with third-generation cellular networks. It is time for us to conclude with satellite WAN connections. Satellite WAN connections are a type of microwave satellite networking. It uses microwave transmissions as an over-the-air method of transmitting voice and data, just like WiMAX. It can be an effective means of extending networks into places that are hard to reach. It does use microwave radio relay as the method of transmitting data through the atmosphere. Just like WiMAX, it requires line-of-sight relay stations, but it can cover even more distances than WiMAX. Why is that? That's because it utilizes a satellite network. By the way, because of the distances that satellite transmissions can cover, this can lead to latency problems. Think about it. The signal's got to go from a terrestrial location up to the satellite, probably over to another satellite, and then down to another terrestrial station. That's a significant amount of distance, and there's going to be some lag. I just talked about the communication satellite. They're also known as ComSats. These do form part of the microwave relay network. ComSats can use a variety of orbits, including the Maligne, geostationary, low polar, or polar orbits. The low polar and polar orbits are used to boost microwave signals before sending the signal back to Earth. Now that concludes this session on WAN Technologies Part 2. I briefly talked about GSM and CDMA WAN connections. Then I moved on to WiMAX WAN connections, and then we concluded with satellite WAN connections. Hello, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 3. Today I'm going to briefly discuss Metro Ethernet WAN connections, then I'm going to move on to leased line WAN connections, and we're going to conclude with some common standards. And with that, let's go ahead and begin this session. Of course, I'm going to begin by discussing Metro Ethernet WAN connections. A Metro Ethernet connection is when the service provider connects to the customer's site through an RJ45 connector. The customer will view that WAN connection as an Ethernet connection, while in reality the type of connection will be dependent upon the level of service that has been purchased. The service provider may also use a variety of different wide area network technologies behind the scenes, but the customer will always view it as being an Ethernet connection. Metro Ethernet is commonly deployed as a wide area network technology by municipalities at the metropolitan area network or MAN level, as in at the municipal level. It's time for us to discuss leased line WAN connections. A leased line is a dedicated circuit or connection between two endpoints used for communication. When we're talking about IT, a leased line is usually a digital point-to-point connection. A leased line can utilize either a plain old telephone service line, a POTS line on the public switched telephone network, or it can be a fiber optic circuit provided by a telecommunications company. Leased lines tend to be more expensive for the customer as the circuit can't be utilized by any other entity. So the whole cost is borne by the customer because they're the only ones who get to use it. Most often the speed of a leased line is limited by what the customer is willing to pay. There are some multiplexing technologies out there that can be used to increase the amount of channels that are provided on the connection. One of the leased line technologies that you need to know about is point-to-point protocol, PPP. It is a common data link layer or layer 2 protocol that's used with leased line networks. PPP can simultaneously transmit multiple layer 3 protocols. It can transmit IP and IPX and AppleTalk all at the same time through the use of control protocols, which are actually specific to the layer 3 protocol that's being transmitted. PPP can include a feature called multi-link PPP, which allows for multiple physical interfaces to be bonded together and act as a single logical interface. This effectively increases the available bandwidth to that system. There are different types of leased line connections. In the United States, Japan, and South Korea, there are T-carrier lines. Each T-line is composed of 24 digital signal channels. These are often called digital signal zero channels, or DSO channels. Each channel is capable of carrying 64 kilobits per second. The 24 DSOs make up what is called a DS1 channel. In Europe, we have E-carrier lines. Each E-line is composed of 30 digital signal channels. These are also called DSO channels. The 30 DSO channels also make up what is called a DS1 channel. When we're talking about fiber optic speeds, we often talk about optical carrier lines, or OC lines. The OC data rates per channel are established by both the SONET and SDH networking standards. SONET is the United States standard, and SDH is the international standards. Interestingly enough, the OC rates are the same across the two standards. It's possible to multiplex multiple channels into the same fiber using different methods. The first method is dense wavelength division multiplexing, DWDM. It allows for up to 32 separate channels on a single fiber cable. Or you could use coarse wavelength division multiplexing, which allows for up to 8 separate channels on a single fiber optic cable. Let's conclude with common standards. The standards I'm going to be talking about are the speeds, and we begin with T-lines. A T1 is composed of 24 DSO channels, which are also known as a DS1, and it's capable of achieving speeds of up to 1.544 megabits per second. If that's not fast enough for you, you can lease a T3 line. It's composed of 28 T1 lines. Now, a T3 line is also known as a DS3, and it can achieve speeds of up to 44.736 megabits per second. If you're in Europe, you might lease an E1 line. An E1 line, which is composed of 30 DSO channels, can achieve speeds of up to 2.048 megabits per second. Just as with the United States, if that's not fast enough for you, you can lease an E3 line, which is composed of 16 E1 lines, which gives you up to 34.368 megabits per second speed. While a T1 is slower than an E1, a T3 is faster than an E3. For OC lines, we have the OC1. It's capable of 51.84 megabits per second in speed. Then there is the OC3, which gives you up to 155.52 megabits per second speed. It's becoming more common now to see OC12s. With those, you get up to 622.08 megabits per second. If you want gigabit type speed, you might consider leasing an OC48. That gives you up to 2.488 gigabits per second in bandwidth. Currently at the top of the line is the OC192. That gives you up to 9.953 gigabits per second speed. So essentially 10 gigabits per second worth of bandwidth. Now that concludes this session on WAN Technologies Part 3. I briefly discussed Metro Ethernet WAN connections, and then I went on to a discussion about leased line WAN connections, and then I briefly mentioned some common standards. Hello, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 4. Today I'm going to be discussing the difference between circuit switched and packet switched networks. Then I'm going to move on to a discussion comparing frame relay versus asynchronous transfer mode. And then we're going to conclude with multi-protocol label switching. There's a whole lot of ground to cover, not a whole lot of time. Let's go ahead and begin this session. Let's begin this session by talking about circuit switched and packet switched networks. Circuit switched networks have a dedicated circuit between two endpoints that is used for communication. While set up, the circuit can only be used for communication between those ends. Circuit switched networks are most common in networks with leased line communication channels. They're best used when there needs to be a fair amount of continuous data traffic between the two endpoints. And with circuit switched networks, there is only one path for the data to take. On the other hand, in packet switched networks, data is broken up into smaller chunks and moved through the network, only to be reassembled at the other end. The data is routed using the destination address, and the data may take different paths through the network that it's traveling through. As a general rule, packet switched networks are less expensive to maintain. Why? because the user doesn't have to maintain a dedicated circuit 24/7. They're only paying for what they're using. Now let's talk about the differences between frame relay and asynchronous transfer mode. Frame relay is a WAN technology in which variable length packets are switched across a network. Frame relay is less expensive than leased lines, but frame relay can be made to look like a leased line through virtual circuits or VCs. A frame relay network will track a VC using a data link connection identifier to identify the ends of the VC. There are two terms associated with frame relay that you should be aware of. The first is access rate. That is the maximum speed of the frame relay interface. The other term is the committed information rate, the CIR. That's the guaranteed bandwidth that a customer receives. So that's the minimum speed of that frame relay network. The access rate may be higher, but the customer is always guaranteed the committed information rate. Now let's talk about asynchronous transfer mode, also known as ATM. ATM is a WAN technology in which fixed length cells are switched across a network. These cells are always 53 bytes long. ATM can handle real-time voice and video because it's very fast, but it has poor bandwidth utilization. The small cell size reduces the efficiency of the technology, but ATM is very fast even if it is inefficient. Common speeds on an ATM network are 51.84 megabits per second and 155.52 megabits per second. Let's conclude with multi-protocol label switching. The acronym for multi-protocol label switching is MPLS. MPLS is a topology that's growing in popularity. Why? Because it's scalable. Also, it is protocol independent. MPLS can be used to replace both frame relay switching and ATM switching. It can be used to packet switch both frame relay and ATM network traffic. This allows MPLS to be used with both frame relay and ATM technologies. MPLS is often used to improve quality of service and flow of network traffic. It uses a label edge router to add MPLS labels to incoming packets if they don't have them. The label edge router then passes those packets onto a label switching router or LSR router. The LSR forwards those packets based on their MPLS labels to their final destination. Now that concludes this session on WAN Technologies Part 4. I talked about the differences between a circuit switched and packet switched network. Then we moved on to frame relay versus asynchronous transfer mode, and we concluded with a brief discussion on multi-protocol label switching. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Network Cabling Part 1. Today we're going to be talking about twisted pair network cabling, then we're going to talk about twisted pair network connectors, and then we will conclude with categories of twisted pair. I have a whole lot of information to cover and I need to get through this quickly, so let's go ahead and begin this session. And we'll begin by talking about twisted pair network cabling. Most people are familiar with twisted pair cables because they are the standard in the modern LAN. They are what you see most often when you're looking at network cabling. Twisted pair cables are composed of 4 pairs of wires contained within an insulating sheath. Each pair of wires is twisted together to reduce electromagnetic interference, which is called EMI. The twist rates differ between the pairs to reduce crosstalk between the pairs, which is a type of EMI. The colors of the pairs of wires are always white orange orange, white blue blue, white green green, and white brown brown. Twisted pair network cabling comes in either unshielded or shielded twisted pair. That would be UTP or STP. The difference is that STP has an additional shield that is either wrapped around each pair of wires or around all 4 pairs of wires. That shielding reduces the opportunity for EMI or crosstalk, but it is more expensive and a little harder to work with because it's not as flexible. UTP, or unshielded twisted pair, is deployed in the network much more often than STP. There are also plenum and non-plenum types of twisted pair. Most twisted pair cabling is non-plenum grade, but building codes often call for plenum grade cable to be run in plenum spaces. Now, a plenum space is that area that is designed to assist in the airflow of a building for HVAC purposes. And most often, the plenum is that space between the false ceiling and the actual ceiling. Plenum cable is jacketed in either a fire retardant cover or in a low smoke PVC jacket. Plenum cables often have a polymer or nylon strand woven into the cabling or into the jacket to help take the weight of hanging cables. This reduces the chance for the cable to stretch, which can cause the pair or pairs of wires inside the jacket to break. Twisted pair is usually either a straight-through cable or a crossover cable, but it can also be used to create a rollover or console cable. A straight-through cable is used to connect different types of devices together, as in a computer to a switch or a switch to a router. While a crossover cable is used to connect similar devices together, as in a PC to a PC or a switch to a switch. The straight-through and crossover cable use different pinouts to achieve their connections. A rollover or console cable is often required to connect to the console port on a switch or a router. It is quite common for one end of the rollover cable to use an RJ45 connector, while the other end utilizes an RS232, also called a DB9 connector. So now that I've mentioned those connectors, let's go on to twisted pair network connectors. And we're going to begin with the RJ11. You don't see these very much in what we think of as networking, but you do see them all the time. The RJ11 uses a 6-position, 4-contact modular connector. That's a 6P4C modular connector. It can carry data or voice, and its common usage is voice communication, telephony. All of your telephone jacks are RJ11s. Then there's the RJ45. This is the one that we always think about when we think about networking with twisted pair cabling. It uses an 8-position, 8-contact, or 8P8C modular connector. It can carry data or voice, and its common usage is data networking, Ethernet. Then there's the RJ48C. It also uses an 8-position, 8-contact modular connector, 8P8C, just like the RJ45. As a matter of fact, it's often thought of as being an RJ45, but it's used as the terminating connector at the demarc point for T1 lines. And as I said just a moment ago, it's often confused with the RJ45, but the active pins are different. Then we have the UTP coupler, the unshielded twisted pair coupler. It's used to connect UTP cables back to back and still maintain adherence to industry standards. You might still come across a 66 block being used for network connections, but probably not. It's a punch-down block that was initially developed to terminate and distribute telephone lines in an enterprise network. So you might still see it for telephony, but it's getting a little bit harder to find it. It was also used in slower speed networks as it can handle data traffic that's rated for Cat3 cabling. Much more likely you'll find a 110 block. Now this is a punch-down block that was developed to terminate and distribute twisted pair network cabling. It's capable of handling the signaling requirements of the modern network. I mentioned the DB9 or RS232 connector earlier. Well, here we go. It is a 9-pin D-subminiature connector developed for asynchronous serial communication between nodes. It was a common type of connector between a computer and an external modem. And as I said earlier, it often makes up one end of the rollover cable. You might come across a DB25, also known as an EIA 232 or RS 232 serial connector. It is a 25-pin D-subminiature connector developed for asynchronous serial communication between nodes, just like the DB9, only it was larger. It too provided a type of connection between a computer and an external analog modem, and it's even less common than the DB9. Now let's move on to categories of twisted pair. And we begin with Cat3. Cat3 was rated for up to 10 megabits per second speed. That's 10 base T networking, and it had a maximum distance of 100 meters. By the way, unless I specify, all twisted pair cabling has a max distance of 100 meters. That 10 megabits per second wasn't quite fast enough, so then we got Cat5. Cat5 is rated for up to 100 megabits per second speed. That's 100 base T networking. And that still wasn't fast enough, so they developed Cat5e. Cat5e is rated for up to 1 gigabits per second. That's 1,000 base T. Now we have Cat6. Cat6 is rated for up to 10 gigabits per second. That's 10 gigabit Ethernet, or 10 GBE. And with Cat6, you can only get that 10 gigabits per second over a max distance of 55 meters. For some reason, they thought they needed to go more distance than 55 meters, so they developed Cat6a. It has the same speed ratings as Cat6, but it has a max distance of 100 meters, and you can still achieve that 10 gigabits per second networking. Now that concludes this session on network cabling part 1. I talked about twisted pair cabling, then I talked about twisted pair network connectors, and I concluded with the categories of twisted pair cabling. Hello, I'm Brian Farrell, and welcome to PACE IT's session on network cabling part 2. Today we're going to be talking about coaxial cabling and fiber optic cabling. There's a fair amount of ground to cover, so let's go ahead and begin this session. And of course we're going to begin by talking about coaxial cabling. Coaxial, or coax, cabling is one of the oldest Ethernet standards for network cabling. It was standardized in 1973. It's been used for baseband, carries just a single digital signal, and it has been used for broadband, carrying multiple digital signals. It is composed of a central conductor that is covered by an insulating layer, which is covered by an outer mesh or foil layer, which is then finished off with an outer insulating layer. That inner metal mesh layer helps to protect against electromagnetic interference, EMI. There are several different types of coax cable. There is RG58. It was used in 10 base 2 networking. It could span a maximum distance of 185 meters and had a 50 ohms impedance value. It's no longer commonly found in the modern network. Then there's RG59. It's commonly used to provide a broadband connection between two devices over a short distance. And it has a 75 ohms impedance value. And it's only used for short distances because it leaks its signal. It can't span very far. Then we have RG6, which is used for cable TV or broadband. Now the distance that RG6 can span varies, but it still has a 75 ohms impedance value. And it's commonly used to make the connection to a cable modem by the cable company. There are two basic types of coax cable connectors. There is the BNC, also known as the bayonet Neal-Councilman connector. You can also call it a bayonet connector. It is used with coax cabling, but is now considered obsolete. The connection from the cable to the device was achieved through a spring-loaded twist lock type of connector. A BNC coupler can also be used to connect two coax cable segments back to back. Much more common is the F connector. It's a threaded bayonet connector, and it's also used with coax cable. An F connector coupler can be used to connect two coax cable segments back to back. Now let's move on to fiber optic cabling. So now let me describe fiber optic cabling. First off, it's relatively expensive and harder to work with than with other types of network cabling. It's not as common as other types, either coax or twisted pair, in the LAN environment. But it can resist all forms of electromagnetic interference, and it cannot be easily tapped into. That means it's harder for people to eavesdrop on your network transmissions. It also can cover long distances at high speed. Fiber optic cabling is designated by fiber type, cladding size, by the way, the cladding is what the light bounces down, and its jacket size, that outer jacket that covers the cable. The size of the cladding and the size of the jacket are listed in micrometers. Most applications of fiber optic cabling require that the cables be run in pairs. One cable to send transmissions, one cable to receive transmissions. The type of connector used on fiber optic cabling can impact the performance of the transmission. There are two basic categories of connectors. There is the UPC, the ultra physical contact. This connector has a back reflection rating of around a negative 55 decibel loss. Then there's the APC, the angled physical connector, which has a back reflection rating of around a negative 70 decibel loss, making it the better performing connector. Now let's talk about fiber types. There's multi-mode fiber, which uses an infrared LED system to transmit light down the fiber. It sends multiple rays of lights down the cable at the same time. It is used for shorter fiber runs, under 2 kilometers. It is less expensive than the other type of fiber cabling. Then we have single mode fiber, SMF. It uses a laser diode arrangement to transmit light down the fiber. It only sends a single ray of light down the cable. Even though my diagram depicts it as going straight, it still bounces down the cladding, but there's only one of them. It's used for longer runs that require high speed, and it can span more than 40 kilometers. So now let's talk about fiber optic cabling connectors. And first up is the SC. That is the subscriber connector or the square connector. You can also call it a standard connector. An easy way to remember it is stick and click. It's a push-pull type connector. Then we have the ST, the straight tip. You can also think of this as stick and twist. It is a spring-loaded twist lock type of connector. There is also the LC, which can be called the local connector or loosened connector or little connector. It's a type of connector that uses a locking tab to secure the connection. Similar to the LC is the MTRJ, the Mechanical Transfer Registered Jack. It's a small form factor connector that contains 2 fibers and that also utilizes a locking tab to secure the connection. You might also find a fiber optic coupler. Guess what it does? It's used to connect 2 fiber optic cables back to back. Now that concludes this session on network cabling part 2. I talked about coaxial cabling, and I concluded with fiber optic cabling. Good day, I'm Brian Farrell, and welcome to PACE IT's session on network cabling part 3. Today I'm going to be talking about media converters, and then I'm going to talk about some cabling tools that you should know about. And with that, let's go ahead and begin today's session. I will begin by discussing media converters. It is not uncommon to be in a situation where a network contains more than one type of cabling. This can lead to a situation where there's a desire to connect different types of media together in order to make a cohesive or single network. Thankfully, media converters are readily available. The issue of trying to connect these disparate types of transmission together mostly comes into play when you're trying to join a fiber optic transmission to a copper wire infrastructure. And that's actually represented in the types of readily available media converters that are out there. The most common media converters will connect single mode fiber to Ethernet, or multi-mode fiber to Ethernet, or single mode fiber to multi-mode fiber, and finally there is a fiber to coaxial cabling media converter. You need to be aware that these devices are out there to help you create a solid network. Now let's move on to cabling tools. So every technician should put some thought into the tools that are in his or her toolbox. It is often said that you get what you pay for, and that is very true with tools. While a good technician can get away with buying the most inexpensive tools, by spending a little more money for a better tool, that can often make the task easier and ultimately make the technician more efficient. But you also need to be aware that you can spend more money than is necessary and not utilize all of the features in a given tool. So you need to find that balance point between spending too much money and not spending enough money to become a really efficient technician. Now let's move on to the tools themselves, and we'll begin with crimpers. Crimpers are used to place cable ends on cables. They can be designed to work with a single type of cable, as in twisted pair, or with multiple types of cable. I've seen some crimpers that have been able to work with RJ11s, RJ45s, and with a coaxial F connector. Next up are wire strippers. Wire strippers are used to remove the insulating covers on wires and cables. Many are designed to just cut through the insulation without damaging the cable contained within that insulation. But some are also designed to cut all the way through the cable so that excess cabling can be trimmed. When you're using those to cut insulation, you need to be careful that you don't cut the underlying cable. Then there are punch-down tools. These are used to secure cable wires into punch-down blocks. A good punch-down tool will trim the ends at the same time as it places the wire in the punch-down block. Then there are cable testers. These are used to test cables for common problems, as in misconfiguration of the ends or incorrect pinouts. Cable testers will often test for the cable standard used, either the T568A or the T568B, or they can tell you whether or not you've created a crossover cable. Cable testers will test for shorts or breaks in the continuity of the cable. Some types of testers can also test for cable length and quality. These type of testers are called cable certifiers. Then we have the TDR, the Time Domain Reflectometer. Now this is a cable tester for copper cabling that can determine the length of a segment and the electrical characteristics of the cable. Also, a TDR can tell you where a break is in a segment. A TDR is capable of performing all of the same tests that a cable tester can, but they are much more expensive than a standard cable tester. This is where you can spend too much money and not utilize all of the features available in the tool. Let's conclude this with the OTDR, the Optical Time Domain Reflectometer. It performs all of the same functions that a TDR can, but it is specifically used for fiber optic cabling. Now that concludes this session on network cabling part 3. I briefly talked about media converters, and then I brought up some cabling tools that you need to know about. Hello, I'm Brian Farrell, and welcome to PACE IT's session on network topologies. Today we're going to discuss what a topology is, then we're going to discuss peer-to-peer and client-server networking, and then we're going to talk about some common network topologies. And with that, let's go ahead and begin this session. So what is a topology? Well, a topology is basically a map that can be used to describe how a network is laid out or how a network functions. A network topology can be described as either being logical or physical. A logical topology describes the theoretical signal path, while the physical topology describes the physical layout of the network. And you should know that a logical and physical topology don't need to match. And with that, let's move on to peer-to-peer versus the client-server networks. So are these really topologies? No, not really. They don't describe the signal path or the physical layout of the network. But yes, they are topologies because they do describe how the network functions. So that's why they're here in this discussion. Now, in a peer-to-peer topology, the nodes control and grant access to resources on the network. No one node or group of nodes controls access to a single specific type of resource. There's no real server present. Each node is responsible for the resources it's willing to share. Now, a client-server topology differs. Network resource access is controlled by a central server or servers. A server determines what resources get shared, who is allowed to use those resources, and even when those resources can be used. Now, in the small office, home office, it's common to find a hybrid topology. That's where a combination of peer-to-peer and client-server networking is used. Now let's move on to some common network topology models. The first one we're going to discuss is the bus. The original Ethernet standard established a bus topology for the network, both logically and physically. And what I mean by a bus topology is the signal traveled along a predetermined path from end to end. It went from one direction to the other direction, and then it could come back. Now, as time went on, the bus developed some mechanical problems. That led to the development of different physical topologies. But the logical topology remained the same in order to maintain backward compatibility. So when we discuss Ethernet networks, the logical topology is always a bus topology, while the physical topology can be different. So let's talk about the bus again. The signal traverses from one end of the network to the other. Now, a break in the line breaks the network. The ends of the bus line needed to be terminated in order to prevent signal bounce. And what that means is that if there was a break or the ends of the line were not terminated, when the signal got to the end, it would bounce back through and create a storm. In a bus topology, the network cable is the central point. Now, kind of related to the bus is the ring. It's a bus line with the endpoints connected together. A break in the ring breaks the ring. In a ring topology, it's common to use two rings, multiple rings, that counter-rotate. This safeguards against a break in one ring bringing down the whole network. Now, ring topologies are not very common anymore in the LAN, but they're still used in the wide area network, especially when SONET or SDH is used. Moving on from the ring, we have the star. The nodes radiate out from a central point. Now, when a star topology is implemented with a hub, a break in a segment brings down the whole bus because the hub retransmits out all ports. Now, when it's implemented with a switch, a break in a segment only brings down that segment. It is the most common implementation in the modern LAN. Then there's the mesh. A true mesh topology is when all nodes are connected to all other nodes. That's a full mesh. Now, those aren't very common because they are expensive and difficult to maintain. But it's common to find partial meshes. That's where there are multiple paths between nodes. Now, everyone knows at least one partial mesh network, and that would be the internet. Now let's move on to the point-to-point topology. That's where two nodes or systems are connected directly together. Now, if you're talking about two PCs, that's when they use a crossover cable to create a point-to-point topology. There's no central device to manage the connection. Now, this is still a common topology when implemented across a WAN connection, utilizing a T1 line. We also need to discuss point-to-multipoint. In a point-to-multipoint topology, a central device controls the paths to all other devices. This differs from a star in that the central device is intelligent. Now, wireless networks often implement point-to-multipoint topologies. When the wireless access point sends, all devices on the network receive the data. But when a device sends, its message is only passed along to the destination. It's also a common topology when implementing a WAN across a packet-switched network. Now let's discuss MPLS. MPLS is multi-protocol label switching, and it is a topology that's used to replace both frame relay switching and ATM switching. It's a topology because it specifies a signal path and layout. MPLS is used to improve the quality of service and flow of network traffic. It uses label edge routers, LERs, which add MPLS labels to incoming packets if they don't already have them. Now the LERs add the labels and pass the packets along to LSRs, label switching routers. These forward packets based on their MPLS labels. That's what makes this a topology. Now that concludes this session on network topologies. We discussed what a topology is, then we discussed the differences between peer-to-peer and client-server networking, and then I brought up some common network topology models that you should know. Good day, I'm Brian Farrell, and welcome to PACE IT's session on network infrastructure implementations. Today I'm going to be talking about design versus function, and then I'm going to talk about categories of different networks. And with that, let's go ahead and begin this session. Let's begin this session by talking about the difference between design and function. When describing a network, you have a couple of different options. Are you describing its design or its function? If you are going to describe its design, then the first place to start is to describe its topology. Is it a bus network? Is it a star network or a point-to-point? But if you're going to describe how the network functions, then the first place to start is to describe the category or infrastructure implementation of that network. And with that, let's move on to categories of networks. First up is the local area network, or the LAN. Most LANs are encompassed by a single network address range. That address range may be broken up into subgroups through the use of virtual local area networks, VLANs. A LAN can span anywhere from a small area, like a single room, to a whole building or a small group of buildings. The LAN tends to be the highest speed network. It is becoming more common to see 10 gigabits per second networking on the LAN. The most common types of network on the LAN are the 802.3 or Ethernet and or the 802.11 or wireless local area network. These are the most common types of network found on the LAN. Then there is the Metropolitan Area Network, or the MAN. It is larger than a LAN. Most often, it contains multiple local area networks. MANs, or Metropolitan Area Networks, are often owned by municipalities. When a MAN is owned by a private entity, it is sometimes called a campus area network. Then there is the WAN, the Wide Area Network. Now, a WAN spans significant geographic distances. They can be described as a network of networks, and the best example of a WAN is the internet. So how do you tell when a MAN becomes a WAN? Well, as a general rule, if all of the infrastructure implementation has a single owner, then it is not a WAN. If it's large, it'll be a MAN, and if it's not quite so large, it'll be a LAN. But it's really easy to tell a personal area network, a PAN. Why? Because they are extremely distance and size limited. Most often, a PAN is a connection between only two devices. Common examples include a Bluetooth connection between a keyboard and a computer. That's a PAN. Then there are infrared or IR connections between a smartphone and a printer. That's a PAN. Another example of a PAN is near-field communication, which is now becoming seen between a smartphone and a payment terminal. The PAN tends to have low throughput of data and low power output. They don't consume a whole lot of power. As the distance between devices increase, the throughput on a PAN will decrease. Now a couple of special categories of networks. And first is the Supervisory Control and Data Acquisition Network, the SCADA network. Now a SCADA network is a type of industrial control system, or ICS, that is designed to control large-scale deployments of equipment. The controlled equipment is usually at more than one site. SCADA is often deployed in energy distribution systems by utility companies. SCADA uses a distributed control system, or DCS, to communicate with programmable logic controllers, PLCs, and or remote terminals to control the equipment and processes from a central location. So they have a central location to control equipment that's at remote locations. SCADA networks are often proprietary and often require additional training to understand them and to operate them. The last special mention on categories of networks is the MediaNet. It's a network designed and implemented specifically to handle voice and video. They are designed and implemented to remove quality of service issues like latency or jitter that can occur in other types of infrastructure. A video teleconference network, or VTC, is an example of a MediaNet. They are often implemented as its own infrastructure or as a sub-infrastructure of a larger network. That concludes this session on network infrastructure implementations. I talked about the differences between design and function of networks, and I concluded with a discussion on the different categories of networks. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to IPv4, Part 1. Today we're going to be talking about the purpose of IP addressing, and then we're going to move on to some IPv4 address properties. There's a whole lot of ground to cover, and we need to do it quickly, so let's go ahead and begin this session. Of course, we're going to start with the purpose of IP addressing. When Bob on Network A wants to view a web page hosted on a server on Network C, how does Bob's computer know where to send him? Well, somehow Bob has gotten that server's IP address, either in IPv4 format or IPv6. IP addresses are the location of a PC or server or some other network device that identifies it by both its network location and host location within that network. IP addressing provides a logical addressing scheme for our computers so that they can communicate on networks. Being logical means that the IP address can be changed with minimal fuss at any time, unlike the MAC address, or the Media Access Control address, which is physically embedded into the device. On the other hand, IP addresses are programmed in and are easily changed. Now that we know the purpose of IP addressing, let's move on to some IPv4 address properties. IPv4 is made up of a 32-bit binary number. That means there are 2 to the 32nd power possible address combinations. That gives us 4,294,967,296 possible address combinations. With all of these possibilities, a process needed to be developed to keep everything neat and tidy. and, most of all, findable. The implementation of a subnet mask was the answer, and I'll get to that subnet mask in just a moment. Something that you will find useful is learning how to convert from binary to decimal. Now, decimal is base 2. That means there are only zeros and ones, as opposed to the base 10 that we're all used to dealing with. If you would like more information on how to convert from decimal to binary or binary to decimal, you can go to that website that's listed under this heading. So now let's talk about the initial properties of IPv4. It is a 32-bit binary number, as I said before. It's divided into 4 sets of 8, called octets. These are separated by periods, or decimals. Each octet is 8 bits, which equals 1 byte. We often represent IPv4 addresses in a human-friendly format that's called dotted decimal. Now, when we look at this address, 192.168.1.9, that is an IP address, but we don't know which portion is the network or which portion is the host. To be able to resolve this, it requires the use of a mask which determines or defines which portion is which. This mask is called the subnet mask, and the subnet mask has the same format as the IP address, as in it's 32 bits and it's represented in dotted decimal format. So let's take a look at how an IP address and subnet mask operate together. So we're going to begin with 192.168.1.9 with a subnet mask at 255.255.255.0. Now the 192.168.1.9 is the IP address, like I said, and the other portion, the 255.255.255.0, is the subnet mask. And it's easiest to show how the subnet masks by converting that dotted decimal back into binary. So we can do that by deconstructing the IP address. So the first octet would be 11 followed by 6 zeros. That equals 192. The second octet is 10101 followed by 3 zeros. That equals 168. That third octet's real easy. It's 7 zeros followed by a 1. And then we have the fourth octet, which is 4 zeros, a 1, 2 zeros, and a 1. That equals 9. Now if we deconstruct the subnet mask, what we have is we have 3 octets that are full of 1s and 1 octet that's full of zeros. That represents that 255.255.255.0. Now if we put the subnet mask under the representation of the IP address, anything that's not covered by a 1 in the subnet mask is a part of the host address. Everything that is covered by a 1 is the network address. So what we have for that IP address is that 192.168.1 is the network portion of the address, and the node portion of the address is the 9. And that's how the IP address and subnet mask work together to define the network and the node. Now that concludes this session on the Introduction to IPv4, Part 1. We talked about the purpose of IP addressing, and then we moved on to some IPv4 address properties. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to IPv4, Part 2. Today we're going to talk about classes of IPv4 addresses, and then we're going to move on to classless IPv4 addressing, and we will conclude with a brief discussion on subnetting IPv4 addresses. There's a whole lot of technical information to cover, so let's go ahead and begin this session. Let's begin by talking about classes of IPv4 addresses. Internet Protocol version 4, IPv4, is a binary addressing scheme that's used for networking. It was initially finalized as a standard in 1981. IPv4 is a common network addressing scheme that is still being deployed today. There is an issue, though, with IPv4. Because of its structure and the growth and popularity of the internet, most of the world has run out of assignable IPv4 addresses. But thanks to some forethought, it's still a valid scheme today. We need to talk about classes of IPv4 addresses, and we begin with a Class A network address. Class A networks have an address range of 0 to 127 in the first octet. That gives us addresses from 0.0.0.0 up to 127.255.255.255. The first octet on the left has a binary representation that always begins with a 0. This gives us a possible 16,777,214 host addresses, and the subnet mask with a Class A network is always 255.0.0.0. Then there are Class B network addresses. They have an address range of 128 to 191 in the first octet. That means that Class B networks can have a range of 128.0.0.0 up to 191.255.255.255. The first octet on the left always has a binary representation that begins with a 10. Now, Class B network addresses give us a possible 65,534 hosts. And the subnet mask used with a Class B network is always 255.255.0.0. Then there are Class C network addresses, and they have an address range in the first octet of 192 up to 223. That means that we have an address range of 192.0.0.0 up through 223.255.255.255. And that first octet on the left always begins with a 110. Class C network addresses give us a possible 254 host addresses or node addresses, and the subnet mask with a Class C is always 255.255.255.0. The last class of address that you need to concern yourself with is the Class D network address. It has an address range of 224 up through 239 in the first octet, which means that it can range from 224.0.0.0 up through 239.255.255.255, and that first octet on the left has a binary representation of 1110. So the first 4 bits are always taken, and they are always 1110. Now, subnet masks are not defined for Class D networking. Class D network addresses are used for multicast communication. And finally, we have a special class of addresses. Well, kind of a class of addresses. And that involves automatic private IP addressing, a PIPA. In some cases, the Dynamic Host Configuration Protocol, DHCP, process may fail. In these cases, a node or host will self-configure an APIPA address. Now, with an APIPA address, the first 2 octets are always 168.254. And if you see that in your IP configuration, you know that you have a DHCP problem. So one of the first methods that they used to conserve the IPv4 address space was they broke them out into public and private IP addresses. Public IP addresses are routable. And being routable means that each public IP address is unique. There can only be one. Now, public IP addresses are not flexible. You are assigned to your network space. You're not really given a choice what your public IP address is going to be. And then there are the private IP addresses. These are non-routable. They do not need to be completely unique throughout the world. They only have to be unique on their network. The first one that we're going to discuss is the Class A license. There is only one Class A license. you have a possible address range of 10.0.0.0 up through 10.255.255.255. Next up is the Class B license. There are 16 possible network addresses, not network and host, but just network addresses available in a Class B license. They have an address range of 172.16.0.0 up through 172.31.255.255. And last but not least is the Class C license. There are 256 Class C licenses, with a possible address range of 192.168.0.0 up through 192.168.255.255. Now, private IP addressing is highly flexible. You get to assign the network space, it's not assigned to you. Now let's move on to classless IPv4 addressing. Now, the classes of addresses actually limited the flexibility of IPv4. Part of the reason for that was that the first routing protocols required the class structure. And you would think that with over 4 billion possible IP addresses that we'd still have flexibility, but we really didn't. Classless addressing, which is called Classless Interdomain Routing, or CIDR, was developed to slow the growth of routing tables. It also slowed the exhaustion of IPv4 addresses. It also created much more flexibility. The subnet mask becomes fluid. It's not rigid with CIDR addressing. It does not affect the private address space ranges, though. Even though the subnet mask is now fluid, you still only have those range of addresses available. And with the introduction of classless addressing, subnetting is now possible and it's highly desirable. So let's take a look at how CIDR notation works. And we'll begin with 192.168.0.9 with a subnet mask of 255.255.0. What that becomes is 192.168.0.9/24. That /24 represents all of the ones in the subnet mask. And that's those first 3 octets on the left, the 255.255.255. And if you look at that address, it's a Class C address, which always has a 255.255.255.0 subnet mask, but it now becomes fluid with CIDR. We can take it and we can make it a 192.168.128.0/23. And what that really represents, that /23, is a subnet mask of 255.255.128.0. And that gives us a network of 192.168.128.0, which actually gives us a host range of 192.168.128.1 through 192.168.129.254. That gives us 512 host addresses as opposed to the possible 254. Now, the broadcast address for that network would be 192.168.129.255. So now let's move on to subnetting IPv4 addresses. So what is subnetting? Well, subnetting cuts address spaces into smaller pieces. It takes one range of addresses and splits it. This creates flexibility in network design and creates efficiency in address space utilization. So let's take a look at an example of subnetting. And this will involve a small office network. So originally, we have a network address of 223.15.1.0/24. This is a Class C private network, and it gives us a possible 254 hosts available. Why only 254? Well, because a host cannot be assigned the network address, which is 223.15.1.0, and it can't use the broadcast address, which is 223.15.1.255. In this example with this network address, all the hosts in the network can see all the other nodes. Now let's say that for security considerations, you want to split this into two networks. Well, you can do this using subnetting. So what you do is you take that /24 network and you create two /25 networks. And those would be 223.15.1.0/25 and 223.15.1.128/25. In this situation, the first network's host address range would be 223.15.1.1 up through 223.15.1.126. And why is that? Well, because you can't use the network address, which is 223.15.1.0, and you can't use the broadcast address, which is 223.15.1.127. The second address range that would be created through this subnetting process would give us a host range of 223.15.1.129 up through 223.15.1.254. That's because you can't use the network address, which is 223.15.1.128, and you can't use the broadcast address, which is 223.15.1.255. Each of those subnets would have 126 possible host addresses. So you took your possible 254 hosts available in one network and you broke it down so that you now have two separate networks, each that's capable of having 126 hosts. And that's an example of subnetting an IPv4 address. Now that concludes this session on the introduction to IPv4 Part 2. I talked about classes of IPv4 addresses. I then moved on to classless IPv4 addressing, and we concluded with a brief discussion on subnetting IPv4 addresses. Good day, I'm Brian Farrell, and welcome to PACE IT's session on the introduction to IPv6. Today we're going to be talking about the IPv6 address structure, and then we're going to move on to IPv6 network transmissions. And with that, let's go ahead and begin this session. Of course, I'm going to begin by talking about the IPv6 address structure. Now, IPv6 is the answer to the question of what do we do about running out of IPv4 addresses? Unlike IPv4, IPv6 will provide enough Internet Protocol, IP, addresses for the foreseeable future. Now, shortly after the creation of IPv4 and its implementation, the IANA, the organization that's tasked with assigning routable IP addresses, realized the available IPv4 address space would not be enough in very short order if nothing was done. The IANA then set about creating the replacement, and they initially started by working on IPv5. While they were working on IPv5, they found that due to the popularity of the internet, which was increasing at that point in time, that it wasn't going to be enough. So they scrapped IPv5 and began working on IPv6. Now the IANA is confident that IPv6 will function as the replacement for IPv4 for many decades to come. Why are they so confident? Well, we'll get to that here in just a moment. Now, IPv6 works at layer 3 of the OSI model, just like IPv4 does. Layer 3 of the OSI model is also known as the network layer, and its major focus is logical network and host addressing. IPv6's job is to provide logical network and host addressing to devices. IPv6 is a 128-bit binary addressing scheme as opposed to IPv4's 32 bits. The 128 bits are grouped together in sets, with each set being separated by a colon. Now each of these sets is 2 bytes long, and a byte is 8 bits. For human readability, the binary IPv6 number is converted to hexadecimal. That's base 16. with each hexadecimal number being equal to 4 bits. Now those 4 bits can actually be referred to as a nibble because it's half of a byte. An IPv6 address is 8 sets of 4 hexadecimal numbers, each being separated by a colon. That means that there are over 340 undecacillion addresses available to IPv6. That's 2 to the 128th power, which is roughly equal to 340 times 10 to the 36th power. See that number there? I'm not even going to begin to read that one to you. So now let's talk about IPv6's local address structure. For the local address, the first 64 bits on the left represent the local network, and the last 64 bits on the right always represent the host. The local address structure follows the EUI, or Extended Unique Identifier, format, specifically the EUI-64 format. For those hosts that have a 48-bit MAC address, that 48 bits is actually padded with an extra 16 bits to make it 64 bits in length. You can always tell a local address, which is also called the link local address, as it always begins with an FE80. With IPv6, every device gets both a local address and it gets a global address. Now the global address is unique. There is only one, and every device gets one. The host address is still always the last 64 bits, but every device actually gets assigned to a global network. The network portion is actually composed of a routing prefix and a subnet. This portion of the global address structure follows the classless interdomain routing, or CIDR, convention, with the number that follows the slash denoting the routing prefix. That's the part of the extremely global network that you belong to. The subnet is composed of the bits between the prefix and the EUI-64 host address. Global IPv6 addresses always begin in the range of 2,000 up through 3,999 in that first group of numbers on the left. Now, in most cases, the need for Dynamic Host Configuration Protocol, DHCP, has been eliminated. When implemented, IPv6 will auto-configure both the local and the global addresses that are required for their networks. When a device first comes online, it will use the Neighbor Discovery Protocol, NDP, to discover what the required network addresses are, both the local and global addresses. This allows devices to configure its own IPv6 address without an administrator's intervention. So let's talk about IPv6 notation. The 128-bit nature of IPv6 makes it cumbersome to write out, and it can take up unnecessary space. Because of this, some rules were developed to ease the burden and save space. When you're looking at a group of IPv6 numbers, any leading zeros in a set can be dropped. The thing to really remember about IPv6 is that only a single set of consecutive zeros may be replaced with the double colon. Why is that? Well, because if you could do it more than once, how would routers and other devices know how many zeros to pad in there? Even with this ability to shorten it, it's still difficult for us to remember IPv6 addresses, but it is still easier to write out, and it still conserves space within systems. Now let's move on to types of IPv6 network transmissions. And we begin with the unicast. Unicast is one-to-one communication. That is where a specific device is sending network traffic to another specific device. Unicast can occur on the local network, which remember always begins with FE80, or it can occur on the global network. Then there's multicast, which is one-to-a-few communication. With multicast, a specific device is sending network traffic to a specific group of devices that have registered to receive that traffic. Routers register to receive multicast transmissions that involve the routing protocols that they are programmed to use. With IPv6, multicast addresses always begin with an FF. Both IPv6 and IPv4 use both unicast and multicast transmissions. A unique type of transmission to IPv6 is anycast. Anycast is one to the closest communication. This is where a specific device is sending network traffic to a specific IPv6 address that has been assigned to multiple devices. The router only sends the communication to the closest one, at least from its perspective. Anycast transmission involves implementing DHCP v6. Earlier I said we really don't need to worry about DHCP anymore, but that's only partially true. While IPv6 is capable of auto-configuring its own local and global addresses, in certain situations that's not always desirable. DHCP v6 version 6 can be configured to hand out specific IPv6 addresses or duplicate IPv6 addresses when necessary. That's useful for when load balancing a network or when network redundancy has been created, or when you have a user that has a tablet, a cell phone, and a laptop, and you want to deliver the transmission to the closest device, the device that he's using at that point in time. That is where DHCP v6 comes in handy. IPv6 and IPv4 are not compatible, but we can do what's called a dual stack configuration. That's where the network and devices on the network receive both an IPv6 configuration and an IPv4 configuration. Or we can use what's called tunneling. There's 6-to-4 tunneling, which is used to encapsulate an IPv6 data packet in an IPv4 datagram, allowing that IPv6 packet to travel across or through an all IPv4 network. 6-to-4 tunneling can also be called Teredo tunneling. Now that concludes this session on the introduction to IPv6. I talked about the IPv6 address structure, and then I talked about IPv6 network transmissions. Hello, I'm Brian Farrell, and welcome to PACE IT's session on special IP networking concepts. Today I'm going to be talking about the Media Access Control Address, and then I'm going to talk about the difference between collision domains and broadcast domains, and we're going to conclude with types of network transmissions. There's a whole bunch of technical information to cover, so let's go ahead and begin this session. Let's begin the formal part of this session by discussing the Media Access Control Address. All networking interfaces come with their own special address already configured. That would be the Media Access Control Address, the MAC address. The MAC address is often referred to as the physical address or the burned-in address of the interface. While MAC addresses may be changed or spoofed, most often it's set by the manufacturer and never actually changes. Now, switches and other OSI Layer 2 devices rely upon that MAC address in order to get network packets to their correct destinations. The MAC address has a specific format. Actually, it has two specific formats. One is 48 bits in length and the other is 64 bits in length, and both of them are represented by hexadecimal numbers. Both formats can be broken down into two parts: the Organizationally Unique Identifier, or OUI, and the Extended Unique Identifier, the EUI. The Institute of Electrical and Electronic Engineers, the IEEE, assigns all electronic manufacturers their own OUI, which always makes up the first portion of the MAC address. Each manufacturer then assigns its own EUI to each device that is produced. Usually it is the serial number of that device. Theoretically, no two interfaces will have the same MAC address. I need to mention the EUI64 format. IPv6 requires that the node address or the MAC address be in an EUI64 format. So that MAC address has to be 64 bits in length. If the EUI of the interface is only 24 bits in length, it is actually split into two parts, and 16 bits of padding are added to create the EUI64 format. Now let's discuss the difference between collision domains and broadcast domains. Before I can talk about collision domains and broadcast domains, I need to talk about carrier sense multiple access with collision detection. All Ethernet networks use this technology, also called CSMA with CD, when transmitting data. In an Ethernet network, all Ethernet devices have equal access to the network media and are capable of transmitting data at any time. This can lead to data collisions. With CSMA CD, a device listens to the carrier signal on the network media. If no other device is transmitting, the device is free to send data. If another device sends data at the same time, a collision is possible, which can corrupt the data. The devices listen for collisions. That's the collision detection part. If a collision occurs, the devices will stop transmitting and wait a random period of time before attempting to transmit again. To do this, they use what is called a back-off algorithm. With that out of the way, now let me explain what collision domains are. Collision domains are an area of the network where packets or network traffic can collide. There are some devices that break up collision domains. They can be broken up by switches, bridges, and routers, but not by hubs. On the other hand, a broadcast domain is defined as all the nodes that can be reached by a broadcast transmission. All the nodes that can be reached reside in the same network. Broadcast traffic cannot pass routers, so the domain is also defined by the subnet mask, and that subnet mask defines the network. Here's a special note. Technically, IPv6 does not use broadcast transmissions. IPv6 replaces broadcast transmissions with multicast transmissions. And what do you know? That's a good segue for us to discuss types of network transmissions. We're going to begin this section by talking about types of IPv4 network transmissions, and first up is unicast. Unicast is a specific source address transmission going to a specific source destination address. It can be thought of as one-to-one communication. It's only two devices transferring data between each other. Then there's multicast transmission. This is where a specific source address transmission is going to a set of registered destination addresses. This is one-to-a-few communication. Routers often use multicast transmissions to track their routes and to make changes to their routing tables. And finally, there are broadcast transmissions. This is where a specific source address transmission is going to all addresses on the local network. This can be considered as one-to-all communication, because all devices on the local network are going to be able to receive this broadcast transmission. So let's move on to types of IPv6 network transmissions. And IPv6 uses unicast, just like IPv4 does. IPv6 also uses multicast, just like IPv4. Where IPv6 differs is with anycast transmission. Anycast is where a specific source address transmission is going to a specific IPv6 address that has been assigned to multiple devices. The router uses an algorithm to determine which MAC address that has that specially configured IPv6 address is closest, and only that device receives the Anycast transmission. Anycast can be considered as 1 to the closest communication. That concludes this session on special IP networking concepts. I talked about the MAC address. I talked about the differences between a collision domain and a broadcast domain. And then I concluded with a discussion on the types of network transmission. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Introduction to Routing Concepts, Part 1. Today I'm going to talk about the purpose of routing, and then I'm going to move on to some basic routing concepts. There's a fair amount of ground to cover, so let's go ahead and begin this session. First up is the purpose of routing. The basic purpose of routing is to connect different networks together to allow them to communicate and pass data traffic between them. Most often, routing protocols are how networks determine where to send network traffic, that's the routes that they will take, and these routing protocols build maps. Actually, they build routing tables, but we'll get to that later, that they use for directing network traffic. Routing is what makes this interconnected world function as well as it does. Networking would be pure chaos without it, as we'd have no idea where to send traffic. Now let's move on to some basic routing concepts. First up is static routing. Static routing uses administrator-defined routes. Each router in a static routing configuration must contain the route. A static route from router A to router B requires that router B has a static route back to router A in order for two-way communication to take place. If we had a static route from A to B and B didn't have one back to A could send traffic to B, but B could not send traffic back to A. Now, static routing is easy to set up in small networks, but it's not so easy to maintain. Networks change all the time. With static routing, when a change occurs in routers, the administrator has to go around to each router and implement that change. Then there's dynamic routing. This is where routers use protocols in order to determine the best route between two networks. The administrator determines which protocols will be used on the routers. In order for the routers to communicate, they must all be using the same protocols. There is an exception to that, and that's route redistribution. An administrator can configure a router to take one dynamic protocol and transform it into a different routing protocol to be used from that point on. This is the only case when routing protocols can be different across a network. Routing protocols can be stacked within a router. That means that there can be more than one dynamic routing protocol programmed into a router. Dynamic routing is very fluid and dynamic, and it's what makes possible today's interconnected world. The next concept is the default route. The default route is the direction that a router will send network traffic when there is no known route in the routing table. The default route is assigned by an administrator. It is usually a designated interface on the router, or it is the next designated next hop interface. Then there is the routing table. The routing table is a list of known routes to all known networks from the router's perspective. It is established by an administrator when static routing is used. It is dynamically built by routing protocols when dynamic routing is employed. Each routing protocol maintains its own routing table. Different routing protocols may have different routes to the same network. The loopback interface is an administratively configured logical number assigned to a router to ease administrative functions or routing processes. Often the loopback interface is assigned in an IPv4 address format even when IPv4 isn't used on the router. Many routing protocols have been designed to take the loopback interface into account when performing administrative functions. The loopback interface may be completely logical, or a physical interface may be assigned to be the loopback interface. Let's move on to routing loops. A routing loop is a possible problem that can be created if interconnected routers have a breakdown in their routing algorithms. When a routing loop occurs, network traffic keeps looping through the routers until some system or mechanism breaks the cycle. Routing loops can create network congestion or even bring down a network. Routing protocols use multiple methods to prevent routing loops from occurring. One of the main methods that they use is what's called the time to live field, or the TTL field. The TTL field keeps track of how long that packet has been in existence and how far it has traveled, and after a specified amount of time or distance, it will inform the next router to drop it. This helps to prevent routing loops. That concludes this session on the Introduction to Routing Concepts, Part 1. I talked about the purpose of routing, and then I moved on to some basic routing concepts. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Introduction to Routing Concepts, Part 2. Today I'm going to be talking about routing metrics, routing aggregation, and then I'm going to conclude with a brief discussion on high availability. We have a fair amount of ground to cover, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about routing metrics. It is quite common for there to be more than one route available to a remote network. Routing protocols use metrics to determine which route is the best route to reach those remote networks. Each routing protocol will use its own set of metrics in determining which routes to which networks are placed in its routing table. The same basic metric may be used by different routing protocols, but when this occurs, the metric is usually implemented in a different manner through the use of different algorithms. The first metric that we're going to discuss is the hop count. The hop count is the number of routers between two endpoints. This is determined from the sending router's perspective. The maximum transmission unit, or MTU, is another metric that is used by routing protocols. The MTU is the maximum allowed size of a packet measured in bytes that's allowed through an interface. The standard MTU for Ethernet is 1500 bytes. Packets that exceed the MTU must be fragmented into smaller pieces, leading to more packets, leading to a slower connection. Bandwidth is another common routing metric. Bandwidth is a measure of the speed of the network connection. The speed is commonly measured in either kilobits per second, megabits per second, or gigabits per second. Another common metric is latency. Latency is a measure of time that a packet takes to traverse a link. When latency is implemented by routing protocols, the total amount of latency or delay to go end to end between 2 points is what is used in the metric. The administrative distance, or AD, is probably the most important metric that's used on routers. The administrative distance is the believability of a routing protocol's advertised routes. Different routing protocols are considered to be more believable or trustworthy than others. Routers use the AD to help determine which routing protocol to use when more than one protocol is installed on the router. The lowest AD of an advertised route will determine the protocol that's used. There are some common standard administrative distance. First up is the directly connected route. That's a direct link between two routers. That has an AD of 0, and it is the most believable or trustworthy of routes. Next is the statically configured route. It has an AD of 1. External Border Gateway Protocol has an AD of 20. It's still fairly trustworthy. Internal EIGRP has an AD of 90. It's not as trustworthy as BGP, but it is more trustworthy than OSPF, Open Shortest Path First, which has an AD of 110. ISIS has an AD of 115, so not quite as believable as OSPF, but more believable than RIP, which has an AD of 120. External EIGRP has an AD of 170, and internal BGP, and I've never seen internal BGP used, has an AD of 200. Now, if you see an administrative distance of 255, that means that that route is not believable at all. As a side note, the AD can be set by an administrator. So if you are running both OSPF and ISIS on a router, but you want ISIS to be used, you could actually set OSPF's AD to a higher number than ISIS, and then ISIS would always be used before OSPF. Now let's move on to route aggregation. Without some mechanism put in place, routing tables would soon become very large and highly inefficient. Through careful planning, network administrators use a process called route aggregation to condense the size of routing tables. They do so through the use of classless interdomain routing, CIDR, to summarize routes to different networks. Route aggregation is common in networking. Let's take a look at an example of route aggregation. Suppose we have a router that has the following networks on its serial 0/1 interface. It has 10.1.1.0/24 known on that interface, 10.1.17.0/24, 10.1.32.0/24, and 10.1.128.0/24. All of those networks are known to that interface, that S/0/1 interface. These routes are what are known as contiguous routes. They're all in a line. They can be summarized or aggregated by a common CIDR entry in the routing table. They could all be summarized by the following entry, 10.1.0.0/16. Now there is a warning about route aggregation. Route aggregation takes careful planning during the network design phase. That above example would not work if the serial interface 1/1 on that same router was connected to network 10.1.2.0/24, because that new network makes those networks on the 0/1 interface non-contiguous networks. All the known networks are no longer all in a row. This leads to the fact that the routes could no longer be aggregated or summarized. Let's conclude with a discussion on high availability. Part of a network administrator's job is to ensure that networks remain up and active for the maximum amount of time. In an effort to ensure that networks don't go down, administrators often remove single points of failure. A single point of failure in a network is the point where a single failure will cause the network to cease functioning. Network administrators often use high availability techniques in order to remove those single points of failure. An example of a high availability technique is the use of redundant links to outside networks. Hot Standby Router Protocol, HSRP, is a specific example of a high availability technique. HSRP is a proprietary Cisco method of creating a fault-tolerant link using two or more routers with connections outside of the local subnet. The two routers are connected together as well as having connections outside of the local network. A virtual IP address is created and shared between the two routers. Devices on the network are configured to use that virtual IP address as their default gateway for packets leaving the network. If a single router goes down, the link outside of the network is still available. Another high availability technique is Virtual Router Redundancy Protocol, VRRP. It is an IETF, Internet Engineering Task Force standard that is similar in operation to HSRP. That concludes this session on the Introduction to Routing Concepts, Part 2. I discussed some routing metrics, then I moved on to route aggregation, and I concluded with a brief discussion on high availability. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to Routing Protocols. Today we're going to be talking about some of the differences between interior and exterior gateway routing protocols. We will introduce some more routing concepts, and then we will end with routing protocols in themselves. There's a whole lot of stuff to cover, so let's go ahead and jump into this session. Let's begin with a comparison between interior and exterior gateway protocols. Interior gateway protocols, or IGPs, are a category of protocols used within autonomous networks. Autonomous networks are networks that you control or that are under the control of a single organization. The most popular IGP protocols are OSPF, Open Shortest Path First, and RIP version 2. That's Routing Information Protocol version 2. Now there is a special mention here, and that's ISIS, which is Intermediate System to Intermediate System. ISIS is popular with extremely large autonomous networks, like an ISP's, or Internet Service Provider's, network. Exterior gateway protocols, on the other hand, are a category of protocols used between non-autonomous networks. So EGPs are used between networks that are controlled by different organizations or entities. The most popular EGP protocol is Border Gateway Protocol. Now, it's not uncommon for organizations to have more than one network that they are routing traffic between. These are called autonomous networks. Some IGP routing protocols use an administrator-defined Autonomous System Number, or AS number, as one means of identifying which networks can directly communicate with each other. The Autonomous System Number is not a metric, but a means of identifying a network that might possibly accept another network's traffic. Something to remember is that the AS is only significant within autonomous networks and has no relevance outside of them. Now let's move on to more routing concepts. Routing protocols can be classified by how they perform their routing. Interior gateway and EGP routing protocols can be broken out into three other categories of protocols, which is designated by their main method of determining routes between networks. The first class of routing protocols are distance vector routing protocols. With distant vector routing protocols, the routes are determined by how many routers exist between the source and the destination. The efficiency of the links in the selected route is not taken into consideration. With distance vector protocols, periodically the whole routing table is broadcast out onto the network. Then there are link state routing protocols. Metrics are used to determine the best possible route between destinations. Doesn't really matter how many hops there are. Once the route has been established, these protocols then only monitor the state of directly connected links and only make changes to their routing tables when changes to the links occur. With link state routing protocols, only changes in link status are broadcasted. And finally, there are hybrid routing protocols. These use aspects of both the distance vector and link state routing protocols. Let's talk about the next hop. The next hop is the next router in the path between 2 points. The next hop is often designated by an interface address of the device that is receiving the data, or by that router's name, or by that router's location. The routing table is the database table that is used by a router to determine the best possible route between 2 points. Different routing protocols use different algorithms to place routes in the routing table. The next concept is convergence. Convergence can be thought of as steady state. Convergence is measured in the amount of time that it takes all of the routers in an autonomous system to learn all of the possible routes within that system. Faster convergence times are desirable as that steady state allows routing to occur more quickly. Now let's move on to the routing protocols themselves. First up is Routing Information Protocol version 2, RIP version 2. RIP is an IGP distance vector protocol. For a route to be placed in the routing table, it can be no more than 15 hops away. A hop count of 16 is considered unreachable. It uses various methods, including the hop count, to reduce the chances of a routing loop occurring. RIP version 2 uses multicast address 224.0.0.9 to advertise its routing table. Open Shortest Path First, OSPF, is the most popular IGP that's currently being used. It is a link state routing protocol. It uses the Dijkstra algorithm to determine the shortest path to a network. After its initial startup, it only advertises changes to its routing table, making convergence much faster. It uses different types of link state advertisements, or LSAs, to announce different changes or different operations. OSPF uses two multicast addresses, 224.0.0.5 or 224.0.0.6, depending upon the type of LSA that it's transmitting. Next up, intermediate system to intermediate system, or ISIS. ISIS is a link state routing protocol like OSPF, and similar to OSPF, it too uses the Dijkstra algorithm, but it uses different metrics to determine the best path. ISIS is highly scalable and offers fast convergence. ISIS is often found within networks under the control of an internet service provider. Then there's Border Gateway Protocol, BGP. It's an exterior gateway protocol that's also a hybrid routing protocol. It is considered the routing protocol of the internet, and as a hybrid protocol, it is often considered a path vector protocol, which makes it a hybrid. One of the metrics used is the number of autonomous systems that must be crossed, not individual routers. BGP is highly scalable, but has a very slow convergence time when changes do occur. As a special mention, I'm going to talk about Enhanced Interior Gateway Routing Protocol, EIGRP. It is an advanced distance vector, or hybrid, IGP routing protocol developed by Cisco. In 2013, Cisco made EIGRP an open source routing protocol in an effort to increase its use in autonomous networks. It uses aspects of both the distance vector protocol and the link state protocol to build its routing table. EIGRP has a very fast convergence time, but it's not as popular as OSPF because OSPF has been open source longer than EIGRP. EIGRP uses a neighbor table which is directly connected routers, and a topology table to build its routing table. The protocol only announces changes to the routing table on multicast address 224.0.0.10 in order to reduce bandwidth consumption. That concludes this session on the introduction to routing protocols. I talked about the differences between interior and exterior gateway protocols. Then I mentioned some more routing concepts, and we concluded with the routing protocols themselves. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Basic Elements of Unified Communications. Today I'm going to be talking about unified communications, and then I'm going to move on to some unified communication concepts, and then I'm going to end with voice over IP. And with that, let's go ahead and begin this session. Of course, I will begin this session by talking about unified communication. Now, unified communications is not encompassed by a single product or device. It's a growing category in the enterprise network. Unified communication, or UC, is the set of products and services that attempts to provide a consistent single user interface and experience across different media types and different devices. UC allows a user to send a message from one type of media, as in email, and have that media received as a different type of media. That email could become a text message or a voicemail. So now let's talk about some unified communication devices. First up is the UC server. These are specialized servers, which quite often are virtual in nature, that are designed to implement unified communication solutions in the workplace. The UC servers work in conjunction with UC gateways. A UC gateway is a network device that is designed to translate between different signaling methods, as in a voice over IP gateway, which will translate an analog public switch telephone network voice signal into a signal that can be understood on the VoIP network. There are some other UC devices. Any device that can be used in the implementation of a unified communication solution is considered a UC device. They may include, but are not limited to, VoIP phones, email systems, video conferencing systems, and instant messaging networks. Now let's move on to some unified communications concepts. The first concept that we're going to discuss is presence. Now, presence is an indicator that is used to communicate the willingness or ability of a user to accept communication. Common presence statuses include available, online, offline, busy, and do not disturb. Presence services are an important service provided in UC solutions, as they will track the individual users across multiple devices and networks in real time through the use of multicast transmissions. Once a communication session has been established, multicast communication is dropped and unicast network transmissions are used. Another UC concept that you need to grasp is quality of service. Quality of service techniques are implemented to improve unified communication by managing network traffic. The most common implementation of quality of service is class of service, COS. COS is a quality of service technique that's used to manage network traffic by grouping similar types of traffic and assigning a network priority to that traffic. As in, unified communication traffic is given a higher priority than email. A 6-bit differentiated service code point, DSCP, is used in the IP header to establish the COS, or class of service. Now let's move on to voice over IP. VoIP is one of the most common implementations in a unified communications solution. Through the use of a presence service, calls can be routed to the correct location for where the user is at. Two important protocols used in Voice over IP are Session Initiation Protocol, SIP, and Real-Time Transport Protocol, RTP. SIP has two purposes. First, it is used to establish a communication session between two endpoints. The other purpose is that once the session is completed, SIP tears down that connection between the two endpoints. During the communication session, RTP is used as the transport call, helping to provide that quality of service through COS to the endpoints. Now that concludes this session on the basic elements of unified communication. I talked about unified communications, then I moved on to some unified communication concepts, and I concluded with a brief discussion on Voice over IP. Good day, I'm Brian Farrell, and welcome to PACE IT's session on virtualization technologies. Today I'm going to be discussing the difference between a hypervisor and virtual machine manager. Then I'm going to move on to components of virtualization, and then I'm going to have a brief discussion on software-defined networking. I have a whole lot of information to impart, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin with hypervisors and virtual machine managers. So what is the difference between a hypervisor and a virtual machine manager? The difference could be nothing, or the difference could be everything. Some people use the term hypervisor very broadly. They use it to refer to any of the software that is used to manage virtual machines. Others will differentiate between the two terms in this way. A hypervisor does not need a host operating system, while a virtual machine manager, or VMM, requires a host operating system such as Microsoft Windows, Apple OS X, or a Linux operating system, while the hypervisor can operate as its own operating system. With that covered, let's talk about some of the components of virtualization. First up is the virtual desktop. A virtual desktop is a virtual machine, or VM, that functions as a desktop. Now, any modern operating system can be run inside of a VM desktop. Multiple virtual desktops may be hosted on or from a single host system. Then there are virtual servers, which surprisingly is a virtual machine that functions as a server. Any modern server operating system can be used in a virtual server environment. Multiple virtual servers may be hosted on or from a single host. Guess what? There are then virtual switches, firewalls, and routers. These are virtual machines that fulfill the functions of the switch, firewall, and router. Virtual firewalls and routers are particularly effective when they are combined with virtual network interface controllers, or virtual NICs, and virtual switches to create virtual networks. Speaking of virtual networks, an important consideration for when designing a virtual network is how that virtual network is going to pass traffic to remote networks, or networks outside of the host system. Virtualization by its nature leads to either an open and highly scalable network or a closed self-contained system. It is possible to create a completely self-contained network with all of the virtual components and never have network traffic leave the host machine. But if there is a desire or need for that network traffic to pass beyond the host system, then that function needs to be specifically granted. A connection must be created between the host system's physical NIC and the virtual networking equipment to allow network traffic to pass through the physical host system. Next up, software-defined networking. Software-defined networking, or SDN, is the process of allowing the administration and configuration of a network to be done dynamically. With SDN, the administrator uses a front-end program to make adjustments to the network. This program sends the instructions to the networking equipment, which is then reconfigured to perform as the administrator desires. SDN can allow network administrators to dynamically adjust network performance without the need to log into each individual device that needs to be adjusted to achieve the desired performance. SDN is considered to still be an emerging technology, but SDN also works well for virtual networks and cloud computing. Now that concludes this session on virtualization technology. I talked about hypervisors and virtual machine managers. Then I moved on to a brief discussion on some components of virtualization, and I concluded with another brief discussion on software-defined networking. Hello, I'm Brian Farrell, and welcome to PACE IT's session on storage area networks. Today I'm going to discuss the justification for storage area networks, and then I'm going to talk about storage area network technology. And with that, let's go ahead and begin this session. Of course, I'm going to begin with justifications for storage area networks. There have been several factors that have led to the increased demand for data storage. One of them has been the dramatic decrease in the actual cost of data storage. It actually costs us less now for storage on a per gigabyte basis than it has in the past. What has happened is that as the cost of storage has decreased, the demand for storage has increased dramatically. Businesses are now generating and analyzing huge amounts of data in an effort to create a competitive advantage. Think big data. I'm sure you've heard about big data recently. Or this increase in data collection has led to an increased demand for storage capacity. Another factor is that as the demand for data has increased, it has needed to be more available, which means that there has been a need to be able to access that data from anywhere, and the accessibility is needed to be increased as well, including from non-standard devices. A storage area network, or SAN, can be a solution to the need for both storage capacity and high availability. There are several advantages to the storage area network. First off is scalability. The amount of data that is being generated today is huge. This has led to a need to store that data. The SAN is more scalable than other options. As your storage needs increase, the capacity of the SAN can be easily increased to meet that storage need. Then there's data availability. The demand has also increased for that data to be available at any time from anywhere, and a SAN can play a vital role in creating that accessibility. One of the most popular implementations of a SAN is to deploy it as part of a cloud computing solution. This increases the availability of that data that's being stored on the SAN. And finally, there's optimization. As the requirements to store data are removed from application servers, those servers can then be optimized to run those applications much more efficiently. At the same time, data storage is also optimized. It's time now to discuss some SAN technology. The storage area network, or SAN, and the network attached storage, or NAS, often get confused with one another, but they are different. The SAN is an actual network of devices that have the sole purpose of storing data efficiently. On the other hand, the NAS is a specifically designed network appliance that has been configured to store data more efficiently than standard storage methods. The difference is that a NAS is a data storage appliance that is placed on a network, while a SAN is a network of data storage devices. It is not uncommon for a SAN to contain multiple NAS devices. With all of that data storage capabilities, several technologies have been developed to ease the transmission of that data. The first one that we're going to discuss is Fiber Channel, or FC. Fiber Channel is a high-speed network technology that was originally developed to operate over fiber optic cables only. Since its introduction, the standards have been modified to allow the use of copper cabling in conjunction with fiber optic cabling. Fiber Channel is commonly used to connect to SANs. When Fiber Channel is implemented, it uses the Fiber Channel Protocol, or FCP, as its transport protocol to transmit SCSI commands. So it transmits small computer system interface commands to storage devices, as in the NAS appliances. So a SAN implements FCP as opposed to TCP as its transport protocol when Fiber Channel is used. Another technology that was developed was Internet SCSI, or iSCSI. iSCSI is an IP-based networking standard that is used to connect data storage facilities and SANs. iSCSI allows for SCSI commands and processes to take place over longer distances than the original SCSI implementation. Jumbo frames are also allowed within the SAN environment. Jumbo frames allow for greater throughput of data by allowing up to 9,000 bytes of data to be in a single frame. This can greatly increase the efficiency of a SAN. As a comparison, the standard frame on an Ethernet network can only be a maximum of 1,500 bytes. Now that concludes this session on storage area networks. I talked about the justification for storage area networks, and then I concluded with a brief discussion on some SAN technology. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Basic Cloud Concepts. Today we're going to be talking about cloud classifications, and then we will conclude with different types of cloud computing. There's a fair amount of information to cover, so let's go ahead and dive right in. I will begin our session with a discussion about cloud classifications. Cloud computing is where the resources on the network are not actually physical in nature. They are provided to the end user virtually. Cloud computing can lead to a very fluid and dynamic environment, as the required resources are normally only provisioned or supplied as needed and are decommissioned or shut down once their use is done. Most often, these virtual resources are not owned by the company or user that uses them, but are provided by a service provider. While cloud computing is highly configurable and changeable, it does have some basic structures that are used in the classification of the type of cloud that is in use. The first classification of cloud computing that we're going to talk about is the public cloud. This is where systems can interact with services and devices within the public cloud and on public networks, like over the internet, and possibly with other public clouds. The public cloud is where the services that are provided are not just provided to a specific user, but are open for the public to purchase and use. Then there are private clouds. This is where systems only communicate with services and devices within a specific private cloud. A private cloud is essentially just that, private. The only users who have access to it are ones who are authorized to use it. The cloud classification can be hybrid. It can combine aspects of both the public and private clouds. And last up, there are community clouds. This is where cloud services are used by private individuals, organizations, or groups that have a common interest. Now let's move on to different types of cloud computing. Because of the nature of cloud computing, it is very configurable to the needs and desires of the purchaser of the cloud services. Purchasers have many options beyond the type of cloud services that they want to provision. They must also determine what type of service they are going to require, from the most basic of services to the most highly complex of services. The purchaser needs to have a plan going into cloud computing in order for it to be efficient and effective for them. So now let's move on to some of those services that cloud computing can offer. First up is software as a service. The end user purchases the rights to use an application or software without the need to configure the virtual servers that will deliver the application to them. It is usually delivered as a web app or web application opened and used from within a web browser, but not always. If you have a subscription to Microsoft's Office 365, you are utilizing software as a service. Then there is platform as a service, or PaaS. The user is provided with a development platform for the creation of software packages without the need to configure the virtual servers and the infrastructure that delivers it. You are essentially renting server or computing power in order to develop your software packages. PaaS is more complex than software as a service. And finally, we have infrastructure as a service. This is where the end user is provided with access to virtual servers, configurable by the customer, and other virtual network resources. Their infrastructure is actually virtually provided to them. This creates a highly configurable environment in which customers can create the resources and the performance that they require. The end user supplies the software that's going to be used on the IaaS network, or they purchase it as an additional software as a service. As you could have guessed from that last statement, it's not uncommon for the type of cloud computing being utilized by an organization to be a mix. Some departments may rely upon and use infrastructure as a service, while the development team will only utilize a platform as a service. Part of the advantage of cloud computing is that the purchaser only needs to initialize and pay for resources as they are needed. In a private cloud situation, it is possible for an organization that is using it to actually own the cloud resources. If they do own the cloud resources, they may have it on-site, or they may pay to have those resources hosted off-site. That way they can offload the maintenance cost of maintaining those resources. Now that concludes this session on basic cloud concepts. I talked about different cloud classifications, and then I concluded with a brief discussion on types of cloud computing. Good day, I'm Brian Farrell, and welcome to PACE IT's session on implementing a basic network. Today we're going to discuss plan the network and then configure the network. There's a fair amount of ground to cover, so let's go ahead and dive into this session. Of course, I'm going to begin with plan the network. So you need a simple small office, home office network? Great, just plug two PCs into a single hub and you have a very basic network. But does it achieve what you want? How do you know if you don't have a plan? A network plan is vital when implementing any network more complicated than the most very basic of networks. That plan should cover what you are hoping to achieve and how you are going to get there. In addition to your expertise, you are also going to need input from your end users. Nothing is quite so frustrating as delivering the network that you've planned and built and having the customer tell you that it is not what they wanted or needed. Let's talk about that network plan in a little bit more detail. The first thing that you should do is create a list of requirements. Now, in order to make that list, you need to define why the network is needed. That will help you to define what network features are required. Then you need to define the scope or size of the network. Once you have those, they will help to establish a budget to implement that network. Once you know why the network is needed and what features are required, then you can work on network design. In network design, you need to determine what equipment is needed to implement that network. Part of the design is also how the network will be organized and how shared resources will be placed on the network. When you're planning the network, something that you should also consider are compatibility issues. You need to know what standards are in use now and what standards will there be in the future. Included in those compatibility issues are, does any current equipment that is required need specific cabling or connectors in order to be installed? That is something that often gets overlooked. Your network plan also needs to deal with network cabling runs, your internal connections. How many node connections will be required and where? How will you plan for future expansion? That future expansion is more than likely going to require more internal connections. You should build in some tolerance for future expansion. Then you need to consider external connections. How will the network connect to the outside? Where will that WAN connection come into your building, and where will your equipment be placed so that it can reach those WAN connections? That is also part of the network equipment placement plan. Part of that plan also needs to consider if there is a wiring or equipment closet and where it's going to be located. If you do have a wiring or equipment closet, are there environmental considerations about placing the equipment in there? Is it too hot? Is it too cold? Is it too humid or is it too dry? You need to think about those things when you're placing your network equipment. Your plan should also cover how network security will be implemented. Are there specific types of firewall and placement considerations for those firewalls? Will virtual local area networks be required, and if so, how many? Also, how will your switch port security be implemented? All of these go into a successful network plan. Now let's talk about configuring the network. Here are some network configuration considerations for you. First up, how will your clients receive their Internet Protocol addresses, their IP addresses? Using static IP address configuration creates a higher level of security, but it's harder to manage. You could use Dynamic Host Configuration Protocol, DHCP, to automatically assign IP addresses from a pre-configured pool, but your security may be a little bit lower if you do so. If you do use DHCP, you might want to consider using MAC filtering. MAC filtering will only allow specified MAC addresses, that physical burned-in address, onto the network. It is an effective security measure, but kind of like static IP addressing, it can be difficult to control and manage, especially as the network grows. Something else to consider is that if a server will be hosted on the network that needs to be accessed from outside of that network, as in you're hosting a web server, then you're going to need a demilitarized zone, a DMZ. The DMZ is an area of the network in which outside connections are allowed while the internal network remains protected from that outside traffic. A DMZ will require a custom configuration of the firewall. In most implementations, 2 firewalls are used, but it's not necessary to use 2 firewalls. Talking about firewalls, firewall placement and configuration considerations are next. Most small office, home office WAN connection devices, as in their cable modems or DSL modems, include firewall services that are sufficient in most cases for those small, simple networks. But if a DMZ needs to be deployed, the best method is to introduce an additional router and firewall into the network, with the DMZ residing between the WAN equipment and the new router firewall combination. Another aspect of deploying a DMZ is that port forwarding should also be used at the router firewall level. Port forwarding is used to direct requests for specific resources, like a request for a web page, to the computer that has the resource. Let's move on to wireless network configuration considerations. The first thing to consider in a wireless network is the name of the wireless network. That's the Service Set Identifier, the SSID. Now, the SSID can be set to broadcast in the clear. Alternatively, the SSID can be set for the broadcast to be hidden. Some people consider hiding the SSID broadcast as a security measure, but it really doesn't work that way. It doesn't stop the broadcast, it only hides the broadcast. A packet sniffer can easily see those broadcasts, and those broadcast packets can be easily interpreted. So hiding the SSID is not an effective security measure, but it does make things a little bit more difficult. The next aspect of wireless network configuration that you need to consider is encryption. First off, I will say you need to have encryption on your wireless network. Not only that, but you need to turn it on. By default, wireless routers and wireless access points, WAPs, do not have encryption enabled. And at the minimum, your encryption type should be WPA2 personal. That's at the minimum. Some wireless network equipment comes with a service that is called Wi-Fi Protected Setup, WPS. And if it does, it's enabled by default. This should be turned off and not used, as it creates a weakness in the wireless network. Why is that? Well, because WPS can be easily exploited by an attacker. The network that you implement may not be exactly what you planned, so document any changes to the plan. Undoubtedly, during the process of implementing that plan, some changes will be introduced, some by you and some by request of the end user. Always document those changes to the plan and have the end user sign off on them. Then be sure to incorporate those changes into the final network documentation. Now that concludes this session on implementing a basic network. I talked about plan the network, and then I talked about configure the network. Good day, I'm Brian Farrell, and welcome to PACE IT's session on analyzing monitoring reports. Today I'm going to talk about baseline reports, and then I'm going to move on to just reports in general. I have a fair amount of ground to cover, not a whole lot of time, so let's go ahead and jump into this session. And of course, I'm going to begin by talking about baselines. How do you know what constitutes good network performance and what indicates that an issue is about to happen? This is where baseline documentation comes into play. Baseline documentation provides a snapshot of the network when it is running efficiently, at least hopefully when it's running efficiently. Baselines are usually kept as a log file. At the minimum, baselines should be established on CPU utilization and network bandwidth utilization. You may also basemark other functions as you deem them to be relevant. Network administrators should perform periodic tests against the baseline to check to see if the baseline is changed. They will change over time. And in order for network administrators to know what constitutes good performance on their network, their baselines need to be current. You can use Window Performance Monitor to help establish the baselines for your network. Let's talk about some of the items that should be considered for baseline reports. First up is network device CPU utilization. Knowing the CPU utilization on a piece of equipment can help to determine when a network device is going to fail. If your CPU utilization is constantly at 100%, you know there's a problem. That problem may be that it's going to fail, or it may be that you need to install more network devices to take care of a growing network. but you won't really know that if you're not baselining the CPU utilization. Network device memory utilization should also be baselined. It can help to determine when it is time to expand the memory of a network device. A good item for baselining is bandwidth utilization. This can help to determine the overall health of a network. It can help to determine when network segmentation should occur. It can also help to determine if a network device is about to fail, particularly if it's creating a storm of data. Baseline utilization reports can help identifying when a security breach has occurred. You might want to consider baselining your storage device utilization. This can help to determine when storage utilization has become a bottleneck on the network, where your storage device is actually causing the network to slow down because there's too much data being pushed into it. Which means that baselining your storage utilization can help determine when to increase the storage capacity of that network. You might also want to baseline your wireless channel utilization. This can help to determine how saturated the wireless channels have become. Once it's been determined that your wireless channels are saturated, a new wireless access point can be installed to alleviate the pressure, and then you need to create a new baseline for wireless channel utilization. This baseline can also help to determine if there is unauthorized wireless access occurring on your wireless network, especially if there is utilization on a channel that is not supposed to have any utilization. Now let's move on to analyzing reports. Before we talk about analyzing reports, let's talk about log file management. Log files can accumulate data quickly, and unfortunately, some administrators only review log files after a major problem has occurred. In most situations, this is a case of too much information at the wrong time. Good administrators will set the proper reporting levels with their logging software. They won't be logging all that debug information, that level 7 information, unless of course they're actively debugging a system or application. Good administrators will review log files and compare them against their baseline documentation. They do this to find issues while the issues are still minor and before they become major. Log files should also be kept and archived in case there is a need for historical data. When you do archive your log files, you should follow the organization's data storage policy. Something to consider is that you may want to create running graphs of important metrics that are captured by log files. Graphing the data gives a quick visual reference, making it easier to spot issues and trends. Many logging applications give the administrator the option of creating those graphs easily and quickly, but then again, they don't do you any good if you don't review them on a regular basis. If you're having an issue with a router or link, one of the first things that you want to do is you want to run an interface report. Now, when you're reviewing the output from the interface report, the first line is usually a report on the status of the link or that interface. If it says something like fast Ethernet is up, line protocol is up, that's all good. That means that interface is up and active and a link has been established. If it says fast Ethernet 0/0 is up, line protocol is down, guess what? All is not good. The interface is administratively set up, but it is not able to communicate with the other end of the link. And there are several different issues that may be the cause there. If that first line says fast Ethernet 0/0 is down, line protocol is up, all is not good. This down-up status indicates that there is an issue on your end of the connection. In most cases, that's going to be a cable issue or with the physical port itself. And your final status option is fast Ethernet is down, line protocol is down. If you see that, all is not good, but also all is not bad, at least not yet. The issue here is that the interface has been administratively shut down. If you want that interface up, you need to issue the command to bring that interface up and then check the status report again. If the link status of the interface indicates that there are no problems, as in it's in an up state, but something is not operating correctly, then it's time to dig a little bit deeper into that interface monitoring report. There are a lot of things that can happen on a network device's interface to cause issues. In most cases, you will be required to log into the device and run the device's report to determine the cause of any problems on that interface. One of the main culprits for creating an issue on an interface are speed and duplex settings. If there is a speed mismatch, the devices will not connect, and it's highly likely that your status will be in an up line protocol down state. If a duplex mismatch has occurred, this will cause intermittent issues. You will need to look at the errors counter in the output or input reports. You also need to look at the counter for dropped packets. If the device is discarding incoming packets, then more than likely the device's CPU is being overutilized. So you may need another device, or that device is about to fail. If the device is dropping outgoing packets, then there is a bandwidth congestion issue on that interface. If the interface resets counter keeps going up, that means that the interface keeps resetting itself. The most likely cause is a communications issue between the two endpoints that's forcing that interface to reset. Now that concludes this session on analyzing monitoring reports. I briefly talked about baseline reports, and then I moved on to other reports that you should be analyzing to take care of problems before they occur. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Network Monitoring, Part 1. Today we're going to be talking about the why of monitoring, and then we're going to talk about tools to monitor the network. There's a fair amount of ground to cover, so let's go ahead and jump into this session. I'm going to begin with the why of network monitoring. How do you know what is going on in your network? Is it healthy or is it about to crash? Network administrators really hate to be surprised by failures in their networks, especially ones that could have been foreseen and therefore kept from happening. How do they keep from being surprised? Well, they enact a plethora of procedures and tools to monitor their networks and to keep track of how those networks are behaving. They do this to reduce the surprise element. Now that we've covered the why of network monitoring, let's talk about tools that you can use to monitor the network. One of the main tools that network administrators use to monitor their networks are log files. All operating systems offer a means of viewing events that occur to that specific machine. That also includes networking equipment. There have been some applications that have been developed to monitor systems and networks that also generate log files, among other actions that they can take. Log files can be used to help pinpoint when a problem occurred and to help narrow down the possible causes of that problem. Log files can also be used to help create a baseline of network behavior so that you know what to expect from your network. Log files can usually be classified as being systems logs, general logs, or history logs. As a general rule, log files are an after-the-fact means of monitoring the network, and they're not very good at real-time analysis. That's partially due to the sheer amount of information that log files can generate. It's just too difficult to keep track of that in real time. Now let's talk about some specific logging tools that you can use. The first one that I'm going to talk about is Event Viewer. It's not really a log file in itself. It comes with Windows Server and most other Windows operating systems, and this tool can be used to review Windows log files. The most important log files that you can view from Event Viewer are application, security, and systems logs. Application logs contain events that are triggered by the actions of an application. For example, if you have Live Update enabled, it will create log entries based on actions taken by Live Update. Then there are security logs. These contain events that are triggered by security events. For example, some logs are created for successful and unsuccessful logon attempts. Then there are systems logs. These contain events triggered by Windows systems components. For example, it will create an entry for when a driver starts or fails to start. In either situation, a log entry will be created. Now let's talk about a non-Microsoft log, and that would be syslog. Syslog was developed in the 1980s, and it provides devices that normally would not be able to communicate with a means of delivering performance and problem information to systems administrators. This permits there to be separation between the software that generates the message, the storage of that message, and the software that analyzes the generated message. This separation of function allows syslog to be highly configurable and has allowed it to continue to be a vital tool for monitoring networks even today. As a matter of fact, the Internet Engineering Task Force, the IETF, liked syslog so much that they standardized it in 2009. Syslog can generate log messages based on the types of services that are running, and it includes a severity level that ranges from 0, the most severe, up through 7, the least severe. Syslog can generate a lot of log messages. Most network administrators configure it so that they only get alerted when a minimum severity level has been reached. As a matter of fact, you almost never want to capture debug log events unless you are actively debugging an application or service, just because it generates so much information. Syslog can be configured so that network administrators receive their alerts via text message or SMS message, or by email, or they may even receive a voicemail message. While syslog is a cool tool, it's not the only one that's out there. There's also Simple Network Management Protocol, SNMP. SNMP is an application layer protocol used to monitor and manage a network's health. Network or systems administrators configure monitors, these are often called traps, on devices that view the operation of a specific item. As in, is that router's interface up or is that router's interface down? The monitors periodically communicate with a network management station, or NMS, through GET messages, that's GET messages, that the NMS sends out. The response from the monitors is stored in a Management Information Base, or MIB, which is a type of log file. The administrator can custom configure the monitors with set messages sent from the network management station. When an event occurs, as in the interface goes down, the trap is tripped and the event is logged. SNMP, just like syslog, can be configured to just log the event, or it can be configured to contact the network administrator. SNMP gives network and systems administrators the ability to provide more real-time monitoring of a network's performance and health. Then there's Security Information and Event Management, SIEM. It's a term for software products and services that combine security information management, or SIM, and security event management, SEM. SIEM may be provided by a software package, a network appliance, or as a third-party cloud service. It is used as a means of monitoring and providing real-time analysis of security alerts. That is an example of the Security Event Management function, the SIEM function. It can also be used as a tool to analyze long-term data in log files. That's an example of the SIEM function, or the Security Information Management function. SIEM can be highly configured to the needs of the individual network. Now that concludes this session on Network Monitoring Part 1. I talked about the why of network monitoring, and then I briefly touched on some tools for monitoring the network. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Network Monitoring Part 2. Today we're going to be talking about active network monitoring tools, then I'm going to move on to wireless monitoring tools, and we're going to conclude with environmental monitoring. We have a fair amount of ground to cover, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about active network monitoring tools. Port scanners are used to scan a network for open ports and protocols. The information that a port scanner gathers is vital information if you want to harden the network. Port scanners are a great method of finding vulnerabilities in the network infrastructure, allowing the network administrator to plug those vulnerabilities before they become a security breach. I do have to issue a word of caution. You should only use a port scanner on a network or system that you are authorized to scan. Port scanning is a possible sign of someone trying to breach a system and can lead to problems if you're not authorized to scan that system. You don't want to have to try and explain to an information security specialist why you were scanning their network if you're not authorized to scan it. A little bit different than a port scanner are applications that use interface monitoring or packet flow monitoring. These are usually deployed as an active software tool to monitor and analyze network traffic within a network segment. They're commonly called packet sniffers or protocol analyzers. They allow for an in-depth look at what traffic is on the network and may reveal security issues that the network administrator can then mitigate. They help to identify top talkers on a network segment. Top talkers are those nodes or applications that generate the most amount of traffic. Packet sniffers can help to identify top listeners on a network segment. A top listener is that interface or the interfaces that are receiving the most network traffic, or put another way, those interfaces that are utilizing the most bandwidth for receiving packets. This can help an administrator when they have determined that load balancing might be needed on the network. Microsoft Message Analyzer and Wireshark are examples of free packet flow monitoring tools. Now let's move on to wireless monitoring tools. And we're going to begin with the Wi-Fi analyzer. A Wi-Fi analyzer is a similar tool to a protocol analyzer, but only for wireless networks. It sniffs out packets on wireless networks and gives you statistics on those packets that it sees. It can check for bandwidth usage, channel usage, top talkers, top listeners, etc., just like a packet sniffer can. Wi-Fi analyzers can also identify networks by passively scanning the radio frequencies to determine where traffic is coming from. Given enough time, a Wi-Fi analyzer can also identify hidden networks, or those that you don't know about. A Wi-Fi analyzer can also infer non-beaconing networks based on data traffic over the radio frequencies. They may not be able to discover the SSID, but they can tell the network administrator that something is passing traffic there. Another type of wireless monitoring tool are wireless survey tools. They're most commonly used as a design tool for setting up high-quality wireless networks. When used in conjunction with mapping tools, the survey tools can help to establish the required amount of access points to get the proper amount of coverage, the ideal antenna placement, and the optimum amount of channel overlap. Wireless survey tools can also help to identify possible sources of radio frequency interference, or RFI. Wireless survey tools are often used to eliminate wireless network performance and security issues before they ever have a chance to occur. Let's move on to environmental monitoring. A network's health can be affected by more than just a network interface failing or a possible security breach. Network and systems administrators also need to be concerned about environmental factors. Some of those factors include the quality and quantity of electrical power being supplied to their equipment, and the amount of heat in the rooms that equipment is kept, and also with that, the humidity level. Power monitoring tools are systems and tools that can be used to evaluate the amount of and the quality of the electrical power being delivered to the system. They're often deployed with or alongside an uninterruptible power supply, or UPS. The monitor will issue an alert when an issue with electrical power has been identified, giving the network or system administrator a chance to rectify the problem before any equipment has been damaged. All electrical components are designed to operate within a specific heat range. Not only are they designed to operate within that heat range, but all electrical equipment will generate some heat while they're in operation. And the harder that equipment works, the more heat they will generate. This is where heat monitors come into play. The heat monitor allows an administrator to control the temperature levels before they become an issue. Humidity is another item that network administrators need to keep in mind. Too little humidity increases the risk of electrostatic discharge, or ESD, but too much humidity increases the risk of condensation on equipment, and your electrical components do not like that condensation. Humidity monitors allow administrators the ability to control the humidity level through the proper means before it becomes an issue. Now that concludes this session on Network Monitoring Part 2. I talked about active network monitoring tools, then I moved on to some wireless monitoring tools, and I concluded with a brief discussion on environmental monitoring. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Supporting Configuration Management, Part 1. Today I'm going to be talking about what configuration management is, and then I'm going to discuss some documentation. With that, let's go ahead and jump into this session. First up is configuration management. Why do we need configuration management? Because even fairly small modern networks can get very complex very fast. Configuration management, or CM, is a discipline that is used to evaluate, coordinate, approve, deny, or implement change in or to an IT system. Configuration management plays a vital role in any network beyond the most simplistic of small office, home office networks. It helps to ensure that the network runs efficiently and smoothly. Network administrators and support staff will play a vital role in developing and implementing any CM system or process. Now that you know what configuration management is, let's talk about documentation. Documentation plays a key role in any configuration management system that gets developed. In the CM process, documentation is used to help evaluate and plan proposed changes. Documentation is also used to help in asset management, network maintenance, and vendor evaluations. The documentation that is created will depend upon the complexity of the systems under consideration. However, even if your organization doesn't implement a true CM style, some documentation should still be kept to reduce the burden on network personnel and to ease administrative management of the network. Some of the documentation that should be kept include policies and procedures. Policies are a set of guidelines that establish how the network is to be configured and operated. They also set the expected behavior of the people within the organization. As a general rule, policies are put into effect at the mid to upper management level. Procedures, on the other hand, are a set of documents that detail how the policies are to be implemented. As a general rule, procedures are set by the management of the level that's affected by the policy, and they get down to the step-by-step process of how to do things. Asset management documentation should also be maintained. This covers a broad category of documentation that's often used to help in the change management process. Asset management documentation contains detailed information on what assets are present. It also includes the maintenance history for those assets. This documentation is often used to help track update and upgrade cycles. Physical network diagrams should also be kept. These are a map or diagram of all network devices and how they connect. A physical network diagram specifies the cabling, connectors, and physical cabling runs. It will also include cable management documentation, which is considered a subcategory of the physical network diagram. The cabling management documentation will contain a wiring scheme, which establishes the type of cabling and the connectors used. It also defines the allowed standards for wiring those cables. Your documentation should also include a logical network diagram. It's similar to a physical network diagram, but more detailed. It provides details on the IP address scheme, active ports, protocols that are allowed on the network, etc., etc. Your logical network diagram also details connected networks. So what local area networks are present, or which virtual local area networks are present, so on and so forth. Part of your logical network diagram also details IP address utilization. IP address utilization can greatly affect the efficiency and performance of the network by allowing you to know which LANs or VLANs have space on which nodes can be added. Your physical and logical network diagrams may be combined into a single document. Vendor documentation also plays a role in supporting configuration management. It covers a broad category of documentation that can include the approved vendor list, the vendor approval process, and purchase order documentation. There are some common vendor documents that you should know. First up is the Memorandum of Understanding, or MOU. This is an agreement between two or more organizations that detail how those organizations are to take some common course of action. It is also often referred to as a letter of intent. It is not legally binding, but it does often lead towards a binding agreement. Then there is the Statement of Work, or the SOW, the SOW. It's a detailed document that specifies what work is to be performed, the expected outcome or deliverables, and the timelines to perform the work. The Statement of Work is often a key document in project management. Included in some vendor documentation is a Master License Agreement, or MLA. This is a legal agreement between two entities in which one agrees to pay the other for the use of a specific piece of software or software package for a specific period of time. Often, instead of being called a Master License Agreement, it is referred to as just a license agreement. Last up is the Service Level Agreement, or SLA. It details the allowable amount of response time the vendor has to resolve an issue or problem. Most commonly, it is associated with a service contract. That concludes this session on Supporting Configuration Management Part 1. I talked about configuration management, and then I moved on to documentation. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Supporting Configuration Management Part 2. Today I'm going to be talking about backups, and then we will conclude with a brief discussion on Bring Your Own Device. And with that, let's go ahead and begin this session. I will begin by talking about backups. Backups are an essential part of any configuration management system. That's because small changes in a network device's configuration can introduce unexpected consequences into that network. In addition, there is always the possibility of a failure of a key component, which can lead to the loss of data or functionality. Backups play a key role in recovering from unexpected consequences or from the failure of a key component. Backup schedules must be implemented, and periodic tests should be conducted to ensure that the backup process is working. There's nothing worse than installing a backup and finding out that you really backed up nothing. There are three basic types of backups. There is the full backup. All data on the targeted system is backed up. This is the slowest backup method with the highest storage requirements, but it does lead to the fastest recovery method. When recovering using a full backup, it only requires the last full backup file. Then there's the incremental backup. With this type, only new or modified files are backed up. This is the fastest backup method with the lowest storage requirements, but it also leads to the slowest recovery method. The recovery process with incremental backups requires the last full backup file and all of the incremental backup files. The middle ground is the differential backup. Only data that is changed since the last full backup is saved. The time to back up is moderate, and it requires a moderate amount of storage, but it also is the middle ground on the length of time for recovery. The recovery process requires the last full backup file and the last differential backup file. Something else that needs to be backed up are your configuration files of network devices. Once a network device has been configured and it's operating as expected, a backup of the configuration files and operating system should be done. This helps to speed up the recovery time in cases of equipment failure or when a change to the configuration has introduced unexpected consequences. Having the configuration file backups on hand means that you don't need to manually input it to recover in these situations. Now let's move on to bring your own device. BYOD policies, or bring your own device policies, allow employees to use their own personal devices on an organization's network. While the employees are happy that they get to use their favorite IT devices on the corporate network, IT departments aren't quite as happy about it. Why? IT departments are tasked with keeping a network safe, yet they have very little control over the devices that employees bring in. In some cases, bring your own device policies have led to the introduction of malware into an organization's network environment. This makes them very unhappy. They can implement network admission control measures, or NAC measures, in an effort to reduce the risk associated with BYOD policies and to introduce configuration management to those devices. Network admission control is a Cisco process. Microsoft uses a similar process, but it's called Network Access Protection, or NAP. While their names may be different, they still function in the same way. NAC includes more than just authenticating users and devices on the network. All of the devices that are requesting access to network resources are screened for the type of device that it is, the operating system that's used, including any updates that are present. NAC will also check for security software, making sure that it's up to date. NAC can also check for the presence of malware or other security vulnerabilities. In an advanced setup, if the device requesting the connection has been rejected, the device is then redirected to a remediation server which attempts to resolve the known issues. So if the security software is out of date, the remediation server may try and bring it up to date and then allow that device to connect to the corporate network. That concludes this session on Supporting Configuration Management Part 2. I talked about backups, and we concluded with a brief discussion on Bring Your Own Device. Good day, I'm Brian Farrell, and welcome to PACE IT's session on the importance of network segmentation. Today we're going to discuss the OSI model and segmentation, and then we're going to conclude with reasons for segmentation. And with that, let's go ahead and begin this session. We will begin by talking about the OSI model and segmentation. So what is segmentation? Well, it's taking a single network or system and breaking it into smaller discrete units. This can be achieved physically or logically. There are many reasons why you might want to segment a network. Some of them could include to ease administrative tasks, to achieve performance gains, to increase security, or to comply with regulations. As I mentioned earlier, segmenting a network can be achieved physically or logically. And either way, it involves different levels of the OSI reference model. It can be achieved at layer 1, the physical layer. This is taking a single network and making it into more than one network through the use of cable runs and equipment. This is the most extreme example of network segmentation. Not only is this the most extreme example of segmentation, but it's also an example of physically segmenting a network. You can also segment a network logically at the data link layer, which is layer 2, or at the network layer, which is layer 3 of the OSI model. This is taking a single network and making it into more than one by logically dividing the network. The logical segmentation of a network takes the least amount of physical resources to achieve it. Now let's move on to reasons for segmentation. First up is compliance. Some rules and regulations require that certain data be kept separate and secure, as in the Payment Card Industry Data Security Standard, or PCI DSS. This requires that you keep customer information separate and secure from normal business information. Segmentation allows for the regulated data to flow across its own network, keeping it more secure. Another reason for segmentation would be for network performance optimization. As a network increases in size, the amount of data that flows through them usually increases. This can slow down the performance of the network. Segmentation breaks the larger network into smaller units, which can lead to an increase in performance on those segments. Related to network performance optimization is the creating of high-performance networks. Some applications require more bandwidth in order to perform at the desired higher level. Voice over IP, video teleconferencing, and media nets, which are all examples of streaming services, all perform better when they are on their own network segments. A major reason for network segmentation is to separate private from public networks. Organizations often allow the public to access the internet from their locations. These are places that offer free Wi-Fi. Segmentation allows this traffic to be kept separate from the private corporate traffic. Then there are legacy systems. Some organizations use systems that are considered critical to their operation but are not capable of residing on modern networks. Segmentation allows the legacy system to reside on its own subnet and network without compromising its performance or the performance of the rest of the network. Then there are testing labs. The lab can be used to test new applications, operating systems, update patches, so on and so forth. If these tests occur on the main network, it is possible that this testing could inject a problem into the main system. Segmentation allows for the testing to occur in a secure, easily controllable environment. And finally, there's security. One of the main reasons for performing network segmentation is for security purposes. Segmentation allows network and systems administrators to more easily control the flow of data between systems. Segmentation also allows network and systems administrators to more easily control access to network resources, therefore creating more security. An example of segmentation for security would be honey-nets. These are network segments that are created with the sole purpose of attracting any network attacks through the use of multiple honeypots. Honeypots are systems that are configured to be attractive to network attackers, helping to draw attackers away from the main network systems and into the honeynet. The network segment of honeypots allows the main network to remain secure and gives network administrators an opportunity to study an attack, including the methods of entry, so that countermeasures can be developed to prevent future breaches. A system that should be segmented are SCADA systems, or Supervisory Control and Data Acquisition Systems. These are the most widespread of industrial control systems, or ICS. The industrial control system uses coded signals over communication channels to provide control of remote equipment. They're commonly used in industrial applications to monitor and control systems. Utilities often use SCADA systems to control their operations through the use of DCS networks. That is a distributed control system network. The DCS allows for the control of multiple SCADA systems from a single location. The Stuxnet virus was originally designed to attack SCADA systems and can spread through the DCS, leading to more damage from the virus. Segmentation of the distributed control system can limit the amount of damage caused by such a virus attack on industrial processes. Now that concludes this session on the importance of network segmentation. We talked about the OSI model and segmentation, and then I concluded with reasons for network segmentation. Good day, I'm Brian Farrell, and welcome to PACE IT's session on applying patches and updates. Today we're going to discuss patches and updates, and then we're going to conclude by talking about upgrading versus downgrading. There's a fair amount of ground to cover, so let's go ahead and begin this session. And of course, we're going to begin by talking about patches and updates. Today's modern operating systems are very complex and are composed of tens of millions of lines of code. Even your network devices and appliances are very complex and have complex software packages and configurations. This complexity of the modern operating system has led to the necessity for updates, patches, and hotfixes. These are used to add features, fix bugs, and repair security holes as they become known. One goal of administrators is to keep systems as up-to-date as possible through the use of these updates, patches, and hotfixes, reducing the system's vulnerability and increasing its functionality while reducing maintenance costs. A patch is a small section of code that is used to either increase functionality or fix a problem within a software package. A patch will change the version of the software package in a minor manner, as in version 1.0.0 will become version 1.0.1. An update is a larger section of code that is used to either increase functionality or fix problems within a software package that become known after production. An update will change the version of the software in a more major manner, as in version 1.0.0 will become version 2.0.0. Or, using a Microsoft example, Windows 8.0 became Windows 8.1. A hotfix, which can also be called a vulnerability patch, is similar to a patch, but it is actually smaller than a patch. They are designed to be deployed to fix a very specific issue within an operating system or other software package. Hotfixes are usually issued to fix security problems that become discovered after the software package has been produced. A service pack is a cumulative Windows update package that contains all patches, updates, and hotfixes between 2 points of time. Microsoft releases service packs as a method of easing the installation of an operating system, helping to keep it current. You install the operating system and then you install the service pack. That way you don't have to download and install every patch, update, and hotfix. In most cases, it is possible to automate the patch and update process through registering the product with the vendor who created it. Microsoft's operating systems can be set to automatically check for updates and it will download and install them if you configure it that way. Most hardware vendors offer the same type of service for firmware and drivers. In most cases, these services can also be set to just inform the system of the availability of patches and updates, allowing administrators to manually download and install them. In a production setting, all patches and updates should be installed and tested in isolation, as in on a test system in a testing lab, before they are installed on vital production equipment. This reduces the chances that a patch or update will bring down a system that is functioning all right but is in need of the patch or update. Now let's discuss upgrading versus downgrading. Quite often it is highly desirable to install the latest patches and updates in order to keep systems running efficiently. However, sometimes issues arise with the installation of a patch or update, leading to problems that were not caught during the testing phase. This is where backups and downgrading come into play. Backup copies of all systems and configuration files should be maintained in order to downgrade or roll back to the previous version for when a problem occurs during the deployment of a patch or upgrade. Being able to roll back to a prior version is often easier and more efficient than trying to resolve a problem that was introduced with an update. Administrators should keep backup copies that include the base package of the operating system or software package, a backup of the system before the patch was installed, and a backup of the system after the patch was installed. All of these backups should be kept and maintained as per your organization's policy. Now that concludes this session on applying patches and updates. We started by discussing patches and updates and then concluded with a brief discussion on upgrading versus downgrading. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Configuring Switches Part 1. Today we're going to talk about unmanaged versus managed switches, and then we're going to talk about spanning tree protocol. There is a whole lot of information to cover, not a lot of time, so let's jump into this session. I'm going to begin by talking about unmanaged switches and managed switches. Before we begin discussing the differences between unmanaged and managed switches, let's talk switch basics. Most switches operate at layer 2, the data link layer, of the OSI reference model. What makes a switch is an application-specific integrated circuit chip, or an ASIC chip. It is used to make switching decisions in place of software. This allows switches to break up collision domains. This allows switches to run in full duplex mode, and this allows switches to make faster decisions than either bridges or routers. When a switch receives a frame on a port, it makes some simple decisions based on its media access control table, or its MAC table. It will make one of three decisions. It may decide to forward the frame. That is where the frame is directed out the port on which the destination MAC address resides. It may decide to filter the packet. That is where the frame is not directed out of ports which are not associated with the destination MAC address. The final decision that it may make is to flood the frame. The frame is flooded or sent out all of the ports on the switch except for the port on which it came in on. An unmanaged switch is a simple switch. Plug it in and it works. There is no method provided for configuration. The unmanaged switch is designed with ease of installation as its main attribute. Managed switches, on the other hand, can be configured through either the command line or a browser-based interface. Managed switches provide for a high degree of network customization and control. A managed switch can also be set up so that an administrator can monitor its performance remotely and use protocols such as SNMP to make some modifications to its configuration. Now let's move on to spanning tree protocol. Spanning tree protocol is a loop avoidance technology. A switching loop can occur on networks where there are multiple paths to reach destination MAC addresses. Digital Equipment Corporation created the Spanning Tree Protocol, or STP, to reduce the possibility of switching loops. The switches elect a root bridge to control the switched network. The switches will shut down ports that are not the best path to the root bridge, thus reducing the risk of loops. No network traffic can flow until after the STP process has taken place and a stable state has been achieved. This stable state is called convergence, and it can take a significant amount of time with STP, up to 50 seconds. After convergence, the STP selected switch ports send out Bridge Protocol Data Unit packets, or BPDU packets, to help maintain the stable state. All switch ports in an STP-enabled network can be in one of 5 states. First off, there is the disabled state. That is where the port is administratively shut down. It's not receiving packets, it's not sending packets, it's just completely disabled. Then there's the blocking state. In this state, the port will not forward packets, but it's still receiving BPDU packets and will drop all other frames. Then there's the listening state. In this state, the port will not forward packets, but listens to BPDU packets to make sure that no loops can occur in preparation for the next state. Then there's the learning state. In this state, the port will not forward packets, but it is learning all of the paths in the network. It is populating its MAC address table in preparation for the next state. The last state in Spanning Tree Protocol is the forwarding state. In this state, the port will forward and receive all packets that are flowing across the network that are directed to that port. The IEEE liked STP so much that it created the 802.1d standard. This is their version of STP. All modern Layer 2 switches run the 802.1d standard by default. The slow convergence time of the 802.1d standard led to the creation of Rapid Spanning Tree Protocol, or RSTP, which is also known as the IEEE 802.1w standard. RSTP has a much faster convergence time than 802.1d. With RSTP enabled on all switches, a network can achieve its stable state in approximately 5 seconds. That's a whole lot faster than the up to 50 seconds with the 802.1d standard. But RSTP is not turned on by default on Layer 2 switches. It must be enabled by an administrator. Instead of 5 possible port states, RSTP defines 3 possible port states. The first of these states is discarding. In this state, the port may be administratively disabled, or it may be in a blocking mode or listening mode. The next state is learning. In this state, the port is populating its MAC address table in preparation for forwarding packets. And the final state is forwarding. In this state, the port is actively forwarding packets. Now that concludes this session on Configuring Switches Part 1. I talked about unmanaged versus managed switches, and then I had a brief discussion on Spanning Tree Protocol. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Configuring Switches Part 2. Today we're going to discuss installation considerations, and then we're going to move on to configuring the switch port. There's a fair amount of ground to cover, so let's go ahead and dive into today's session. Of course, I'm going to begin with installation considerations. The first installation consideration is whether or not you need a managed or unmanaged switch. The business or enterprise network is more complex than the small office, home office network. A SOHO network may be able to get by with using one or more unmanaged switches and still operate adequately. But once beyond the level of a SOHO, More thought and planning is required as unmanaged switches are no longer up to the job. You are going to need managed switches. There are multiple issues to consider when installing a managed switch, and it is wise to plan for those in advance to save both time and frustration in setting up a network. One of the first things to consider is if there will be VLANs, virtual local area networks. While switches may break up collision domains, they do not break up broadcast domains, but VLANs will. A virtual local area network takes a single network environment and creates smaller network segments by subnetting the network address range, effectively breaking up the broadcast domains of that network. VLANs are used in a switched network environment for a variety of reasons. To break up broadcast domains into smaller segments, just like I just said. Another reason to use VLANs is they increase security by limiting access to network resources. The administrator configures the VLANs and then assigns users, nodes, or ports to a specific virtual local area network. All managed switches do come with a native VLAN, which is determined by the manufacturer. This native VLAN is used to help manage the switch. VLAN traffic is allowed to cross switch ports as long as the VLAN information matches. So VLAN 2 can send traffic to VLAN 2, but VLAN 2 cannot send traffic to VLAN 3. VLAN traffic is allowed to cross switch ports as long as the VLAN information matches. It does this through the use of trunk ports. That means that VLAN 2 can send traffic across a trunk port to VLAN 2, but it cannot send traffic from VLAN 2 across a trunk port to VLAN 3. VTP, or Virtual Trunk Port Protocol, is a Cisco proprietary method of creating a virtual trunk port, which allows VLAN traffic to pass between switches and to automatically manage the VLAN environment. In order for different VLANs to communicate with each other, a router or some other layer 3 device must be installed on the network. The next consideration is how is the switch going to be managed? Switches may be managed out of band. That means that no network connection is required. This is achieved through the use of the console port on the switch. The console port is a specific port on managed switches used to connect to and configure or manage a switch. A rollover cable may be required to make the connection to the console port. Security should also be set on console ports to prevent unauthorized access through that console port. Your other option for switch management may be to use in-band management. With in-band management, a network connection is used to manage the switch. One of the most common methods of allowed in-band management is through the use of virtual terminals or VTY connections. The most common VTY connections are Telnet or Secure Shell Sessions, SSH sessions. Security should also be set if Telnet is allowed on VTY type connections. By default, SSH is a secured connection. If you determine that you're going to use in-band management, the next thing that you need to do is to establish a default gateway address. That default gateway address must be placed on an interface that belongs to the native VLAN, or the default virtual local area network. The default gateway on a switch is different than the default gateway on a router. On a switch, it is only used to manage the switch and not to pass other network traffic. As part of the setup and management of the switch, an administrator should configure which users and passwords are allowed to connect to the switch and what their level of access to the configuration is going to be. In-band and out-of-band management security settings may be different. Some users may be allowed in-band management access while others are not, and vice versa. If authentication, authorization, and accounting protocols are used in the network, the switch must be configured to use them as well. With that done, let's move on to configuring the switch port. I'm not going to actually show you the commands for how to configure the switch port, but I'm going to give you the information that you need to consider when configuring the switch port. First up is speed and duplexing. Most modern switch ports can auto-negotiate both the speed of the link and the duplexing mode used. But in some cases, an administrator may be required to manually set both the speed and the duplex in order for a connection to occur. Speed and duplexing errors are the most common cause for a link not being established between a switch and a router or between switches. Next up is VLAN assignment. All switch ports will belong to a VLAN, and that VLAN will either be an administrator configured one or it will be the native virtual local area network. As a side note, the native VLAN can be administratively changed, which should be done to increase the security level on the switch. Then there's trunking. Trunk ports are switch ports that are designed to carry VLAN traffic between switches. The standard protocol used is 802.1q. 802.1q strips off the VLAN tag. Actually, it changes that tag to match the native VLAN, which allows the traffic to cross over the port, and then once on the other side, then the 802.1q port on the other side reinserts the original VLAN tag. And that is trunking in a nutshell. You might want to consider port bonding using LACP. That's Link Aggregation Control Protocol. It is a protocol that is used to create a single logical channel from redundant connections between switches. So it bonds those ports together. This will increase the bandwidth between the switches. Now we're going to talk about PoE. Not Edgar Allan Poe, but Power over Ethernet. Some switches come equipped with Power over Ethernet ports, or PoE ports. These ports can use one of two methods to provide current over the network cable, as well as carrying data, allowing these ports to power small network devices while at the same time communicating with them. The port itself may provide the current, or the port may allow the use of a power injector to provide the power instead of the port itself. There are multiple PoE standards in place. The two most common are actually the PoE standard, the 802.3AF, which can provide up to 15.4 watts of current, or the PoE Plus, which is 802.3AT, which can provide up to 30 watts of current. Port mirroring may also be enabled on a switch port. This allows the configured port to receive all network traffic going to and from a specific port. By using port mirroring, an administrator can examine and analyze the traffic going into and coming from a specific host or port. Port mirroring is most often used in conjunction with a packet analyzer, also known as a packet sniffer or network sniffer. Administrators often use port mirroring to examine the flow of traffic to determine what method of network optimization to use, or for when they're determining which security measures to put in place. Port mirroring can create a significant amount of network overhead, so it should be used sparingly on an active network, and you may want to shut it down once your research has concluded. That concludes this session on configuring switches part 2. I talked about installation considerations, and then I talked about configuring the switch port itself. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Wireless LAN Infrastructure Part 1. Today I'm going to give an introduction to wireless network standards, then I'm going to move on to antenna technology, and we will conclude with wireless access points. There is a whole plethora of information to impart, not a lot of time, so let's go ahead and begin this session. I'm going to begin by giving an introduction to wireless network standards. To talk about the standards, I need to introduce you to the IEEE 802.11 specifications. These are a set of specifications that deal with the data link layer and the physical layer of the OSI reference model. These establish how wireless network communication can occur. The 802.11 standard specifies the use of unlicensed radio frequency bands as the carrier for network traffic. It also specifies that network communication will be half duplex in nature, and that it will be implemented using carrier sense multiple access with collision avoidance, or CSMA-CA. Carrier sense multiple access with collision avoidance technology requires that devices only transmit data when no other data transmission signal is present on the carrier wave. Now, the 802.11 standards have been amended over time to become our common standards that we see today. These standards include the 802.11b wireless standard. It was commercially released in 1997 and operates within the 2.4 gigahertz Industrial, Scientific, and Medical, or ISM, radio frequency band. Now, within the 2.4 gigahertz RF band, it uses multiple channels that are 22 megahertz wide. There are 11 separate channels, of which only 3 do not overlap. 802.11b has a theoretical throughput of 11 megabits per second, and it is compatible with the 802.11g and N standards. Then there's 802.11a. It was also commercially released in 1997 and operates within the 5 gigahertz unlicensed National Information Infrastructure, or U-NII, radio frequency band. It offers up to 23 separate channels that offer a bandwidth of 20 megahertz each. None of the channels overlap. 802.11a has a theoretical throughput of 54 megabits per second. It is not compatible with any other standard. 802.11g was commercially released in 2003 and operates within the 2.4 gigahertz radio frequency band, just like 802.11b. It also offers a bandwidth of 20 megahertz on 11 separate channels. It has a theoretical throughput of 54 megabits per second, and it's also compatible with 802.11b. It's also compatible with 802.11n and 802.11ac. And that brings us to 802.11n. It was commercially released in 2009 and can operate on both the 2.4 gigahertz and 5 gigahertz radio frequency bands at the same time. It uses a 20 megahertz wide channel within the 2.4 gigahertz band and a 40 megahertz wide channel within the 5 gigahertz band. It has a theoretical throughput of 600 megabits per second through the introduction of multiple input and multiple output MIMO technology and beamforming. And it is compatible with .11b, .11g, and .11ac. And that brings us to 802.11ac. It was commercially released in 2013 and operates on the 5 gigahertz radio frequency band. The available bandwidth varies by administrative settings and can be dynamically changed by the wireless access point based on how much radio frequency interference, or RFI, is present and how many users are on the wireless network. 802.11ac has a theoretical throughput of over 1 gigabit per second through the introduction of multi-user, multiple input and multiple output technology, or MU-MIMO technology, and beamforming. 802.11ac is only compatible with 802.11g and N. So why broadcast a wide signal to a specific device when it's possible to target that device specifically? This is the question that beamforming answered. Once a device makes a connection to an access point that is capable of beamforming, the AP will auto-tune its antenna and transmitter to more specifically target the device when communication occurs. This can reduce RFI and increase throughput on the wireless local area network. While 802.11n allowed for beamforming, it was not a standardized option until the implementation of 802.11ac. Since we've covered the standards, let's move on to antenna technology. First up, the basics. Antennas are used to broadcast and receive radio frequency signals, and they fall into two basic categories. There are omnidirectional antennas, which are designed to broadcast and receive signals in all directions. Then there are unidirectional antennas, which are designed to broadcast and receive signals in a specific direction. Antenna placement and type of antenna will have an impact on wireless local area network performance. Both MIMO and MU-MIMO are technologies that allow for more than one spatial stream to be transmitted and received by a single device through the use of multiple antennas. MIMO allows for up to 4 spatial channels, while MU-MIMO allows for up to 8 spatial channels. MU-MIMO also allows for a single signal to be spread across multiple transmitters. This accounts for the multiple user part of the name. Let's conclude with a discussion on wireless access points. The wireless access point is a foundational piece of the wireless local area network. The wireless access point, or WAP, can also be known as an access point, or AP, and it creates a point of entry for wireless to enter the more traditional wired networking environment. The AP can also be used to join other types of networks. Wireless access points in most cases use unlicensed radio frequency bands in order to communicate with devices. One or more antennas are used in order to radiate and receive radio frequency signals in a half-duplex manner. Wireless routers are common in the small office, home office environment. They are wireless access points that have routers built into them, reducing the need for networking components. A wireless bridge is an access point that can bridge wired network segments together in certain situations. Access point performance is impacted by the number of wireless devices that are attempting to access the network. This can be mitigated by adding additional access points to the network. Strategically adding WAPs to the wireless local area network can allow users to migrate from one wireless signal to the next. This is called roaming. So let's talk about roaming a little bit more. When implementing multiple access points, you might find that you also need to implement wireless controllers. They're commonly found in wireless networks of medium-sized and larger businesses. They're used to control wireless local area networks that have multiple access points that all function as part of a larger wireless network through the use of special protocols that can increase the usability of the wireless local area network. One of those special protocols is Lightweight Access Point Protocol, or LWAPP, which is a Cisco proprietary protocol that is used by Cisco wireless controllers. Dynamic or static VLAN pooling can be established with a wireless controller. This is taking the wireless local area network signal and creating and controlling virtual local area networks to allow more devices to connect to a single access point. Wireless controllers are often used to create a wireless network mesh that seamlessly spans more area than is normally possible with wireless access points. The mobile devices are seamlessly handed off from one access point to another when they reach the edge of a signal. Now that concludes this session on Wireless LAN Infrastructure Part 1. I did an introduction to wireless network standards. I moved on to antenna technology, and I concluded with wireless access points. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Wireless LAN Infrastructure Part 2. Today I'm going to be talking about basic wireless LAN topologies, and then we're going to conclude with wireless LAN concepts and terms. There's a fair amount of ground to cover, so let's go ahead and jump into this session. Of course, I'm going to begin by talking about wireless local area network topologies. And the first topology is the ad hoc topology. It's a very basic wireless local area network that does not require the use of a wireless access point, which can also be called a WAP, and it can also be called an access point. The devices negotiate the wireless connection between themselves. An example of this are when laptops connect wirelessly without the use of a wireless access point. Then there's the infrastructure topology. It's a more common type of wireless local area network that uses a WAP or multiple WAPs to create a connection point for wireless devices. Most often, it's used to connect a wireless network to a more traditional wired network, but that wired network is not absolutely required. Then there's the mesh topology. This is a type of infrastructure topology that employs the use of multiple access points to create larger seamless network coverage areas. They're commonly deployed with wireless controllers and wireless access points. Something to remember is that the higher the wireless device density, the more wireless access points that will be required to handle the load. Like any other network device, access points only have a certain amount of capacity. As the workload increases, the amount of throughput will decrease as each device contends for access to that wireless access point. Adding more WAPs and/or adding more access points and wireless controllers can greatly ease the load and increase the efficiency of the network. Now let's move on to wireless LAN concepts and terms. First up is the IBSS, or Independent Basic Service Set. An IBSS is created when an ad hoc network topology is created. The devices use the IBSS in order to control the communication that occurs between the connected devices. Then there's the BSS, or Basic Service Set. When a single wireless access point is in infrastructure mode, it will create a BSS. This means that it can control the flow of communication between every device that connects to the SSIDs under its control. Then there's the ESS, or Extended Service Set. An ESS is created when two or more access points share a common SSID and have overlapping coverage. Through the Extended Service Set, the WAPs will negotiate how to hand off a wireless device between them as it roams the network. So I mentioned the service set identifier just a moment ago, or the SSID. It plays a key role in the wireless local area network environment. All active wireless access points will use a beacon transmission to advertise the networks that they belong to. What they advertise is their SSID, which can also be thought of as their network name. Those beacons are how devices know which networks they can connect to. Even when an access point is set to hide the beacon, the broadcasts are still occurring. So although hiding the SSID broadcast may make it more difficult to join a wireless network, it's not a true security measure because the broadcast is still occurring. Now let's talk about 802.11a-HT and 802.11g-HT. Both of these terms relate to the 802.11n standard. They denote the type of connection, a high throughput connection, and the radio frequency, which will either be the 2.4 gigahertz radio frequency band or it may be a 5 gigahertz connection. Then there's good put. Good put is the actual amount of application data passed through a connection with the overhead removed. It's measured in bytes per second. It is different than throughput. Throughput measures the total amount of data capable of being passed through a connection, so it includes network overhead. Then we have signal strength. It's a measure of the strength of the radio frequency signal that comes from an access point, which can help to determine the amount of area that can be covered by that access point. As a general rule, the closer a device is to the wireless access point, the stronger the signal that is received. This strength of signal can be affected by wireless access point or antenna placement, the type of antenna used, and interference sources that may be present. A wireless site survey with heat mapping tools can help in the setup of a high-quality wireless local area network, or it can help you to pinpoint problem areas within your network. The heat mapping software builds a visual map by measuring the received signal strength indicator, or RSSI, and the signal-to-noise ratio, or SNR, which can be directly correlated to data throughput. Using these tools allows the administrator to find gaps in coverage as well as areas where the coverage extends beyond the desired boundaries, helping to create a more efficient and secure network. Now that concludes this session on Wireless LAN Infrastructure Part 2. I talked about basic wireless LAN topologies, and we concluded with some wireless LAN concepts and terms. Good day, I'm Brian Farrell, and welcome to PACE IT's session on risk and security related concepts. Today I'm going to be talking about the big picture of recovery, and then we're going to move on to some concepts and terms that you should know. There's a fair amount of ground to cover, not a whole lot of time, so let's go ahead and jump into this session. We begin with the big picture of recovery. Standards and policies are used to help ensure that everyone is on the same page at the same time. All organizations should review their operations and create standards and policies that suit their needs. Once they are created, the standards and policies should be adhered to. This includes all of the information technology systems. By stressing the importance of standards and policies, risks to an organization can be reduced and security can be strengthened. All policies and standards should be reviewed on a periodic basis to help ensure that they remain relevant and be updated as necessary. One of the standards or policies that should be created is the Disaster Recovery Plan. A disaster is any event or emergency that goes beyond the normal response resources, as in an earthquake or a flood or a major fire. The longer a business is not able to function, the more damage is done. The Damage Recovery Plan, or DRP, detail the steps to recover from a disaster situation, as in when the off-site backups need to be used or if a fallback site needs to be brought into operation. They also have sections dealing with how to help ensure employee safety. A sub-element of the DRP is the Business Continuity Plan, or BCP. A BCP includes an impact analysis of the business effects of down systems. The impact analysis helps to identify single points of failure in the business system. A BCP helps to prioritize what systems or processes need to be brought back first to get an organization operational again. It identifies mission-critical systems, processes, and data. The Business Continuity Plan helps to guide the creation of the Disaster Recovery Plan. Now let's talk about some concepts and terms that you should know. First up is single point of failure. A single point of failure is a system or component that if it goes down has a major impact on operations. An example of a single point of failure is if a key router goes down and it prevents customers from ordering products, that's a single point of failure. Once identified, these failure points can be mitigated through several different methods, such as redundant systems, as in adding a backup router to the previous example, or maybe a redundant power supply. Single points of failure can also be mitigated through system redesign, as in removing that point of failure through a redesign of the system. You should also be familiar with uninterruptible power supplies, or the UPS. A UPS will mitigate power issues that can have a negative impact on sensitive networking components. It conditions the incoming power to remove spikes and sags in the current, helping to ensure that the flow of current is even and consistent, which is very beneficial to your electronic and networking components. They also help to ensure the continued operation, at least for a given period of time, in the case of complete electrical power supply loss, as in an outage. Depending upon your UPS, you may be able to run for minutes, hours, or possibly days if you have a generator. First responders are the first people to discover or respond to a security issue. Ideally, it will be someone who has been properly trained in how to deal with the situation. Within the network security realm, first responders can play a key role in mitigating damage and collecting evidence. Then there's the concept of a data breach, which is any unauthorized access to data, particularly to sensitive data. Breaches may be unintentional or intentional. They may also occur from inside the network, so internally, or they may originate from an external source, so they may come from outside of your network. The severity of the breach is greatly determined by the sensitivity and the quantity of the data that's been accessed. Data breaches can be very expensive to organizations. They can result in a loss of reputation, which can lead to a loss of revenue. When it became known that Target lost sensitive customer information, credit card information, people became unwilling or uncomfortable with shopping at Target. Even though they quickly fixed the breach, the results lingered on. A data breach may result in a loss of business secrets, which may cost that organization a competitive advantage. And finally, data breaches may result in fines or penalties levied by governments or other organizations. User awareness and training can greatly reduce your security risks. Quite often, the weakest link in the security chain is the end user. The risks can be reduced by making the users properly aware of security and security threats through awareness training and just security training in general. This training should be conducted on an ongoing basis. It's never a one and done thing. Penetration testing is the finding of weak spots and the hardening of systems. It is actively and aggressively testing the whole IT system in an effort to find weak spots. This can include using social engineering methods on your end users to find out if they are your weak link. The data generated is used to harden the IT system in an effort to mitigate future risks. Similar to penetration testing is vulnerability scanning. This is the finding of network holes and then plugging them. It's mostly done through the use of automated software. Networks are probed for vulnerabilities, as in open ports or unnecessary protocols. Once these ports or protocols have been identified, these holes into the network can then be plugged. But remember, you need to have authorization to perform vulnerability scanning, or you may be having an uncomfortable discussion with your security personnel. Now that concludes this session on risk and security related concepts. I talked about the big picture of recovery, and then I covered some concepts and terms that you should know. Hello, I'm Brian Farrell, and welcome to PACE IT's session on common network vulnerabilities. Today we're going to be discussing vulnerabilities associated with unsecure protocols, and we're going to conclude with vulnerable network practices. There's a fair amount of ground to cover, so let's jump into this session. I will begin by discussing vulnerabilities associated with unsecure protocols. Network security is never a completely done deal. It often seems as if as soon as one hole is plugged, another one opens up. Vulnerabilities are discovered all the time, making it difficult for network administrators to keep up. While this is true, there are still some steps that administrators should take to reduce the vulnerabilities that exist in the systems under their control. By reducing known vulnerabilities, administrators can then spend their time preparing for and reducing exposure to up-and-coming threats, thus increasing their productivity. The first vulnerable protocol that we're going to discuss is Telnet. Telnet is a protocol that is used to create a virtual terminal connection that is commonly used for troubleshooting. Telnet is very unsecure because all communication occurs in clear text. Telnet does not support encryption. Whenever possible, Secure Shell or SSH should be used to create those virtual terminal connections in place of Telnet. Then there is SNMP, Simple Network Management Protocol, versions 1 and 2. SNMP is a protocol that is used to remotely manage and configure network devices. Due to their lack of encryption support, versions 1 and 2 are unsecure and susceptible to packet sniffers. This can allow an attacker to grab those packets and actually gain control of the configuration and management of your network devices. If you're going to use SNMP, version 3 should always be used as it supports more security, including encryption. FTP, or File Transfer Protocol, is a protocol that is used to transfer files across a network connection. While a username and password are required in most cases to use FTP, it doesn't support encryption, which creates a vulnerability in the process. Because of this lack of encryption support, everything is done in the clear, making it susceptible to being captured, and you could lose sensitive information. Secure FTP, or SFTP, should be used in place of FTP as it creates an SSH FTP session. TFTP, or Trivial File Transfer Protocol, is a simple stripped-down version of FTP that doesn't support authentication like standard FTP, so it's even more unsecure. It is commonly used to download and upload configuration files for networking equipment. TFTP should only be used when a connection to networking equipment is made through the console port, thus eliminating the possibility of eavesdropping. And that console port should have its own security measures in place. Everyone's fairly familiar with HTTP, or Hypertext Transfer Protocol. It's the protocol that is used to send and receive data over the internet. It is unsecure in its basic format and susceptible to being intercepted due to its lack of encryption. HTTPS, or HTTP Secure, should be used when conducting sensitive business over the internet, as it will provide encryption and other security services. Hopefully your network still doesn't use Serial Line IP, or SLIP. It is an early protocol that was developed for communicating over serial ports and modem connections that required a static IP address. It is very outdated and very unsecure. SLIP does not support encryption. Hopefully you will be using point-to-point protocol in its place. PPP does support encryption and is much more secure. Now it's time to talk about vulnerable network practices. First up are unpatched or legacy systems. Unpatched systems are by their very nature unsecure. Keeping all operating systems and applications up to date will reduce vulnerabilities in the network, and it helps to harden that network against attack. In some situations, it is necessary to keep legacy systems alive. This can create vulnerabilities in the system, as weaknesses in these legacy systems tend to be well known. Special security measures should be taken with legacy systems in order to reduce the opportunity for exploitation. One of the best security steps that you can take is placing these legacy applications or systems on their own network or on their own virtual local area networks. Then there are open ports, and an open port can either be physical or it can be an application port. These open ports create a hole in the security of the network and may be exploited. While not all open ports can or should be closed, security should be placed on these ports that need to remain open to reduce the vulnerability of the network. A good practice is to use a port scanner periodically to verify that only absolutely required application ports are open. Another thing to remember is that you should only use a port scanner if you are authorized to scan that network. or you may end up in a rather lengthy discussion with your security personnel. Unnecessary running services are another vulnerable network practice. Operating system services are used to perform some functions within the system, but it is possible for them to be exploited. A periodic review of all running services should be conducted on all equipment that is attached to the network. All unnecessary running services should be disabled to harden your network. Clear text credentials are another vulnerability that's rather common. Many applications and devices require the use of credentials in order to be used. In some cases, these credentials are sent in clear text format, which makes them easier to read when captured. A good practice is to periodically review all applications and systems to determine which ones use clear text credentials. Then you need to either limit their use or figure out how to encrypt the transmissions to secure your systems. Unencrypted communication channels are another problem. Any method of communication on the network that is not encrypted is an unencrypted channel that is subject to being breached. While not all communication channels need to be encrypted, a good practice is to review all channels and make a decision about which ones need to be encrypted and which ones do not. All wireless network channels should be encrypted. There are no exceptions. Do not create an unencrypted wireless network. That's just asking for problems. A vulnerability that few network administrators think about are RF or radio frequency emanations. One method of intercepting communication is to analyze signal leakage. That's the RF emanation. Many forms of communication are subject to these signal emanations, but there are steps that can be taken to reduce them. Tempest is a set of standards established by the NSA and NATO that outline steps that can be used to reduce the opportunity for the interception and analysis of communication. That concludes this session on common network vulnerabilities. I began with vulnerabilities associated with unsecure protocols. I then concluded with vulnerable network practices. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Common Network Threats Part 1. Today we're going to be discussing inside jobs or threats, and we're going to conclude with some outside threats to your network. With that, let's go ahead and begin this session. Of course, I'm going to begin by talking about inside jobs or threats. First up is malicious employees. We may not know the reason why they're malicious, but they are difficult to defend against as they are already inside the defenses of the network. And because they're employees, resources have been granted to them in order for them to be able to do their job. One of the best defenses against malicious employees is using the principle of least privilege, only granting the least amount of authorization that is required for a person to get their work done. That's the best defense against a malicious employee. Compromised systems are another threat. Once a PC or network device has been compromised, it is vitally important to isolate it from the system as a whole. A compromised PC could lead to a completely compromised network, as malware may be able to spread across its connections. Once malware has gained access to network resources, it can be extremely difficult to root out and remove. Malware may also degrade the network's performance, causing other issues. Then there is social engineering. This is the process of using social pressure to cause somebody to compromise a system from inside the defenses of the network. Social engineering pressure can be applied in multiple forms. An employee can receive a phone call from somebody claiming to be from the IT department asking for their credentials. It may occur in person. The social engineering can occur through email or through a rogue website. There are many avenues in which social engineering can occur. The best defense is through end-user education. Training your end users to resist social engineering is a good idea. ARP cache poisoning is another threat that can occur on your network. In ARP cache poisoning, the ARP cache, which maps IP addresses to MAC addresses, is corrupted by an attacker, with the end result being that the attacker has control of which IP addresses are associated with MAC addresses. It's commonly used in man-in-the-middle attacks, which I will cover in just a bit. Then there are protocol or packet abuse threats. This is the process of taking a specific protocol and repurposing it to perform a different function. Protocol abuse is commonly used to bypass a router's access control list from inside of a network. An example of this is encapsulating a not allowed protocol within a DNS packet, which is almost always an allowed protocol, in order to get that unallowed protocol out of the network. The man-in-the-middle attack is another threat that you should be aware of. The attacker is not necessarily inside the network per se, but is in between two endpoints that are communicating on a network. In most cases, the man-in-the-middle attack involves disrupting the ARP process between the two endpoints. The attack allows a malicious user to be able to view all network packets that are flowing between the communicating hosts. Often a man-in-the-middle attack is used in an attempt to gain sensitive information like network credentials. Then there's VLAN hopping. This is circumventing the security that is inherent when virtual local area networks are created. Normally, traffic that is tagged for one VLAN is not allowed onto another VLAN without the intervention of a router. VLAN hopping occurs when the attacker adds an additional fake VLAN tag to the network packets. Once the packets get to the switch strips one of the VLAN tags off the packet and then passes it through. Once through the switch, the packet is considered as belonging to the new VLAN, thus bypassing the security that's inherent in VLANs. Now let's move to outside threats. One of the largest threats that face network security personnel is the unknown vulnerability. Network and systems administrators expend vast amounts of time protecting the assets under their control, and they can do a pretty good job of hardening their systems, but it's not a perfect job. The problem lies with zero-day attacks. Zero-day attacks take advantage of either new or recently discovered vulnerabilities, which means that the networks and systems probably haven't been hardened against them yet. The unfortunate reality is that attacks keep changing, and security experts must be willing to adapt in order to keep pace. If they can't adapt, they will fall behind and their networks become vulnerable. Let's talk about the brute force attack. This is using computing power and time to compromise passwords. The attacker uses a program that continually tries different password combinations, often in the form of a special dictionary application, in an effort to crack a password. The best defense against this is to limit the number of times that a user can attempt to log on before they're locked out. Then there's spoofing. This is a category of threats where either the MAC address or the IP address of the attacker has been modified to look like a friendly address in order to bypass network security. A common use in the past was for an attacker to spoof their IP address so that the outside attacker was actually viewed as an inside host. A common defense against this type of spoofing is an ACL rule that doesn't allow an inside IP address to come from outside of your network. Then there's session hijacking. An attacker attempts to take over a communication session after a user has been authenticated. The hijacking can occur through various methods, as in using a packet sniffer to steal a session cookie or installing malware on a user's computer that is activated after the user is authenticated. That concludes this session on Common Network Threats Part 1. I talked about inside jobs or threats, and then I concluded with a brief discussion on some outside threats. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Common Network Threats Part 2. Today I'm going to be talking about more outside threats, and then I'm going to be talking about some wireless network threats. I have a fair amount of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about outside threats. Because of how they are implemented, it is often difficult to put network security threats into a single category. Many attempts to breach a network combine different aspects of different threats. For example, a man-in-the-middle attack is often combined with some type of spoofing that is used to help it succeed. That means that in most cases, security requires more than just a single line of defense. Good administrators recognize this and implement multiple layers of security in order to harden and protect their systems. The first major threat that we're going to talk about is the denial of service threat, or the DOS threat. This covers a very broad category of threats to networks and systems. That's because DOS covers any threat that can potentially keep users or customers from using network resources as designed. A traditional DOS attack attempts to flood a network with enough traffic to bring it down. It's commonly used with a flood of malformed ICMP requests. The host that receives the flood can be so busy dealing with the deluge of data that it cannot respond to legitimate requests. Then there's the permanent DOS attack. It's an attempt to permanently deny a network resource for others. It can be achieved by physically destroying or removing the resource, or it can also be achieved through the use of malware that corrupts or damages the underlying digital system to the point where it cannot be repaired and must be replaced. There are also friendly or unintentional denial of service attacks. An unintended DOS attack can occur when poorly written applications consume more network resources than are available. Another unintentional DOS attack can occur when a network interface controller, or NIC, begins to fail. It's quite common when a NIC is about to fail for it to go offline and come back online repeatedly and rapidly. This consumes network resources, which can cause an unintentional DOS. More disruptive than the standard denial of service attack is the distributed denial of service attack, or the DDoS attack. It's a denial of service attack in which more than a single system is involved in sending the attack. A DDoS attack has a higher chance of succeeding due to the increased number of participants. The machines used to send the attack may be voluntary participants, this is called a coordinated attack, or they may be part of a botnet. With the botnet, malware has been installed on the machines and they are no longer under the complete control of their owners. Many distributed denial of service attacks involve botnets where the attacker has actually rented the botnet for the sole purpose of performing the DDoS. The goal of the DDoS is to create a large enough spike in traffic that the target becomes unreachable. In some cases, the target system may need to be rebooted in order for it to come back online. There's the reflective denial of service attack. It's also known as an amplified DOS. The attacker uses some method, usually some form of spoofing, to hide the source of the attack. In a reflective DNS attack, the attacker usually spoofs the intended target's IP address and sends multiple requests to an open DNS server. The DNS server responds by sending traffic back to the targeted system, and the attacker's hope is that the response from the DNS server will overwhelm the targeted system. A cousin to the reflective DNS attack is the reflective NTP attack, or the reflective network time protocol attack. It works in the same way. However, instead of using DNS, it relies upon open NTP servers. Not very common anymore, but you still need to know about it, are the Smurf attacks, also known as smurfing. It's a type of reflective denial of service attack that also involves spoofing the intended target's IP address. A network is flooded with ICMP requests in which the source address for the requests appear to be that of the intended target. As the replies return, the network becomes slowed down by the traffic. The goal is to overwhelm the target system and bring it down. It's time to move on to wireless network threats. Our first topic is an unintended threat. A common feature on modern wireless access points is Wi-Fi Protected Setup, or WPS. The goal of WPS is to create an easy and secure method for consumers and small businesses to set up a secure wireless network. Unfortunately, the outcome has fallen short of the goal. While WPS does ease the setup burden, it is also easily exploited by an attacker and should actually be disabled on all equipment. This exploit has been known for a couple of years, and you would think that equipment manufacturers would quit enabling WPS by default on their equipment, but that's not the case. So when you set it up, you need to disable WPS. Then there's war driving or war chalking. This is the practice of attempting to sniff out unprotected or minimally protected wireless networks. Once it's found, marks are placed on buildings and streets indicating that networks are available and vulnerable. Something to remember is that wireless networks are vulnerable merely due to the fact that they need to broadcast over the air. Then there's WEP cracking or WPA cracking. This is using a packet sniffer to capture the password and/or the pre-shared key on a wireless network. Wired equivalent privacy, or WEP, can be cracked in minutes. Wi-Fi protected access, or WPA cracking, will take hours, but it can still be cracked. Neither of these encryption standards should be used on your wireless networks. Rogue access point attacks are another threat that you need to be aware of. This is where an unauthorized WAP gets installed onto the network. Unfortunately, the biggest culprits are the end users themselves. They install their own wireless access points for convenience and then don't properly secure it. This opens a vulnerability into your network. You need to periodically check for rogue access points on your networks, even if you don't have wireless installed. Related to the rogue wireless access point attack is the evil twin attack. A WAP is installed and configured with an SSID that is very similar to the authorized version. As users access the evil twin, their keystrokes are captured in the hopes of gaining sensitive information, like the credentials to log into the actual wireless network. The evil twin attack can also be considered as a type of wireless phishing attack. Then there's bluejacking. Bluejacking is the sending of unsolicited messages over a Bluetooth connection in an effort to keep the target from responding to valid requests. It's more of an annoyance than an actual network threat because it mostly involves the personal area network, which tend to be very limited in their abilities. Related to bluejacking is blue snarfing. It's an attack in which the attacker creates a Bluetooth connection with another device without that device's permission. The goal is to retrieve information from the attacked device, as in contact information or stored email. This vulnerability has been patched and may no longer be a concern, but you still need to be aware of it. Now that concludes this session on Common Network Threats Part 2. I talked about outside threats and I concluded with some wireless network threats. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Network Hardening Techniques Part 1. Today I'm going to discuss using secure protocols, using anti-malware software, and I'm going to conclude with implementing switch and router security. There's a whole lot of information to impart, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about using secure protocols. Network security is always an ongoing process because the threats to it keep changing. Although security threats are continually evolving, administrators can use some techniques to harden the base network structure to help ease the ever-shifting security landscape. These hardening techniques establish a good security foundation that can be further built upon, making the network that much harder to crack. One of these hardening techniques is to use secure protocols whenever possible. So let's discuss some of those protocols. First up is Secure Shell, or SSH. It's a protocol that is used to create an encrypted communications session between devices. It's commonly used to create a secure virtual terminal session. It should be used in place of Telnet whenever possible. Then there's SNMP version 3. That's Simple Network Management Protocol version 3. It's a protocol that's used to manage and configure devices remotely on the network. It's more secure than the prior two versions because it supports encryption. Secure File Transfer Protocol, or SFTP, should always be used in place of FTP. It's a protocol that's used to transfer data and manage file structures in a secure manner through the use of an SSH session. As I said just a moment ago, it is a better option than FTP, which requires user authentication but does not encrypt the communication. SFTP encrypts the whole process. Then there's TLS, or Transport Layer Security. It's a cryptographic protocol that's used to encrypt online communications. It uses certificates and asymmetrical cryptography to authenticate hosts and exchange security keys. It is a better option than SSL, or Secure Socket Layer, which functions in a similar manner. When performing sensitive online business, you should use HTTPS, Hypertext Transfer Protocol Secure. It's a protocol that is used to secure the communications channel between a web browser and a web server. HTTPS uses either TLS or SSL technology. IPsec, or IPsec, is a network layer IP security protocol suite that can use multiple methods to mutually authenticate both ends of the communication channel. It also will encrypt all data transmissions. Unlike most other protocols, it can provide end-to-end security for any application. Let's move to using anti-malware software. Anti-malware applications help to protect networks and network resources against malware intrusions, as in spyware, viruses, and worms. There are three main options for using anti-malware applications. There's host-based anti-malware. The application is installed on the individual machines and only protects those nodes on which it resides. It's easily tuned to the needs of the individual host, but requires that the user keep it up to date. Then there's network-based anti-malware. The application is installed within the local network and served to the individual clients that require it. It is easily administered, but harder to tune for the individual hosts. But the network administrator can ensure that it remains up to date. And finally, there's cloud-based anti-malware. The application resides in the cloud, so it is outside of the local network. And it is served to the clients inside the local network as needed. This service has a very small footprint on the local machine and tends to be kept more current than the other options. But it is an added cost that must be evaluated. Let's conclude with talking about implementing switch and router security. When is using a password not secure? Well, the answer is when the password is kept in clear text. One solution to this is to save passwords and other sensitive information as hashes. Hashing is a cryptographic process that uses an algorithm to derive a set value, also known as the hashed value, from the sensitive data. The hash can be used to verify that data is coming from where it is supposed to and that it has not been intercepted or changed in transit. The most popular hashing algorithms are MD5 and SHA or SHA. Of the two, SHA is the more secure. And the wise network administrator makes sure that all passwords and usernames are kept as hashed values. Under implementing switch security measures, switch port security measures are vital. First off, switch port security should be enabled. All enterprise switches are capable of having security measures enabled at the port level, and that should happen. Also, the native VLAN should be changed from its default value. All active ports should be assigned to non-native VLANs. All non-active switch ports should be assigned to an unused non-native VLAN. Also, VLANs should be created to clearly segment the network into logical, secure areas. A switch port security measure that should be considered is MAC address filtering. This will only allow specific MAC addresses to connect to specific ports. DHCP snooping should be enabled. This will only allow DHCP responses from an administrator-defined switch port. This means that all DHCP responses will come from the same port. In addition to DHCP snooping, dynamic ARP inspection, or DAI, should also be enabled. This process is combined with DHCP snooping to restrict the opportunity for ARP cache poisoning to occur. All address resolution protocol requests are compared against the ARP table contained in the administratively defined DHCP server. Implementing these measures will greatly increase the security of your switches. Let's move on to router security measures. Each interface on a router should have an access control list, or ACL, in place to control and filter traffic. Each interface can actually have two ACLs. One ACL on the inbound side of the interface and one ACL on the outbound side of the interface. An ACL is a set of rules that is used to govern and filter the flow of network traffic into and out of a network. The ACL examines packets against its established rules, beginning from the first rule at the top of the list and continuing down through all the rules. The rules either allow or deny the packet from continuing. Once the packet matches a rule, the rule is enforced and the ACL process is exited. ACL rules can be based on protocols and ports, IP addresses, source addresses, destination addresses, etc. All ACLs end with an implicit deny statement, meaning that if it isn't specifically allowed, then the packet is discarded. The ACL can be time-based, as in day of the week or time of day, and it can fulfill a specific function based on the reason that it is created. As in, an ACL can be used to filter out websites or web content. That concludes this session on Network Hardening Techniques Part 1. I talked about using secure protocols, then we moved on to using anti-malware software, and we concluded with a brief discussion on implementing switch and router security. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Network Hardening Techniques Part 2. Today we're going to talk about encryption basics, and then we're going to talk about wireless network hardening, and then I'm going to conclude with a brief discussion on security policies. With that, let's go ahead and begin this session. I'm going to begin by talking about encryption basics. Encryption is the process of taking a message and scrambling the data so that it can't be read if it gets intercepted. Encryption relies upon the fact that the receiver of the scrambled data has the proper key that allows it to unscramble the data and put the message back together. The strength of the encryption is usually determined by the strength of the key. The strength of the key is measured in the number of bits that it takes to generate the key. The more bits that it takes, the stronger the key is. There are two basic types of encryption. There's symmetrical encryption, in which both ends of the communication channel use the same key to encrypt and decrypt the message. Pre-shared key, or PSK, is symmetrical in nature. Then there's asymmetrical encryption, in which two different security keys are used in an arrangement called PKI, or Public Key Infrastructure. The private key encrypts the message and the public key decrypts the message. On the return side, the original receiver encrypts with the original sender's public key, which then gets decrypted with the private key. In this arrangement, the private key cannot decrypt what it encrypted, and the public key cannot decrypt what it encrypted. So it only works if there are two separate keys. So let's talk about those asymmetrical encryption keys. There are two main types of asymmetrical encryption keys. There is the EAP TLS type key, that's Extensible Authentication Protocol Transport Layer Security type of key. It requires the use of a certificate authority, or CA, that is trusted by both parties. The CA provides the certificates to both parties that allow for the generation of both the public and private security keys. It's very secure, but it is also difficult to manage and maintain. Then there's TTLS, Tunneling Transport Layer Security. It's as secure as the EAP TLS, but only the authentication server receives a certificate for the key generation process, and it's easier to manage and maintain than EAP TLS. With that covered, let's move on to wireless network hardening. Wireless networks can represent a special challenge in the network hardening process. The goal of most hardening techniques is to keep nefarious elements from ever seeing the network traffic. But with wireless networks, that is all but impossible, as traffic is broadcast over known radio frequency channels. This traffic is subject to capture, and the transmissions inform any who care that an active wireless network is present. There are steps that can be taken, as in encrypting the traffic, to make sure that even if the network traffic is captured, it cannot be read. This helps to keep the network traffic safe and the network from being breached. One of the first techniques that you can use to harden a wireless network is MAC address filtering. MAC address filtering can be used to limit which devices can connect to the wireless network. If an unknown MAC address attempts to connect to the network, it is ignored by the wireless access point. So when it requests to join, the WAP checks its MAC filter, and if that MAC isn't in the filter, it just drops that requester. While MAC filtering can be effective, it can also be difficult to manage, and it is also possible to spoof MAC addresses. Which brings us to basic authentication and encryption for wireless networks. First up is WEP, or Wired Equivalent Privacy. It's an encryption standard that uses either a 40-bit or a 128-bit encryption key and the RC4 algorithm to authenticate devices and encrypt transmissions. It uses a pre-shared key as a password or passphrase to authenticate users. WEP is easily cracked and should not be used. As a matter of fact, WEP can be cracked in minutes. Better than WEP is WPA, Wi-Fi Protected Access. It's an authentication and encryption standard that improved upon WEP, but still uses PSK and the RC4 algorithm. But to increase security, it also introduced Temporal Key Integrity Protocol, or TKIP. TKIP generates a new security key for every packet, and that new security key has a strength of 128 bits or greater. Now, it's not as easily cracked as WEP, but it can still be cracked and should not be used unless absolutely necessary. and hopefully that's not the case in your wireless network. Better than WPA is WPA2 Personal, Wi-Fi Protected Access 2 Personal. It's an authentication and encryption standard that improved upon WPA. It does not rely upon the weak RC4 encryption algorithm, but it does use AES as its algorithm. That's Advanced Encryption Standard. It can also use the PSK method, but this is not required, as WPA2 Personal can also dynamically assign security keys. While it's theoretically possible to crack WPA2 Personal, it would be extremely difficult to do so, so this should be the minimum level of security on any wireless network. Better yet, if possible, deploy WPA2 Enterprise. Now this forms a portion of the 802.1x standard. It is used to authenticate users on a wireless network and uses one of the forms of the Extensible Authentication Protocol in setting up the encryption. A central authentication server is required for 802.1x or WPA2 Enterprise, which does allow for greater control over the authentication process. As a side note, EAP is actually a set of definitions for how security keys will be exchanged in order for encryption to take place. It's time to conclude with a brief discussion on security policies. While security policies are only written documents, they can actually do quite a bit to harden a network against a breach. Security policies document or outline what is allowed or not allowed to occur on the network from a security point of view. They are usually crafted at the upper layer of management with the help of knowledgeable IT personnel. They establish the expected behavior, which can go a long ways towards hardening your network. Security policies give administrators the authority to put into place measures to protect the security of the network. In many cases, they also give administrators the authority to enforce the policies that lead to a hardened network. Well, that concludes this session on Network Hardening Techniques Part 2. I began by talking about encryption basics, then we moved on to wireless network hardening, and we concluded with a brief discussion on security policies. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Network Hardening Techniques Part 3. Today I'm going to discuss user authentication, and then I'm going to talk about some authentication and authorization methods. There's a fair amount of ground to cover, so let's go ahead and dive into this session. Of course, I'm going to start by talking about user authentication. Hardening the network will not do you any good if there is poor authentication of the users and devices that are allowed on the network. The process of proving that you are who you say you are, if you are a person, or that you are what you say you are, if it's a device, is called authentication. Authentication is different than authorization. Authorization is what you are allowed to do after you have been authenticated. There are several different ways in which users can be authenticated, and there are several different methods in which authentication can be implemented. Let's talk about basic authentication of the user. There are three basic factors for authenticating users. There's by what you know. This is the user and password method. By what you are. This is commonly implemented through biometrics. And finally, there is by what you have. This is commonly implemented through the use of security tokens. These are the three basic factors for authenticating users. Now you can combine these in a process that's called multi-factor authentication. That's requiring the use of more than one of the factors of authentication, as in requiring a password and a fingerprint scan, or the code from a security token and a password. Those are multi-factor authentication. Now, multi-factor authentication is used to increase the security of the authentication process. You might also implement a single sign-on process. It's a process in which the user only has to provide authentication once via a single smart device rather than having to authenticate for each and every network resource that they request. So let's talk about authentication and authorization methods. The first method we're going to talk about is PAP, Password Authentication Protocol. When logging into a network resource, the user or device is required to supply a username and password. The username and password are sent in clear text format, so this method is considered unsecure and should only be used as a last resort. More secure than PAP is CHAP, Challenge Handshake Authentication Protocol. It is similar to PAP in that when logging into a network resource, the user or device is challenged to supply a username and secret password, and it authenticates through a three-way handshake process. The way it works, the resource issues a challenge. It wants to know the hashed value of the username and secret password. The user's device sends the hashed value to the resource device. The resource evaluates the hashed value and either accepts or rejects the connection. By using CHAP, the username and password are never sent in clear text. It's much more secure than PAP. There's also MS-CHAP. It's functionally the same as Challenge Handshake Authentication Protocol, but it is Microsoft's proprietary implementation of it. You might also implement one of the forms of Extensible Authentication Protocol, or EAP. It's not a single protocol on its own, but a set of additional authentication methods used by remote access clients. Currently, there are more than 100 different methods defined by the EAP specifications. One of the more popular is Kerberos. So let's talk about Kerberos. It's an authentication protocol which uses TCP or UDP port 88 by default. It's a system of authentication and authorization that works well in environments that have a lot of clients. The main component of Kerberos is the Key Distribution Center, or the KDC. The KDC has two parts, the Authentication Server, or AS, and the Ticket Granting Service, or TGS. Here's how it works. When a user logs in, a hashed value of his or her username and password is sent to the authentication server. If the AS likes the hash, it responds with a ticket granting ticket and a timestamp. So it will respond with a TGT that also has a timestamp. The client then sends the TGT with the timestamp to the ticket granting service, the TGS. The TGS then responds with a service ticket, which can also be called an access token or just a token. The service ticket authorizes the user to access specific resources on that network. As long as the TGT is still valid, the TGS will grant additional authorization by issuing a new service ticket as required for as long as the TGT and its timestamp are still valid. Now that concludes this session on Network Hardening Techniques Part 3. I talked about user authentication, and then we concluded by talking about authentication and authorization methods. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Physical Network Security Control. Today we're going to be discussing the why of physical network security, and then we're going to move on to some physical network security practices. There's a fair amount of information to impart, so let's go ahead and begin this session. Of course, I'm going to begin by discussing the why of physical network security. Your network security actually begins at the door. The boundaries of your building should be your first line of defense. If an attacker has physical access to the network resources, then there is a high probability that those network resources can be breached. The level of security that gets deployed should be driven by the amount of security that is needed. As the need for overall security increases, so should the level of physical security. There are dangers that are associated with unauthorized physical access. There is theft of those network resources, and they are expensive to replace. Unintentional damage can occur when there is unauthorized physical access. It only takes a simple spilled drink to destroy a server or a router or a switch or some other expensive component. It's also possible that if an attacker has physical access, they can reconfigure those network resources. This can result in a breached network. One type of reconfiguration that's possible are devices that have credential workarounds. Some networking equipment comes with known workarounds for when administrator credentials need to be recovered, as in when an administrator leaves an organization without disclosing his or her logon credentials, or when an administrator forgets those credentials. Cisco even publishes the steps of its workaround on its website, and those steps are available for anybody to review. If you're curious about those steps, you can check out that web link that I've posted here. This well-known vulnerability is an easy exploit for anybody that has physical access to Cisco equipment. With the why of physical network security out of the way, let's move on to physical network security practices. Basic physical security should include knowing who's in the building and who has access to equipment. You can do that through employee badges. Security check-in should be implemented for all visitors. All vulnerable network resources, as in servers and networking equipment, should be kept in a secure area. Then there's intermediate physical security. This is where access to all vulnerable network resources is controlled and logged. One way to implement this is to use RFID badges to gain access to network resources. Or you could implement cipher locks that people have to punch in a code in order to unlock the door. Another step in intermediate physical security is the separation of resources. Switches and routers are secured separately from servers, with different access levels for the servers and the networking equipment. In environments where high security is needed, advanced physical security needs to be implemented. A zoned approach is an advanced physical security practice. It's a layering of security in which multiple barriers, or security tests, must be passed before physical access is granted. The methods of physical security that are used can be thought of as those security tests. You can use security guards, requiring all authorized personnel to have some form of ID so that the security guards can identify if that person is in an area in which they're allowed. Then there are door locks. You could use simple keyed locks, the analog approach. A slightly more advanced method would be cipher locks, with the deployment of different codes for different areas or different groups of people. This allows for the logging of who has unlocked a door. You might also implement RFID magnetic locks, which also allow for the logging of who has unlocked the lock. One of the most advanced types of door locks would be a biometric lock. They're locks that make the person gaining access prove who they are through either a fingerprint scan or a retinal scan, or possibly even a voice print. Video monitoring can also be deployed as a form of physical security, allowing you to record who has had access to those resources. You need to remember to store the recordings separately from the resources being monitored, so if the resource gets stolen, they don't steal the recording as well. You may implement a separation of resources. Networking equipment is kept separate from servers, and the methods of access for the two resources are different. And finally, in highly secure environments, a man-trap may be implemented. A man-trap usually involves at least two doors. Access is granted through one door, but the next door cannot be opened until further verification has been achieved, and the person that's between the doors cannot go back out the other door. That means that ideally the person between the doors is trapped until some action or verification takes place. That concludes this session on physical network security control. We talked about the why of physical network security, and then we concluded with a brief discussion on physical network security practices. Good day, I'm Brian Farrell, and welcome to PACE IT's session on firewall basics. Today I'm going to discuss types of firewalls, and then we're going to move on to firewall settings and techniques. I have a whole plethora of information to impart, not a whole lot of time, so let's go ahead and jump into today's session. Of course, I'm going to start with types of firewalls. First up are host-based firewalls. These are installed at the node, which is usually a desktop computer. They're often used in conjunction with network-based firewalls. Now, host-based firewalls are always software applications. Then there are network-based firewalls. Usually these are implemented on the perimeter of the network segment that needs the protection. They're used to protect private networks from public or outside networks. Network-based firewalls can be a network appliance, which means that it was specially designed and deployed to provide only firewall services, or it can be a software application, either as part of the router's operating system or as a specialty application on a server that is providing some routing function. It's time to move on to small office, home office firewalls. In most cases, the network firewall is provided by a wide area network connection device. So most often the main firewall is provided by the DSL modem or the cable modem. In conjunction with this, a host-based firewall is often used with the network-based firewall. This provides a little bit more protection, and it allows for more granular configuration of the firewall protection part of network security. There are stateless inspection firewalls. These examine all the packets either entering or leaving the network. It examines these packets against a set of rules. This set of rules is called an access control list, or ACL. The ACL rules are defined as static values by an administrator. As I stated, all of the packets are examined against the rules in the ACL, starting with the first rule. If a packet matches a rule, that rule is enforced and then the ACL is exited. Stateless inspection firewalls do not care about the state of the connection. They only care about the packets, and all packets are examined. Then there are stateful inspection firewalls. A stateful inspection firewall doesn't really care about the packets, it only cares about the state of a connection between two endpoints. As a general rule, connections are not allowed to be made from outside of the local network segment to the local network segment being protected. Only the initial packets going from inside the network to a destination outside of the network are inspected against an ACL. If the ACL allows those packets to leave the network and a connection is made, or once the connection has been established, the firewall only monitors the state of that connection. It allows the free flow of packets between the inside node and the outside destination as long as the state of the connection remains valid. There are application-aware firewalls. These are firewalls that not only examine the packets, but also the application protocol that is being used. So it knows if it's FTP or HTTP that's being used. Application-aware firewalls make allow or deny decisions based on the application layer protocol as well as other ACL rules. They are slower but more thorough in protecting the private network than firewalls that are not application aware. There are also context-aware firewalls. These are firewalls that can identify not only applications but also users and/or devices. This is the context of the traffic. So context-aware firewalls can be used to restrict or allow traffic based on the context as well as other ACL rules. Then there are Unified Threat Management Devices, or UTM devices. These are network appliances that include not only a firewall service, but other services as well, usually intrusion detection services or intrusion prevention services. One concern with a UTM device is that it can create a single point of failure in the network. What happens to the network if that UTM device fails? Is your security gone, or does the network go down? That is a concern about using a UTM. Most often, firewalls are implemented on a router's interface or at the host level. When implemented on the router interface, the firewall takes part in the routing process. When implemented at the host level, the firewall protects the host on which it resides. There is an exception to these scenarios, and it's the implementation of a virtual wire firewall. This type of firewall is a network-based firewall that resides between two devices and provides neither routing nor switching functions. It contains two interfaces, and as traffic passes between those interfaces, the packets are compared to an ACL. But it's usually not used to protect a specific host, and it does not take part in the routing function. It's time to proceed with firewall settings and techniques. First up is the ACL. Each firewall interface may have two ACLs associated with it, an inbound ACL and an outbound ACL. The inbound ACL examines all packets inbound on that interface. An outbound ACL examines all packets outbound on that interface. The ACL contains a set of administrator-defined rules that either allow or deny packet traffic. Rules can be based on such criteria as source or destination, IP address, MAC address, protocol, and time of day. When an ACL examines packets, those packets are examined against the set of rules from top to bottom. Once a rule is matched, as in deny FTP packets from leaving the network, that rule is enforced and the ACL is exited. The last rule of any ACL is an implicit deny. That means if the packet being evaluated does not match any of the explicit rules of the ACL, the implicit deny is enacted and the packet is blocked. Care and caution should be used whenever creating an ACL, if nothing else, because that implicit deny statement ends every ACL list. You may end up blocking traffic that you did not intend to block. It's time to discuss firewall placement, and we're going to begin with perimeter placement. This requires that the firewall be placed at the outside edge, usually at the wide area network connection, of the local segment or the LAN segment. Stateful inspection firewalls work well on the perimeter. They are usually slower to make the initial connection, but once that connection is achieved, they offer better performance. You could have internal placement of your firewall. This requires that the firewall be placed in a logical central location. It's usually used to route between different internal private networks. Stateless inspection firewalls work well for internal placement. They are faster to make connections and require less memory. A DMZ or demilitarized zone requires a special configuration or placement considerations for your firewalls. The DMZ is a specific area that is created, usually between two firewalls, that allows outside access to network resources while the internal network is still protected from outside traffic. You should consider using a DMZ if you're going to have a web server on your network. Outside users will need to access your web server, which is on your network, but your internal network still needs to be protected from malicious traffic. The external facing router allows specific outside traffic into the DMZ, while the internal router prevents that same outside traffic from entering the internal network. That concludes this session on firewall basics. I talked about types of firewalls, and then we ended with firewall settings and techniques. Good day, I'm Brian Farrell, and welcome to PACE IT's session on network access control. Today we're going to be talking about edge versus access control, and then we're going to talk about some access control concepts. With that, let's go ahead and begin this session. Of course, I'm going to begin by talking about edge versus access control. When access to network resources is granted or denied by a firewall, it is considered to be at the edge of the network. So that is edge control. While this may work well in smaller and simpler networks, it can become very complicated and cumbersome as the network grows. Through implementing other access control measures, these complications can be reduced, while at the same time the security of the network may be increased. This idea is called Network Access Control, or NAC. These access control measures do not replace the need for firewalls. They do, however, allow the firewalls to concentrate on controlling network traffic into and out of the network. That is what they do best, and that is what they should be concerned about, not who or what type of device can connect to the network. Firewalls are not very efficient at that aspect of edge access control. Let's move on to some access control concepts. First up is authentication via 802.1x. 802.1x is a popular method of authenticating client devices and users on either Ethernet or wireless networks. When a client device, which is called the supplicant, attempts to join a network, an authenticator, which is usually a switch or wireless access point, requests the supplicant's credentials. The authenticator then forwards the client's credentials to an authentication server, or AS, which is typically running software such as Remote Authentication Dial-In User Service, or RADIUS. The authentication server evaluates the credentials and either informs the authenticator to allow or deny the supplicant device access to the protected network. If the credentials are validated, the authenticator, that's that switch or wireless access point, grants the supplicant access to the protected network. 802.1x is very popular in enterprise-type networks. Access control can also be achieved through posture assessment. This is the process of evaluating more than just the client's credentials. Commonly, posture assessment is used to evaluate the type of device that is requesting a connection. Is it a tablet, or is it a PC, or is it a mobile phone, so on and so forth. Posture assessment can be used to evaluate the type of anti-malware software that's on the device and how updated that software is. During this process, a check is also performed to determine if malware is present on the device. Posture assessment is commonly used to evaluate the operating system as well, as in how updated that operating system is and what the registry settings are at the time that access is being requested. If the client passes the assessment, it is allowed onto the protected network. If the client does not pass the assessment, usually one of two actions are taken. The first action could be that the client is notified of the rejection and what has to occur before it can pass the posture assessment. Does it need an operating system update? Does it need anti-malware installed? So on and so forth. The other action that is commonly taken when a device has failed the posture assessment is that it is passed on to a remediation server, which will then attempt to resolve the cause of the failed posture assessment. It will do this with no user interaction required. Once it has remediated the device and it can pass the assessment, it then goes through the process again and is allowed onto the network if it passes. It's time to move on to the posture assessment process. One of two types of agents, think software code, is used on client devices during the assessment process. It could be a persistent agent, which is permanently loaded on the device and starts when the operating system loads. This type of agent can provide more functionality than the other version. A persistent agent is more likely to be used if that device regularly connects to the network. The other type of agent is a non-persistent agent. When the client device attempts to access the network, the agent is loaded onto the device to help in the assessment process. Once the assessment process is completed, pass or fail, the agent is removed from the device. A non-persistent agent would work best for a guest device. When devices attempt to connect to the protected network, they are placed on a guest network with very limited access. They are left on the guest network until the assessment process is completed. In some cases, particularly when the client fails the anti-malware check, the client device may be placed into a quarantine network, which will only have access to a remediation server, and it cannot move beyond that quarantine network until it can successfully pass the posture assessment. Now that concludes this session on network access control. I talked about edge versus access control, and then we concluded with some access control concepts. Good day, I'm Brian Farrell, and welcome to PACE IT's session on basic forensic concepts. Today I'm going to be discussing collecting the evidence, and then we're going to have a discussion on what to do after the evidence has been collected. I have a fair amount of ground to cover, so let's go ahead and begin this session. We will begin this session by talking about actually collecting the evidence. The first step in basic forensics is the recognition that forensic measures need to take place, as in that a security incident has occurred. Most of us, at least hopefully, will not need to deal with a murder mystery, at least not in the workplace. With that said, it's almost certain that we will have to deal with some type of security or legal issue when supporting an organization's network. The response to security and legal issues needs to be done in a manner such that evidence is recorded and preserved. The first step is recognizing that something has occurred which needs to be documented and that the evidence needs to be collected and preserved. That's the first step in forensics, at least as far as forensics pertains to network administration. Network administrators and technicians are quite often the first responders to a security breach on IT systems. As such, they have some responsibilities. First off, they need to secure the area and limit who has access as much as possible. Also, do not power down computer systems. The restricting of access and not powering down the systems is done to protect possible evidence from being contaminated. Document everyone who has accessed the area after it has been secured. This protects your chain of custody. If necessary, to stop an ongoing computer attack, it is permissible to unplug the network cable from the computer, but that's it. Once the area is secure, if necessary, now is the time to escalate the response. Depending upon the situation, you may need to bring in specialists or even the police. No matter what, it's important that the scene get documented thoroughly, including what is on any computer monitors. Taking photographs is a great way to document the scene. If photographs are taken, they should be done with a Polaroid type camera and film, not with digital pictures. It's harder to manipulate a Polaroid and therefore it's more believable than a digital image. It may also be necessary to diagram to draw out the area. Also, interview any witnesses as soon as possible, before their memory starts to degrade or before they begin to collaborate on what story to tell. Also, the electronic evidence collection process needs to begin as soon as possible, and it needs to be collected by order of volatility. So let's talk about the evidence and data collection process. electronic evidence is volatile and easily corruptible just because of what it is. It's magnetic data. So the order of collection is important. The first thing that should be collected are the contents of memory, or RAM. This is the most volatile of all types of data. Next are swap files. They're not as volatile as random access memory, but are still very temporary in nature. Then all network processes need to be documented, at least all of those that are active on the affected system or systems. After documenting network processes, next up are the system processes, and that is all system processes that are active on the affected system. After that, move on to file system information, including the attributes of the files. You need to do this before you do anything else so that you have completely documented the attributes of the files. Once all of that is done, it's time to make a copy of all of the contents on all of the disk drives of the affected systems. And that would be by raw disk blocks. So let's talk about that a little bit more. After isolating the affected system or systems from the network, you need to create a bit level image of the system or systems. That means an exact duplicate of the disk drives. And actually you need to create two copies, two images. And with those two images, you also need to create a message digest of the image drives to be able to later prove that they have not been tampered with. You can use MD5 or SHA as the hash algorithm to make that message digest. One image should be securely stored to be used as evidence, and with that should go the hashed image. That way you can prove in court that it hasn't been tampered with. The other image can be examined and modified in order to determine what exactly happened. Now let's move on to a discussion about what happens after the evidence has been collected. And the first item is the chain of custody. Now this actually starts during the collection period and survives the collection period on into the future. The chain of custody is a document that identifies who collected the evidence, when it was collected, and who has had access to it since it has been collected. Proper chain of custody document can prove that the evidence has been accurately preserved, and the chain of custody document can also be considered part of the evidence. A chain of custody document will help to ensure that all the evidence that is collected is admissible in court. A broken chain of custody will negate the collected evidence. And by that, if your chain of custody gets broken, your evidence is no longer considered evidence. So now let's talk about the e-discovery process, or the electronic discovery process. In legal situations, the discovery process involves the exchange of evidence between both sides of a litigation or prosecution situation. E-discovery refers to the discovery process as it pertains to electronic data, as in email, database files, or chat records, any data that's kept in electronic format. Once identified in the e-discovery process, a legal hold is placed on the data that has been identified. A legal hold occurs when data has been deemed to be possibly relevant in either a prosecution or litigation situation. If a legal hold occurs, all normal processing of that data needs to cease. That data needs to remain in the state that it was in during the e-discovery process. So a legal hold requires that backup tapes not be recycled and that the normal archival process for that data be suspended until the legal hold is removed. There are some items to consider when electronic data needs to be transported and it's considered evidence. If it's physical evidence, as in a hard drive, a chain of custody document must be created for the transportation process, and it needs to include an exact description of the evidence, the means of transport, who received the evidence to transport it, and who had access to the evidence during the transport process. If you're using electronic means of transport, a message digest should also be included to prove that the exact evidence sent is the evidence that is received. Once the forensic process has concluded, or once the investigation has been completed, a forensic report needs to be created based on the findings of the investigation. During the evidence collection and investigation process, the characteristics of the evidence should have been documented, so you know what timestamps were present or any identifying properties that are associated with that evidence. All of this information needs to be recorded and analyzed using scientific methods. Once completed, the forensic report should be able to completely reconstruct and document the evidence. A forensic report may be used in the litigation or prosecution process. In addition, a good forensic report may help in the creation of a better response plan for use in the future. Now that concludes this session on basic forensic concepts. I talked about collecting the evidence, and then we concluded about what happens after the evidence has been collected. Good day, I'm Brian Farrell, and welcome to PACE IT's session on network troubleshooting methodology. Today I'm going to be talking about the importance of a methodology, and then I'm going to cover the 7-step troubleshooting methodology recommended by CompTIA. There's a fair amount of ground to cover, not a whole lot of time, so let's go ahead and begin this session. We are going to begin by discussing the importance of a methodology. First up is one of my favorite quotes concerning methodologies. And it is, "My methodology is not knowing what I'm doing and making that work for me." That's from Stone Gossard of Pearl Jam, and unfortunately, we don't quite have that kind of liberty when it comes to troubleshooting networks. All networks will require troubleshooting. If you don't know where to start or haven't developed a methodology, you will waste time and resources. The complexity of modern networks means that there is a lot that can go wrong. Without a troubleshooting methodology, your frustration levels and the frustration levels of those you support is going to rise. A systematic troubleshooting methodology can significantly reduce the time required to resolve a problem and close a network trouble ticket, saving both time and other resources. It's time to move on to CompTIA's 7-step troubleshooting methodology. Of course, we're going to begin with step 1, which is identify the problem. Gather information. What is actually occurring or not occurring? Is the problem extremely local, as in relegated to your network? Or is the problem occurring in an area that is out of your control? Identify the systems. Remember, the symptoms are not the problem. They just point toward the underlying issue. Most often, when the trouble ticket comes in, it will have some of the symptoms, but it will not have identified the actual problem. Approach multiple problems individually. Handle them one at a time. Question the users. This needs to be done both politely and firmly. Many problems that are reported within a network are the result of the end user needing to be educated or re-educated in proper procedures. At the same time, you also need to remember that most end users don't have your level of technical knowledge. So be patient, but don't patronize. And finally, when identifying the problem, determine if anything has changed. This also requires a systematic approach, so be very thorough. Step 2 is to establish a theory of probable cause. Make a list of all of the possible causes of the problem. To develop this list of possible causes, you should consider multiple approaches to the problem, from bottom to top and then from top to bottom of the OSI model. That is a great way to approach the problem from multiple directions. Divide your list of possible causes into 3 ranked sections. They should be not likely, likely, and most likely. This will provide a great place to start. When establishing your theory of probable cause, remember to question the obvious. If the network printer doesn't work, check to be sure that it is turned on. The third step is to test the theory of probable cause. If the theory is confirmed, move on to the next step. If the theory is proven to be incorrect, then reestablish a new theory of probable cause. If you run out of probable causes or the situation worsens, it may be time to escalate the issue up the troubleshooting chain. Once you've confirmed your theory of probable cause, it's on to step 4. Establish a plan of action and identify potential effects. Simple problems may require a simple plan, as in if the network printer doesn't work and the probable cause is that it's not turned on, turn on the network printer. More complex problems will require more complex plans. In some cases, it is a good idea to write the plan out step by step in order to determine the best course of action and to identify any possible repercussions that the resolution to the problem may introduce into the network. Step 5 is to implement the plan or to escalate the problem. If you have the authority, put your plan into action. If you don't have the authority, escalate the problem up the troubleshooting chain, including all facts and determinations when you're escalating the problem. Don't make that next level above you have to recreate everything that you've done. Once you've implemented your plan, it's on to step 6. Verify full system functionality. Don't just verify that the original problem has gone away, because sometimes a fix will introduce a new issue into the system. If a new issue has occurred, it's time to go back to step 1 or to escalate the problem. If you have verified full system functionality, this is where you implement preventative measures to keep this problem from reoccurring. And finally, step 7. Document findings, actions, and outcomes. Document everything. This will save time if and when the problem reoccurs. Your documentation may lead to new best practices for your organization. It's important to document your missteps as well. It will keep the next technician from making those same missteps that you have made. And this will help to improve your chances of becoming the network support technician rock star in your organization. That concludes this session on network troubleshooting methodology. I talked about the importance of a methodology, and then I covered CompTIA's 7-step troubleshooting methodology. Hello, I'm Brian Farrell, and welcome to PACE IT's session on troubleshooting connectivity with utilities. Today I'm going to talk about connectivity utilities defined, then I'm going to move on to connectivity utilities explained, and we will conclude with some additional software for troubleshooting connectivity. There's a fair amount of ground to cover. Let's go ahead and begin this session. Of course, I'm going to begin with connectivity utilities defined. Before we can define the utilities, we need to define connectivity. Connectivity is a program or device's ability to connect or link to other programs or devices. A connectivity utility is a utility or application that is used to establish connectivity and or to diagnose or fix a connectivity issue. With that out of the way, let's move on to connectivity utilities explained. All modern operating systems come with pre-packaged connectivity utilities designed to diagnose and or to repair connectivity issues. In some cases, you can use these utilities or programs from a graphical user interface or GUI. However, in all cases, you can use the following applications from the command prompt. First up is ping. It is a simple utility that is used to determine if there's connectivity between two nodes or two endpoints. It uses ICMP echo requests. There are two basic formats to the ping utility. You can ping an IP address, or you can ping the host name or the fully qualified domain name. You can use ping 6 or ping -6, and you will ping only IPv6 hosts. Then there is tracert or traceroute. It is a utility that is used to determine the path used between two nodes. Tracert, T-R-A-C-E-R-T, is the Windows version, and Traceroute, T-R-A-C-E-R-O-U-T-E, is the Linux, Unix, or OS X version of the command. It also uses ICMP echo requests, but it uses it with an incrementing time to live field to form queries and get responses. Each time the ICMP echo request is sent out, the TTL field is incremented by 1. And Tracert is used to determine how many routers are between 2 points. It can be of limited value though, as many routers have ICMP disabled. It uses the same basic format as ping. Then there is PathPing. It is a network connectivity utility that has been supplied in Microsoft operating systems since the introduction of NT. PathPing builds upon the functionality of ping by combining it with Tracert. When the application is used, it will, in effect, perform a Tracert command, defining the path to the end node, and then it will perform a ping test on each hop. One disadvantage to PathPing is that it requires 25 seconds per hop to show the ping results, and it uses the same command format as ping and Tracert. One of my favorite utilities is ipconfig or ifconfig. ipconfig is the Windows version and ifconfig is the Linux, Unix, OS X version. It's used to determine the IP configuration of a given node. It can also be used to change that IP configuration if used correctly. When using to diagnose connectivity, look for incorrect IP addresses, incorrect subnet masks, incorrect DNS addresses, and/or an incorrect default gateway. Then there's ARP, which stands for Address Resolution Protocol. ARP is used to correlate IP addresses to MAC address. This utility can help to determine when there is an issue with an address resolution protocol table on a given node. Then we have NSLookup. That stands for Name Server Lookup. It's supported by all major operating systems, and it's used to diagnose domain naming system issues or DNS issues. It can be very helpful in determining if a DNS server is having a problem. DIG is similar to NSLookup, but it is specific to Unix, Linux, and OS X. It does use different switch modifiers and returns slightly different results. There is the route utility. This is a Windows-specific command. It's used to view and modify the routing tables on a Windows operating system node. Next up is NBT-STAT, which stands for NetBIOS over TCP Statistics. Windows implements the NBT protocol for backwards compatibility. As a result, the NBT-STAT utility is used if a NetBIOS issue is suspected. Then there's NetStat, which stands for Network Statistics. It's a utility that is used to display protocol statistics and current TCP/IP network connections. It's useful for determining if a connection has been made and the status of that connection. It's time to move on to some additional software. First up are throughput testers. They're used to determine the data flow or bandwidth of a network. They can be used internally to test the flow or bandwidth within a local area network, or they can be used externally to test the flow of a WAN connection. They are often used to create a baseline of network performance. And last up, we have protocol analyzers. These are often called packet sniffers. They examine network behavior on a very basic level, at the packet level. They can examine all the packets coming into and out of an interface. Protocol analyzers are useful to see what is consuming network resources, as in they can tell if a broadcast storm is occurring or if an interface is going bad. Wireshark is a common protocol analyzer that is often used, and it's free. That concludes this session on troubleshooting connectivities with utilities. The first topic was connectivity utilities defined, then we moved on to connectivity utilities explained, and we concluded with a brief discussion on some additional software. Hello, I'm Brian Farrell, and welcome to PACE IT's session on troubleshooting connectivity with hardware. Today I'm going to discuss what makes a cable bad, cable testing tools, and I'm going to conclude with some additional tools. I have a fair amount of ground to cover, so let's go ahead and begin this session. We will begin with what makes a cable bad. Network cables can go bad or be bad without any visible indication. Alternatively, a cable may be inappropriate for a particular application. It can be difficult to visually tell if cables are wired correctly and/or a break in the wire may not be visible. Both of these will cause problems. Additionally, anything that makes the cable fall out of specification will make it a bad cable. How long is the cable? Is it over the maximum length? Is the cable rated for the amount of data being run over the wire? All of these are questions that can be answered using the proper tools. It's time to discuss cable testing tools. First up is the multimeter. It can be used to test for breaks in copper wiring. Good network cables have a very low resistance value from one end of the cable to the other. By the way, your resistance is measured in ohms. A high or infinite ohms value indicates a break in the cable. So you can use multimeters to test for continuity to make sure that traffic can flow from one end to the other. Crimpers are not a testing tool per se, but they are used for attaching cable ends onto cables, which if you suspect you have a bad cable end or a miswired connector, you're going to need a set of crimpers. It can either be specific to a particular type of cable end, or it may work for more than one type of cable. And by the way, it's not uncommon to need to replace the ends of twisted pair wiring cables. Every network technician should have a cable tester or cable certifier. These can be either fairly simple or very complex. Cable testers will test for continuity in the wire, as in, is there a break? Cable testers will also test for proper pinouts. Are all the wires in the right places? Some will test for the wiring standard. Is it wired for the T568A standard or the T568B standard, or have you created a crossover cable? Cable certifiers are a little bit more complex, but they will also test for more network-related items. They can test the speed of the wire. They can test for duplex settings between two endpoints. Cable certifiers are used to certify a given network segment. Toner probes are another handy tool. They are usually a two-piece set. They have an injector which places a signal onto the wire and a probe which detects the signal and emits a tone when it detects that signal. These are also sometimes called a fox and hound. They're used to find and trace wires. They're useful when having to replace a single wire in a bundle of wires. You can place the injector on one end to figure out which wire it is at the other end. Then there is the time domain reflectometer. This is a cable tester or certifier that can also determine the length of a segment. They can also tell where a break is in a segment, which can then allow you to put in a splice. They are more expensive than a standard cable tester or certifier. Related to the TDR is the optical time domain reflectometer, or the OTDR. They perform the same function as a TDR, but it is used for fiber optic cabling. It is often called a light meter, as it can measure the quantity and quality of the light going through a fiber optic cable. Some other thoughts on cable testing tools. Unless your job entails mostly installing cabling, the most important tools are the cable tester, crimper, and toner probes. Personally, I have never been able to justify the cost of a TDR. I have used them, but I've rented them instead of purchased them. Most of the time, you can make do with inexpensive tools. However, spending more on certain tools will usually save time and money in the long run. An exception to the inexpensive tool rule are toner probes. Inexpensive toner probes can be difficult to work with, or they just don't work at all. I would recommend stepping up and spending a little bit more for your toner probe. Try to strike a balance between cost and effectiveness. You can spend thousands of dollars on some of these tools, especially TDRs and OTDRs, and never utilize them to their fullest potential. The next topic is additional tools. And we will begin with the wireless analyzer. It is a similar tool to the protocol analyzer, but it is used for wireless networks. It sniffs out packets on wireless networks. This information can be used to help solve wireless connectivity issues. A wireless analyzer can also perform other functions. It can check for bandwidth usage, channel usage, top talkers, and top listeners. It can identify networks by passively scanning the radio frequency channels. It can identify hidden networks if given enough time, and a wireless analyzer can also infer non-beaconing networks based on data traffic, so it can help you to find those rogue access points. Then there are looking glass sites, or LG sites. These are publicly available sites that can be used to view routing information remotely, as viewed from the LG server's point of view. They create a read-only portal on which routing statistics can be generated and viewed. LG sites can be helpful in determining if the connectivity issue is occurring because of problems on the local network or if the remote connection is the issue. That concludes this session on troubleshooting connectivity with hardware. I talked about what makes a cable bad, I talked about cable testing tools, and I concluded with some additional tools. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Troubleshooting Wireless Networks, Part 1. Today I'm going to be talking about configuration issues, and then we will conclude with some other issues. There's a fair amount of information to go over, so let's go ahead and begin this session. I will begin by talking about some common configuration issues. While wireless networks are a huge convenience to users, they do introduce a new set of troubleshooting issues into the network. Not only do the standard issues that crop up in a wired network need to be considered, the added layer of complexity that adding a wireless access point brings to the table will also need to be considered. When wireless networking is brought into the mix, a very solid troubleshooting methodology becomes just that much more critical. Now on to the actual configuration issues. First up is the Service Set Identifier configuration, or the SSID configuration. When this is an issue, the major symptom is that the user is unable to connect to the wireless network, and the probable cause is an SSID mismatch. The corrective measure is to check that the SSIDs match exactly. Remember, they are case sensitive. Then there is encryption configurations. It has the same symptom as the SSID misconfiguration. The user is unable to connect to the wireless network. Probable cause is an encryption type mismatch or incorrect security key. The possible corrective measure is to check the encryption settings on the wireless access point and on the device to make sure they are the same. Another configuration issue that can cause problems is an incorrect channel or overlapping wireless channels. The symptom is that the user is unable to connect or the wireless network has very poor performance. The probable cause is either incorrect channels or the overlapping channels is causing the signal-to-noise ratio to be reduced. That's the SNR. The possible corrective measure include adjusting the WAP settings and device settings so that they're using the same channel. Hint, there are only 3 available non-overlapping channels on the 2.4 gigahertz radio frequency. Then there are incompatibilities. And the symptom is, again, the user is not able to connect to the wireless network. The probable cause is you have an 802.11a device being used in an environment in which it won't work, as in you're using 802.11g or n. Or there is a frequency mismatch between the wireless access point and the devices. The possible corrective measure is to make sure you're using equipment with compatible wireless standards. Untested updates can also cause a configuration issue. The symptom again is the user is unable to connect or there is poor performance. The probable cause is a conflict between the update and other configuration settings or the wireless network settings. The possible corrective measure is to roll back the system to the prior configuration. Here's another hint. It is a best practice to make a backup copy of a system before installing any updates. Let's move on to other wireless issues. Troubleshooting networks requires a combination of art and science. Some of the best tools in your arsenal will be patience and strategic thinking. Network issues can express themselves in a multitude of ways. One of the best things that you, as a technician, can do is to see if you can recreate the problem. An issue that can be recreated can usually be resolved easily. Also remember that the users you are dealing with are the reason that you have a paycheck. Treat them as you would like to be treated, even if it is the 10th time that you've reminded Bob that his username and password are case sensitive. Interference is a common issue on wireless networks. The symptoms include slow performance and/or intermittent drops. The probable causes can include overlapping channels, walls, or other equipment that operates in the same frequencies. Some possible corrective measures include changing the RF channel or frequency or adjusting the wireless access point placement. Then there's poor signal strength. The symptoms include slow performance and/or intermittent drops, especially towards the end of your wireless network coverage area. Probable causes include low RF power settings, antenna type, and/or the placement of the access point. Possible corrective measures include changing the RF power setting, as in increasing it, or adjusting the antenna and/or WAP placement. There is a caution here. Increasing your radio frequency power or adjusting the equipment placement may cause the signal to go where it was not intended to go. So if you do either of those, you need to check and make sure that you're not putting your signal where you don't want it to be. Bandwidth or device saturation can also become an issue. The symptoms include slow performance and/or intermittent drops. The probable cause is that there are too many users or applications for the available bandwidth. Possible corrective measures include increasing the number of wireless access points and/or changing to a wireless standard with more throughput. The wrong antenna type may also become an issue. The symptoms include low or no signal in an area or signal in an area where it is not supposed to be. The probable cause is the wrong antenna type for the coverage. The corrective measure would be to change to an antenna type to suit the required coverage. Then there is signal bounce. The symptom is poor performance in unexpected locations or an unexpected wireless network signal in an area that was not intended to be covered. The probable cause is the RF signal bouncing off of a hard object. The possible corrective measure would be to adjust the wireless access point placement. That concludes this session on troubleshooting wireless networks, Part 1. I talked about configuration issues, and then I moved on to some other wireless network issues. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Troubleshooting Wireless Networks, Part 2. Today I'm going to be discussing wireless environmental factors, and then we're going to conclude with wireless standard-related factors. There's a whole lot of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about wireless environmental factors. When planning and setting up a wireless network, quite often environmental factors that may impact the wireless network are disregarded. It is easy to get distracted by all the moving pieces of the wireless network, as in the SSID configuration, encryption, and which standards to use. Dealing with these often leads to overlooking factors in the environment that may impact the quality of the planned network. To get the most out of a wireless network, these factors need to be taken into consideration as they can have a major impact on the overall quality and performance of the installed network. We don't think about it very often, but building materials can influence wireless networks. A wireless network works by sending and receiving radio frequency waves across a given area. Anything that can interrupt the signal or change the path of the waves can create a problem in the network. This is called signal bounce. The signal may return to the wireless access point out of phase, leading to poor performance or dropped packets. Alternatively, the signal may end up being bounced into areas where coverage was not planned, leading to a security issue or an interference issue with other wireless networks. Some building materials of concern include concrete walls, metal studs, and window films, particularly window tinting with a metallic content. When evaluating environmental factors, it is important to consider more than just the building materials. All hard surfaces have the potential to create an out-of-phase or bounced signal, including office furnishings and file cabinets. Using a wireless analyzer and wireless survey tools during the planning stage of a wireless network will lead to better placement of the wireless equipment, which ultimately leads to a better performing network. Let's move on to some wireless standard related factors. First up is wireless standard compatibility. Not all of the 802.11 standards are compatible with each other. This is partially due to the RF frequencies that are used, and with the most common frequencies being the 2.4 gigahertz or the 5 gigahertz radio frequency band. The problem with compatibility can also be because of the type of modulation that is employed. Modulation is the encoding of information to be placed on a carrier wave, and it's employed to put the signal on the network. The most common forms of modulation are orthogonal frequency division multiplexing, OFDM, and direct sequence spread spectrum, or DSSS. So let's look at a compatibility list for 802.11. 802.11a is not compatible with most other standards. 802.11b is compatible with 802.11g and N. 802.11g is compatible with .11b and .11n. 802.11n is compatible with 802.11b, G, and AC. 802.11ac is compatible with 802.11n. So let's talk about the wireless standards. 802.11b uses the 2.4 gigahertz RF band and DSSS as its form of modulation. It offers up to 11 megabits per second networking with a maximum indoor range of 115 feet and a maximum outdoor range of 460 feet. 802.11a uses the 5 gigahertz RF band and OFDM as its method of modulation. .11a offers up to 54 megabits per second networking with a maximum indoor range of 115 feet and a maximum outdoor range of 390 feet. Then there's 802.11g. It uses the 2.4 gigahertz RF band, and it can use both OFDM and DSSS as its methods of modulation. .11g offers up to 54 megabits per second networking with a maximum indoor range of 125 feet and a maximum outdoor range of 460 feet. Then we have 802.11n. It can use both the 2.4 and the 5 gigahertz radio frequency bands, with OFDM as its method of modulation. 802.11n can offer up to 600 megabits per second networking with a maximum indoor range of 230 feet and a maximum outdoor range of 820 feet. Finally, we have 802.11ac. It uses the 5 gigahertz radio frequency band with OFDM as its method of modulation. It's expected to offer up to 1 gigabits per second networking with a maximum indoor range of 115 feet. At this point in time, we do not have a maximum outdoor range as they're still working on establishing that. That concludes this session on Troubleshooting Wireless Networks Part 2. We talked about some wireless environmental factors, and then we concluded with a brief discussion on wireless standard related factors. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Troubleshooting Copper Wire Networks Part 1. Today I'm going to give you a summary of the troubleshooting methodology, and then we're going to move on to common copper wire problems. With that, let's go ahead and begin this session. I'm going to begin with a summary of the troubleshooting methodology. CompTIA recommends a 7-step troubleshooting methodology. Step 1 is to identify the problem. A mistake in identifying the problem can negate the rest of the steps. And remember, the problem is not the symptom. The problem what is causing the symptom to occur. Step 2, establish a theory of probable cause. Step 3, test the theory of probable cause. Once you have tested the theory of probable cause, move on to step 4, establish a plan of action to resolve the problem. Step 5 is implement the solution or escalate as necessary. Step 6 is to verify full system functionality. And your last step, step 7, is to document findings, actions, and outcomes. And there we have a brief review of the 7-step troubleshooting methodology. With that, let's move on to common copper wire problems. First up is electromagnetic interference, or EMI, and radio frequency interference, or RFI. Because copper wire transmissions are electrical in nature, their electrical signals can degrade by sources of either EMI or RFI. Sources of interference may corrupt the network signal, leading to a loss of communication or poor communication between end nodes. There are several possible sources of EMI and RFI. These include other electrical wires. Network cables should be kept separate from normal electrical runs, and if possible, network cabling should always cross electrical wires at a 90-degree angle. Never run network cables right alongside the normal electrical run, as the probability of interference will greatly increase. EMI and RFI can also be caused by other electrical components. Manufacturing environments often have a lot of EMI and RFI present. Another major source of interference is fluorescent lights. Interference problems can often be identified by when they occur. For instance, does the problem only happen when somebody turns on all the lights? The solution may be to move from UTP to STP or to reroute the network cables to avoid the source of the EMI or RFI. All copper wire networks have distance limitations. And by that, all network transmission media experience attenuation, which is a loss of signal strength over distance. This can lead to poor communication or loss of communication between end nodes. A decibel logarithmic scale is used to measure the amount of acceptable and unacceptable attenuation. As network transmission speeds increase, the attenuation also increases as a ratio of signal to signal loss. Possible attenuation issues can be identified when a cable cannot handle the higher transmission speeds for which it is rated. A cable certifier or TDR will usually identify this problem. Possible solutions are to install a network switch to boost the signal strength or to reroute the network run to create a shorter run of cable. Then there's crosstalk. Even with the steps taken to reduce it, all cables experience crosstalk between the pairs, which can lead to intermittent or constant transmission issues. More crosstalk is present at the near end, where the transmissions originate, than at the far end, where the transmissions are received. As network transmission speeds increase, the opportunity for crosstalk increases. A good cable certifier or TDR will identify the problem. Possible solutions include replacing the network run with cable rated for a higher transmission speed, replacing the cables with one that has better shielding, or reducing the transmission rate of the network. Bad connectors are also a common problem on copper wire networks. Once a good cable is in use, the end connector may still become broken, especially after repeated use, leading to a loss in connectivity. In particular, this can happen on RJ45s. The locking tab can be easily broken, leading to a loose connection or creating an open connection. A cable tester may identify this problem as an open connection, but a thorough inspection of the cable ends can help to identify the problem. The solution is to replace the bad connector with a good one with your crimper. Then there are bad cables. Cables can go bad, especially if they are in places susceptible to damage, leading to loss in connectivity or poor network communication. A cable tester can be used to identify the problem as either an open connection or a short. An open connection indicates a broken wire. A short indicates an electrical signal traveling down an unintended path, as in down the wrong wire. The solution is to replace the bad network cable. That concludes this session on troubleshooting copper wire networks, Part 1. I did a summary of the troubleshooting methodology, and then I concluded with some common copper wire problems. Good day, I'm Brian Farrell, and welcome to PACE IT's session on troubleshooting copper wire networks, Part 2. Today we're going to be talking about what constitutes a bad cable, and then we will conclude with some common copper wire problems. With that, let's go ahead and get into today's session. I'm going to begin with what constitutes a bad cable. Network cables can go bad or be bad without any visible indication. Additionally, a cable may be inappropriate for a particular application. Anything that makes a cable fall outside of specifications will make it a bad cable. How long is the cable? Is the cable over its maximum run length? Is the cable rated for the amount of data being run over the wire? All of these plus more can constitute a bad cable. By using the proper tools and methodology, a bad cable can be identified and any problems associated with the bad cable can be rectified. Let's talk about copper wire termination standards. They are currently established by the TIA-EIA, that is the Telecommunications Industry Association Electronic Industry Alliance. They have established a set of termination standards for twisted pair copper wire. The standards ensure that network transmission is consistent across networks. The standards involve how the pairs of wires are ordered when placed in the termination device, which is usually either an RJ45 or a punchdown block. The current standards are the T568B and the T568A standard. The pinout for the T568B standard is white orange orange, white green blue, white blue green, white brown brown. On the other hand, the pinout standard for the T568A standard is white green green, white orange blue, white blue orange, white brown brown. Not following the standards may lead to network problems. Cable testers and certifiers can be used to determine if a twisted pair copper wire network cable meets the standards. We're going to begin with twisted pair termination standards. A straight-through cable is used to connect different types of devices, e.g. a computer to a switch or a switch to a router. Both ends of the cables are terminated to the same standard. Alternatively, there's a crossover cable. A crossover cable is used to connect similar types of devices, as in a computer to a computer or a switch to a switch. One end will be terminated to the T568A standard and the other end will be terminated to the T568B standard. A problem can arise when you have mismatched cabling standards. Using the wrong type of cable, as in using a straight-through cable when a crossover cable is specified, can lead to network problems. Many IT devices use a process called auto-MDI, MDI-X, in which they can auto-sense the type of device on the other end of the cable and electronically change their send-receive setup to match the cable used. But reliance on this may contribute to the problem. Cable testers can be used to help identify the problem in a mismatched cable standard. When creating your own cables, you may end up with split pairs. The problem occurs during the termination process. At least two pairs of wires that should be grouped together in the termination device get separated. The problem may not be identified with the most basic of cable testers. They will still test as having continuity from end to end. If the split pairs are due to a misunderstanding of the termination standards, it may still test as a straight-through or crossover cable. This often leads to a crosstalk issue. A good cable certifier will always identify the problem. Then there's the TX-RX reverse, or the transmit-receive reverse problem. A PC-type device always uses pins 1 and 2 as one pair of wires to transmit a signal, and pins 3 and 6, another pair of wires, to receive a signal. The receiving device must be configured to either receive on pins 1 and 2 and transmit on pins 3 and 6, or the proper cable must be used, like a crossover cable. If not, the link will not be created. That is a TX-RX reverse. If the link fails to be created, check the pinout on the cables to ensure that a TX-RX reverse has not occurred. Now that concludes this session on troubleshooting copper wire networks Part 2. Today I discussed what constitutes a bad cable, and I concluded with a couple of common copper wire problems. Hello, I'm Brian Farrell, and welcome to PACE IT's session on troubleshooting fiber cable networks. Today we're going to be talking about using the specific tool for the job, and then we will conclude with some common fiber cable problems. There's a fair amount of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about using the specific tool for the job. The nature of fiber optic networks makes troubleshooting them a little more expensive than other types of networks. The reason for this is that the best, and sometimes only, tool that can be used for troubleshooting fiber optic cable problems is the optical time domain reflectometer, or the OTDR. Using the specific tool for the job at hand will ease the burden of diagnosing and resolving any network issues. While an OTDR costs thousands of dollars, or in some cases tens of thousands of dollars, in many cases it can quickly diagnose the problem. A quick diagnosis can lead to a quick solution, often saving significantly more than the cost of the tool by preventing lost productivity and/or revenue. That is why we spend money on OTDRs. So let's talk about some common fiber cable problems. We're going to begin by talking about attenuation or decibel loss. All network transmissions degrade over distance. This is called attenuation or decibel loss. This loss of signal strength can lead to slower speeds, loss or corruption of network traffic, or the loss of the network communication link. The OTDR can not only diagnose attenuation, but it can also help in the placement of a repeater station. Then there's broken fiber optic cables. As with all types of cable media, fiber optic cables are subject to breakage. As a matter of fact, in some cases they are more delicate than other types of media. Certain types of fiber cable can span many kilometers, making it difficult to determine where a break has occurred. The OTDR can be used to determine where a break in the fiber optic cable has occurred, allowing the technician to insert a splice at that point. A common cause of breaks in fiber optic cable is exceeding the bend radius limitations of the cable. Due to the construction of fiber optic cables, it is subject to breakage if it is bent beyond a certain point. It is possible for small form factor pluggable transceivers or for gigabit interface converter transceivers to go bad. The SPF and GBIC transceivers are hot swappable, replaceable modules that are used to add gigabit capabilities to switches, routers, and other networking equipment. A bad transceiver will prevent communication from occurring. An OTDR can be used to help diagnose a bad SPF or GBIC module. It is possible to have a fiber type mismatch. Single mode fiber and multi-mode fiber use different methods for placing the signal on the optic fiber. If a mismatch occurs, the most common problem is that it will be impossible to make a network connection. This is also referred to as a wavelength mismatch, as the wavelength or color of the light being used is different between the modes of fiber transceivers. The OTDR can be used to determine the types of transceivers that are being used. There are some other fiber optic cable issues that can arise. Anything that can interrupt the flow of light from transceiver to transceiver will create a problem. Dirt or smudges on the connectors may cause an issue with fiber optic cable transmissions. When this is suspected, using a soft polishing cloth to clean the ends of the cable will solve the problem. There is a caution: never look directly into the ends of connected fiber optic cable. If you do so, you run the risk of damaging your eyes. Connectors are also specific to the mode of transmission, as in SMF or MMF. Connecting the wrong type of connector to a cable will prevent proper communication from occurring. Also check to make sure that the proper connectors are being used with the proper type of fiber optic cables. Worn or broken connectors will create an air gap, which will create a network transmission problem. Always inspect the connectors for their condition before use. An OTDR can be used to determine where the loss of signal is occurring, even if it is at the connector. That concludes this session on troubleshooting fiber cable networks. We talked about using the specific tool for the job, and then we concluded with common fiber cable problems. Good day, I'm Brian Farrell, and welcome to PACE IT's session on troubleshooting common network issues. Today we're going to talk about problems that should be escalated, and then we will conclude with problems that you should resolve. There's a fair amount of ground to cover, so let's go ahead and begin this session. We're going to begin by talking about problems that an entry-level network technician should escalate. The complexity of modern networking has made using a solid troubleshooting methodology a necessity, not an option. Networks can express problems and issues in many ways. This can lead to much frustration on the part of the network users and the technicians responsible for fixing problems. If such problems are not resolved quickly, they can lead to loss of revenue and productivity for an organization. There are a number of problems that should be escalated up the troubleshooting chain as soon as they're discovered in order for them to be resolved in the most expedient manner. The first of those problems is the switching loop. Users complain that the network works fine for a while and then goes down, and then works fine for a while and then goes down. This indicates a spanning tree protocol convergence issue or a switching loop. In either case, this is beyond the entry-level technician's capabilities and should be escalated as soon as possible. Then there's the broadcast storm. A failing NIC or application may cause a situation in which a broadcast storm is created. The NIC goes down, then comes back up, then goes back down, and it does this repeatedly. This is often referred to as a flapping NIC. Each time it comes up, it sends out a broadcast advertising its status, which creates traffic congestion. An application can do the same thing. In either case, escalate this up your support chain as soon as it's discovered. Similar to the switching loop is the routing loop, but it involves the routing process. This is more likely to occur when older routing protocols are used, but may also occur due to a misconfiguration of routers, as in there are multiple static routes to the same location. Often switching to a newer routing protocol like OSPF will resolve or banish routing loops, but this needs to occur farther up the support chain. There are other routing problems that, once discovered, should be moved up the chain. Routing problems can manifest themselves in many different ways, including missing IP routes, failure to discover neighboring devices, or failure to connect to neighboring devices once they're discovered. When routing problems are suspected, it is necessary to escalate the issue to the proper technical team. One problem that can be difficult to diagnose is the mismatched maximum transmission unit, or MTU. This is often called an MTU black hole. Different types of WAN connections have different MTU settings. That is, the largest allowable size of a packet that can traverse a link or be accepted by the link. The MTU for Ethernet, by the way, is 1500 bytes. Routers will negotiate the MTU between links using ICMP, that's Internet Control Message Protocol. If ICMP has been disabled on the router, which is a common practice, when a router receives a packet that exceeds the MTU, it will not respond and it will drop the packet. The sending router continues to send the oversized packets into the MTU black hole, never getting a response back that the packets are too big. So the data is flowing, but it's not going anywhere. When suspected, this too should be moved up the support chain to the correct technical team. NIC teaming can also create a problem. This is the process of bonding multiple network interface controllers on a single system for the purpose of increasing bandwidth or for failover purposes. A misconfiguration may actually cause a loss of performance or, in a worst case scenario, the total loss of functionality. If you're dealing with teamed NICs, move it up the support chain. Then there are power failure or power anomalies. Power failures are easy to diagnose but may be difficult to recover from. While battery backups and generators may mitigate the issue, they will not resolve the problem. If the problem occurs within the building, contact the appropriate group responsible for building maintenance. If the problem occurs outside the building, contact the appropriate utility. Electronic devices are sensitive to power issues. Anomalies in the quality of the electricity delivered to the device may cause problems. Using battery backups or uninterruptible power supplies with power conditioners will help to mitigate power anomalies. With problems to escalate covered, let's move on to problems that you can resolve. We will begin with incorrect IP configurations. Under incorrect IP configurations, we will begin with the default gateway. The default gateway is the local network or computer's access to outside networks. An incorrect gateway will keep traffic from reaching its destination. If it's suspected, verify what the correct gateway settings should be and correct it. Then there are duplicate IP addresses. When duplicate IP addresses have been configured, the first device booted up will get the address, and the second one that gets booted up will get an address supplied by a PIPA. This can occur when DHCP address reservations have not been configured correctly. This is easy to verify and correct and should be done when an ePIPA address is received by a device. There are other DHCP misconfigurations that can occur. The problem is expressed in a similar manner as the duplicate IP address problem, as in an ePIPA address is supplied, and is caused by a misconfigured DHCP server. Again, verify your DHCP settings and correct. Then there are DNS misconfigurations. Users complain that they cannot get to resources or destinations on the network when using the host name. DNS is used to resolve host names to IP addresses, so a misconfiguration will prevent the function of the DNS process. Verify the correct DNS settings and correct as needed. It's also possible to have incorrect VLAN assignments or incorrect virtual local area network assignments. Users will complain that they cannot get to necessary network resources. This tends to be a single host issue or to involve a small group of hosts. Verify the VLAN settings and again, correct as necessary. Incorrect interface configurations will also create network issues. Users may complain of poor network performance or not being able to connect to resources at all. This issue tends to affect a whole network segment. Configuration issues could include mismatched port speeds and/or duplex settings on the interfaces. Verify the correct interface configurations and correct the settings. Simultaneous wireless and wired connections will also create some networking issues. Many laptops come with wireless and wired network capabilities built into them. It is possible for a laptop to attempt to use both at the same time. This may cause the device to quit communicating on the network as a whole. Reminding users to turn off wireless capabilities before joining the wired network will resolve this problem. Not having good end-to-end connectivity is another common problem. The complexity of networks will just about guarantee that end-to-end connectivity, the ability to reach remote hosts, will be lost at some point. The ping and tracer utilities can be used to find where the break in communication occurs. This information can then be used to determine the next course of action. Last up is hardware failure. Networking equipment and devices will fail. When this happens, it is usually denoted by the sudden loss or intermittent loss of networking functions or access. The key to resolving this issue is in determining what has failed and replacing it. That concludes this session on troubleshooting common network issues. I began by talking about problems that should be escalated, and then I concluded with problems that should be resolved. Good day, I'm Brian Farrell, and welcome to PACE IT's session on common network security issues. Today I'm going to be discussing security issues caused by misconfiguration, and then I will conclude on other network security issues. With that, let's go ahead and begin this session. Of course, I'm going to begin by talking about security issues caused by misconfigurations. It's easy to assume that a network is secured from threats, while in reality it may be very vulnerable. A network may actually be vulnerable because of a misconfigured security setting or because of a common practice within an organization. A network may not be as secure as you think due to the ever-changing threat landscape. Nefarious hackers are continually seeking new exploits that they can use to breach network security, including possible misconfigurations in network security settings. These security settings may have been correct at the time that they were set up, but due to the changing landscape, they may be considered a misconfiguration now. A misconfigured firewall and/or access control list may cause a security issue. These can result in 3 different categories of security issues. Traffic that should be blocked isn't, allowing threats in. Traffic that shouldn't be blocked is, This can prevent the receiving of vital updates, or all traffic is blocked. This isn't necessarily a security issue per se, but it is still a misconfiguration. And it is possible for a junior network administrator to just remove the access control list or firewall to allow the traffic to start flowing again, which is a security issue. To protect against a misconfigured firewall or ACL, thoroughly test them before putting them into action. A misconfigured application may become a security threat. A web application that does not perform proper validation of input may lead to a buffer overflow attack. This may lead to a successful attack on the web server on which it is hosted. Thoroughly testing applications before placing them into service will mitigate the threat. Unpatched operating system or firmware will become a major security issue quickly. The manufacturer of operating systems and hardware firmware will often produce security patches or fixes for vulnerabilities as they become known. An unpatched OS or firmware becomes very vulnerable in short order and may become a threat to the network. Most software makers have an updating service. Subscribing to that service will help to mitigate the threat. Open TCP IP ports are a security issue. Open ports on networks are listening for requests for or by services, applications, or protocols. All open ports are a security vulnerability, and there are 65,535 possible ports that may be open. A best practice for network security is to specifically close all unnecessary ports to harden a network. The TACACS Plus and Radius services are often used to authenticate devices and users on networks. A misconfiguration on either may lead to a security issue that allows malicious users to be authenticated to use network resources. Thoroughly reviewing the configuration of authentication services will help to mitigate the problem. In addition, all default local accounts should be disabled. These default local accounts may present a slight opening for a malicious user to exploit authentication services. Active default usernames and passwords are an issue. Almost all devices and applications come with default usernames and passwords to ease the setup process. If left active, these defaults create a security issue, as they tend to be well known or are easy to find through simple research. A best practice is to disable all default usernames and passwords after setting up the device or application. It's time to move on to other network security issues. First up are malicious users. Malicious users may be the single biggest security issue facing any network, and they will fall into one of two categories. There is the untrusted malicious user. This is an outside entity that has exploited a security weakness to gain access to network resources, as in a hacker who has breached a database's security features to gain access to valuable information. Even worse than the untrusted malicious user is a trusted malicious user. This is a person or entity that has been explicitly granted access to network resources that then exploits this trusted position for malicious purposes. And they are harder to guard against because you've already granted them access inside of your defenses. A best practice is to review log files on a regular basis to see what resources are being accessed and by whom to help maintain security. Packet sniffers are also a security issue. Packet sniffers examine network traffic at a very basic level and can be used to help in the administration of a network. But packet sniffers may also be used by malicious users to see what protocols and activities are allowed on the network. This may help them in further attacking the network. Then there is malware. It is usually defined as malicious software that has the intent of causing harm. As a category, malware covers any code-based threat to a network or system. Examples of malware include viruses, trojans, and spyware. To protect against malware, anti-malware applications should be running on every device. To be proactive, end-user education should also be in place to teach them to recognize the dangers that malware presents. The Internet Control Messaging Protocol itself may become a security issue. ICMP can be a valuable tool for diagnosing issues on networks, but it can also become a security vulnerability. ICMP can be exploited in a denial-of-service type of attack. ICMP can also be used to redirect legitimate users to a new malicious default gateway, possibly resulting in loss of data or sensitive information. It is now a best practice to deny ICMP requests on a router's outward-facing interface. Denial of service or distributed denial of service attacks are becoming more common. In an attempt to bring down a network or website, malicious users will often send thousands or hundreds of thousands of requests for service. The attacker's goal is to make that resource unreachable by legitimate users. Many modern firewalls and other network appliances have been configured to recognize the signature of such an attack and can take steps to mitigate the results. When creating applications, developers often create backdoors into the programs. Backdoors are a method of accessing an application or service while bypassing the normal authentication process. Unfortunately, these backdoors are sometimes left open after the development process has been completed. Once these become known, they can be exploited. In most cases, the application is listening on a specific port for a request for access. The best mitigation technique is to close all unnecessary ports on a network. Kind of sounds familiar, doesn't it? Then there's jamming. All wireless networks use radio frequency channels to transmit data on the network. It is possible to create enough interference on the RF channel that it is no longer usable on the network. An attacker will often use jamming when performing a denial-of-service type attack. However, it can also be used to perform an evil twin type attack. By jamming the legitimate channel, the attacker is hoping that users will switch to the channel that the rogue access point is transmitting on. Many of the modern networking standards and devices employ techniques to mitigate the threat of jamming, as in both 802.11n and 802.11ac are difficult to jam standards. Then there is banner grabbing. Many network devices display banners when users are signing into or requesting services from network devices. These banners can impart information about the type of device or the type of service that is being requested. This information may be used by a hacker to research possible exploits. The best practice is to disable all unnecessary services and banners on network devices. That concludes this session on common network security issues. I began by talking about security issues caused by misconfiguration, and then I concluded with other network security issues. Good day, I'm Brian Farrell, and welcome to PACE IT's session on common WAN components and issues. Today I'm going to be talking about common wide area network components, and then we're going to move on to common WAN issues. There's a fair amount of ground to cover, not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about common WAN components. First up are copper line drivers or repeaters. These are used to allow network traffic to go farther distances over copper wire type networks. They take an incoming signal and regenerate it, boosting the strength of that signal, and then they send it back out, thus reducing attenuation. Common to all WANs is the demarc. Demarc stands for the demarcation point. This is the physical point where the telecommunication company's responsibility ends and the customer's begins. The telco takes care of the upstream end of the network, and the customer takes care of the downstream end of the network. The DMARC may be simple or it may be very complex, depending upon the size of the organization and the required services. Then there is the Network Interface Unit, or the NIU. In the SOHO environment, the NIU is usually the DMARC. Also in the SOHO environment, the NIU is usually provided by the Internet Service Provider, or ISP. An NIU can be a cable modem, a DSL modem, or another piece of hardware that connects the customer to the ISP. One type of NIU is the Smart Jack. It's an NIU that can provide feedback on conditions to the ISP. Smart Jacks help the ISP determine if a problem exists on its end of the DMARC through the use of remote loopback capabilities. Many Smart Jacks can also provide translation between protocols, as in translating a serial PPP communication stream into Ethernet. More than likely on larger networks, you will find CSU DSUs. That's Channel Service Unit, Digital Service Units. This is the interface point that provides the connection between a point-to-point line and the device that is directing network traffic, which is usually a router. The CSU DSU may be an external device, or it may be a removable module inside of a router. Only two CSU DSUs may exist on a single point-to-point line, one at either end of the connection. With the common components covered, let's move on to common wide area network issues. First up is a loss of internet connectivity. Many factors can lead to a loss of connectivity on both sides of the DMARC. Before contacting the WAN provider, check the local area network equipment for its operation. If the issue is not to be found on the LAN side, then contact the wide area network provider. One of the tests that the WAN provider will conduct is a loopback test to check its line for interference. DNS issues are also common in a WAN environment. They may look like a loss of internet connectivity, but it isn't. The users may complain that they cannot connect to an outside source like www.google.com, but it may not actually be a connectivity issue, but a DNS issue. If using a local DNS server, verify the settings and make corrections accordingly. If the network is using the WAN provider's DNS settings, attempt to ping the IP address. If that works, there is a WAN connection. If you then use the ping utility with the fully qualified domain name and this fails, then contact the WAN provider to resolve their DNS issue. Interface issues are also common. Errors on a router's WAN interface can indicate several different issues. Monitoring an interface's status and reading the error reports may provide a clue as to the issue. The most common issue that prevents a good connection is a speed or duplex mismatch. A speed mismatch between interfaces will prevent a link from being established. A duplex mismatch between the interfaces will create errors, as in output and input errors. If you're experiencing discards and drop packets, there's a couple of things to consider. If the device is discarding incoming packets, then more than likely the device's CPU is being overutilized. It may be time to upgrade. If the device is dropping outgoing packets, then there is a bandwidth congestion issue, which may be caused by interference on the line. So either you may be trying to move too much network traffic, or there may be an issue on the wide area network provider's side of the line. Router configurations are a common problem when establishing a new WAN connection. A misconfiguration of the WAN interface of a router will lead to, guess what, a WAN connection issue. If this is suspected, verify the proper configuration settings with the WAN provider. Unfortunately, company policy and practices sometimes get reported as a wide area network issue. Some applications may be throttled or have their available bandwidth reduced for quality of service reasons, leading to slow service, which is a perceived wide area network issue. Also, acceptable use policies may restrict or block access to certain sites or types of sites, which may appear to the end user as a WAN issue. There's not much that you as the technician can do to resolve this, but it is up to you to explain it to the end user. A satellite wide area network connection may also become an issue. If a satellite WAN connection is used, latency will increase due to the distances covered by the transmissions. Latency is the measure of time between the sending of data and the receiving of the data. Careful application of quality of service techniques may mitigate the effects of latency on some applications, but you're still going to have more latency with a satellite connection than other types of connections. Split horizon is another issue. Split horizon is a technique used in routing to help prevent routing loops. With split horizon, a router will not advertise a route to another network out of the interface that it learned the route on. With a point-to-multipoint wide area network connection, the router may have difficulty with split horizon. It will learn all of the routes available to it on the same interface, but it can't advertise those routes back out of that interface. Creating logical sub-interfaces on the wide area network interface will usually resolve this problem. The logical sub-interfaces appear to the router as individual interfaces, allowing the router to advertise the routes back out of the WAN interface. That concludes this session on common WAN components and issues. I talked about common WAN components, and then I concluded with some common wide area network issues. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the OSI Networking Reference Model. Today I'm going to begin by talking about a brief history of the reference models, and then I'm going to talk about the network reference models themselves, and then I'm going to conclude with a comparison between OSI and TCP/IP. There's a fair amount of ground to cover, so let's go ahead and begin this session. So let's begin with a brief history. The Open System Interconnection Reference Model is a conceptual model with two major components. The first main component of the OSI networking reference model is an abstract model of networking. It's a 7-layer model. The second major component is a set of specific protocols which allow differing computing systems to communicate with one another despite their different architecture. So why was a networking model required? Well, early networks communicated using proprietary languages. Because of those proprietary languages, early networks could only communicate with like systems. So an IBM network could only communicate with another IBM network. In addition to that, the U.S. government desired a robust computer communication system that could survive disaster. The first networking reference model that was developed was the TCP/IP reference model. The Transmission Control Protocol Internet Protocol reference model was published as the United States Department of Defense standard in 1982. All of the major systems manufacturers adopted the TCP/IP reference model beginning in 1984. AT&T moved the Unix implementation of TCP/IP to open source in 1989, further cementing TCP/IP's place in networking. The OSI reference model came later than the TCP/IP reference model. The OSI model was published in 1983, and it defines the relationships between differing protocols and hardware. It's time to move on to a discussion about the networking reference models in more detail. We're going to begin with the OSI reference model. It is a 7-layer reference model. Layer 1 is also called the physical layer. It standardizes the electrical signals that networks use. It also defines cable standards and how the bits of data are placed on the physical media. Network cables and hubs are part of Layer 1 of the OSI model. Then there's Layer 2, which is also called the data link layer. It's responsible for identifying the individual nodes, both the sending node and the receiving node. It also introduces an error correction method known as the frame check sequence, or FCS. Layer 2 is composed of 2 sublayers. The first of those is the logical link control layer. It is mainly responsible for flow control and error correction. Then there is the media access control layer. It is mainly responsible for node addressing. Switches and bridges are Layer 2 devices. Then there's Layer 3, the network layer. It's responsible for routing functions between networks. It also identifies networks and nodes on the network. Routers are Layer 3 devices. Then there's Layer 4, the transport layer. It's responsible for breaking the data into smaller pieces for the lower layers and for the actual data transport protocols, 2 of which are TCP and UDP. The transport layer may be required to confirm the actual delivery of the data stream, and it may be required to offer error correction. And it does this through the use of TCP, or Transmission Control Protocol. Then there's Layer 5, the session layer. This is the layer that is responsible for establishing the initial parameters between 2 systems. It sets up and tears down the communication channel. Layer 6, or the presentation layer, is responsible for taking data and converting it from a machine-dependent language to a machine-independent language. This is also the layer that has the main responsibility for encryption between networks. And finally, we have Layer 7, the application layer. This is the layer that is responsible for the protocols that request services or functions from other systems. These protocols may not be the actual application. For instance, Internet Explorer is an application that uses HTTP at Layer 7 to request web pages. Now let's talk about the TCP/IP reference model. This is a 4-layer reference model. The lowest layer is the network interface layer, which can also be known as the link layer. It handles electrical signaling, flow control, error detection, and node addressing. Then there's the internet layer. This layer handles routing functions and identifies network systems and nodes on those networks. Then there is the transport layer, which handles breaking the data into more manageable pieces for the lower layers. It is also the layer that is responsible for the delivery method, which can be either reliable or unreliable, and error correction for when reliable delivery is used. And finally, there is the application layer. This layer handles requests for services from applications. It also handles translation to machine-independent languages and encryption. It also sets up and tears down communication sessions between systems. So now let's do a comparison between the OSI and TCP/IP reference models. While TCP/IP is the dominant model, most technicians communicate issues using the OSI model because it is more specific. When a problem occurs, and believe me, they will, it is easier to resolve them with the more highly defined set of specifications of the OSI model versus the specifications of the TCP/IP model. It's easier to resolve an issue at the session layer of the OSI model than it is to track down what went wrong in the application layer of the TCP/IP model. Both the OSI and TCP IP models are reference models only. It is not mandatory that they be followed. Each developer and manufacturer determines its own method of implementing the reference models. While in theory there will never be a problem in communicating between devices and systems, remember, it is only a theory. Now that concludes this session on the OSI networking reference model. I began with a brief history, then I moved on to the networking reference models themselves, and then I did a very brief OSI and TCP IP comparison. Good day, I'm Brian Farrell, and welcome to PACE IT's session on the Transport Layer plus ICMP. Today I'm going to discuss TCP and UDP, and then I'm going to conclude with a brief discussion on ICMP. There's a fair amount of ground to cover, but not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about TCP and UDP. Before I can talk about TCP and UDP, we need to talk about the transport layer. Most networking models follow the Open Systems Interconnection Reference Model, or the OSI model. It is composed of 7 different layers, which include the application, presentation, session, transport, network, data link, and physical layers. The layers work together to create a system of communication that allows for different types of computing systems or networks to communicate with each other. Layer 4, also known as the transport layer, receives data from the session layer, which is layer 5, and determines what method or type of delivery is required for the data. The transport layer then hands that data with the instructions for the method of delivery to layer 3, which is also known as the network layer, which is then responsible for determining where the data is actually going. There are 2 main transport layer protocols. They are TCP and UDP. TCP, or the Transmission Control Protocol, is a protocol that determines the type of delivery method that will be used in network communications. TCP uses a reliable method to deliver network packets. TCP helps to set up the connection session. It helps to establish error control during the communication session, and it helps to tear down the communication session when it's done. Now, TCP does use a reliable delivery method. One of the main ways that it does this is through the use of a 3-way handshake. The first step of this handshake is the request for the connection. The second step is the reception of the response from the other end. The third part of the 3-way handshake is when the requester sends an acknowledgement back that sets the sequence numbers that will be used with every packet that is delivered. Every packet that gets sent must be acknowledged by the receiver. If the sender doesn't receive the acknowledgement of a packet, the sender will then resend that packet. All packets are sent and received in order. They're never out of order, or they should never be out of order. So now let's talk about UDP, or User Datagram Protocol. It's a protocol that determines the type of delivery method that will be used in network communication, just like TCP. Unlike TCP, UDP uses an unreliable method to deliver network packets. It does not help to set up the connection session. It does not establish error control, and it does not help to tear down the communication session. It uses an unreliable delivery method. This could better be described as a best effort delivery method. It sends the data stream to the destination, trusting that the destination is A, listening for the data stream, and B, willing to accept that data stream. The data stream flows with no acknowledgement of it being received. That's how UDP works. Not all communication can be treated the same. That is why there are both reliable and unreliable delivery methods. With TCP, the sender can be assured that the other end of the line has received all of the packets that were sent and that the packets were received in the proper order. This works well for communication that is not sensitive to latency issues that are associated with the overhead of reliable deliveries. UDP strips off the overhead but sacrifices reliability. It is well suited for network communication in which speed is more important than reliability. When using voice over IP, it is more important for the flow of packets to be continuous than for communication to be held up while waiting for packets to arrive in the right order. Voice over IP communication can survive the occasional dropped packet, but it gets very miserable when it has to wait for those packets to arrive. Now let's move on to ICMP. The Internet Control Message Protocol works at layer 3, which is also known as the network layer, of the OSI reference model, and it is used by IP, or the Internet Protocol, to perform several services. As a messaging service for IP, ICMP packets are carried as encapsulated IP datagrams. It provides information about network issues. The ping utility uses ICMP to test for end-to-end connectivity between two devices using ICMP echo request packets. The traceroute utility uses a combination of ICMP echo requests and destination unreachable packets to map the actual route between two endpoints. Also, if a router's memory buffers are full, it will continue to send out ICMP buffer full messages until the congestion has been reduced. This allows the other routers to slow down their transmissions to avoid packet loss. That concludes this session on the transport layer plus ICMP. I began with a brief discussion on TCP and UDP, and I concluded with another brief discussion on ICMP. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Basic Network Concepts Part 1. Today we're going to be talking about encapsulation and modulation. There's a fair amount of ground to cover, so let's go ahead and begin this session. We're going to begin by talking about encapsulation. The Open Systems Interconnection Reference Model, or the OSI model, uses a layered approach to enable disparate devices to be able to communicate effectively. During the communication between two devices or nodes, each layer is only responsible for being understood by the corresponding layer on the other device. As data flows down from the application layer through to the physical layer, it is encapsulated at each layer with information to help the corresponding layer at the other end of the communication line understand what is happening. As the data is received at the other end, it is de-encapsulated or unwrapped as it moves up the OSI stack by the corresponding layer. Let's talk about how encapsulation works. The application layer begins the process by sending data that is encapsulated or wrapped with application layer control information to the presentation layer. The encapsulated data is called a PDU, or Protocol Data Unit. The application layer PDUs are segmented by the presentation layer, with each segment being encapsulated by presentation layer control information. They are now presentation layer PDUs. The process of segmenting and encapsulating continues down through the OSI stack until it is transmitted as bits by the physical layer. The receiving physical layer passes the bits to the receiving data link layer, which reads the data link layer PDU information and then de-encapsulates and desegments it, sending the new packets to the network layer as network layer PDUs. The process of de-encapsulating and desegmenting continues up the OSI stack until it is received by the application layer, where it is finally fully de-encapsulated and fully reassembled. This encapsulation and de-encapsulation allows differing systems to be able to communicate together effectively. With that covered, let's move on to modulation. The physical layer of the OSI stack is responsible for transmitting bits of data across some form of media. So it literally is responsible for transmitting zeros and ones across the media like a cable. The question arises, how does the physical layer transmit the data across the media? The bits of data are modulated or encoded by the physical layer and placed on the carrier signal of the media, which carries the modulated data onto its next destination. The carrier signal can also be referred to as the carrier channel. Once the bits are received, they are demodulated or unencoded by the receiving physical layer. A carrier signal is a standard waveform, usually in the form of a sine wave, that is used as the base carrier of another input signal. A sine wave is a mathematical curve that is represented by a smooth repeating oscillation. Now let's define modulation. Modulation is the process of varying one or more properties of a carrier signal with an input signal, usually for the purposes of conveying information. Modulation can be used to encode digital network traffic onto media that uses a digital carrier signal, as in using an ISDN connection between two networks. Modulation can also be used to encode a digital signal onto a media that uses an analog carrier signal, as in digital network traffic traveling over the public switched telephone network or PSTN. Multiplexing is often used with modulation. Multiplexing can be used to increase the number of modulated signals that can be placed onto a carrier signal. So let's talk about multiplexing, and I don't mean your local movie theater. The type of carrier signal will determine if multiplexing can occur. A baseband carrier signal cannot have multiplexing occur, as the modulated signal will consume all of the available frequency or channel width. Multiplexing can be utilized on a broadband carrier channel, as each modulated input is assigned a portion of the channel width of the carrier channel. Multiplexing can use one of two methods to weave streams of modulated signal into the carrier signal. There's frequency division multiplexing. This is the process of mathematically dividing the carrier channel frequency into multiple segments and assigning the results to modulated input signals. Then there is time division multiplexing. This is the process of mathematically dividing the carrier channel width into multiple time segments and assigning the time slots to different modulated signal input streams. It's time to talk about the difference between a baseband and broadband carrier channel. And we're going to begin with baseband. A simple definition of baseband is a stream of data that is sent over a carrier channel as a digital modulated signal. The digital signal will take all of the carrier signal's available frequency or time. While the modulated input does take all of the carrier channel's available frequency, the communication is bidirectional. It can flow back and forth. A simple definition of a broadband carrier channel is a stream of data that is sent over a carrier channel as an analog modulated signal. The analog signal will be assigned a portion of either the carrier channel's available frequency or time. While the modulated input doesn't take all of the carrier channel's available frequency, the communication is not bidirectional. For two-way communication to take place, multiplex channels must be created. That is, a channel for each direction. Now that concludes this session on Basic Network Concepts Part 1. I began with encapsulation and I concluded with modulation. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Basic Network Concepts Part 2. Today we're going to be talking about network transmission concepts, and then we're going to conclude with CSMA-CD and CSMA-CA. There's a fair amount of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin with network transmission concepts. The first concept is wavelength. Wavelength is a measurement of the distance between peaks in a wave pattern emitted by electromagnetic radiation, as in light waves, radio waves, or microwaves. Each type of electromagnetic radiation falls into a specific range of wavelengths. By modifying a wavelength, data can be encoded into the wavelength and transmitted to a receiving device, which then decodes the transmission. Then there's baud rate and bit rate. The baud rate was originally used to measure the speed of a telegraph transmission. It is a measure of the number of state changes in a given period of time. The usual state change that was measured was electricity, as in the number of times the state changed from 0.5 volts to 1.5 volts. The bit rate is a measure of the number of zeros and ones that can be transmitted across a medium in a given period of time. So it is a measure of the actual bits that can be transmitted. It is usually measured in bits per second, or BPS. The bit rate is a more accurate measure of transmission throughput than the baud rate. Then there's sampling size. When converting from an analog audio signal to a digital signal, a computer or other device captures the analog audio waveform and mathematically converts the captured sample into different wavelengths, which is how we get the discrete sounds. This occurs over a specific period of time, which is called the size of the sample, or the sampling size. And finally, there's carrier detect and carrier sense. Carrier detect is when a device can only tell when a carrier signal or channel is present by the reception of a control signal. The presence of the control signal signifies that transmissions can occur. The control signal controls the order of transmissions, so data collisions are not possible. The control signal can also be used to establish the maximum speed of the transmission that can be used. Carrier sense is when a device uses feedback from a receiver to determine if a carrier channel is present. If a carrier signal is detected, the device can send transmissions. Data transmission collisions are possible with carrier sense. And that logically leads us into CSMA-CD and CSMA-CA. The carrier detect method of network transmission works well when there are just a few nodes that need to be connected together. However, as the number of nodes that need to transmit increase, the efficiency of carrier detect begins to decrease to the point where it can become unmanageable. Although the carrier sense method of network transmission is not as efficient when the scale of the network is small, as the number of nodes increases, it becomes more efficient than the carrier detect method. So let's talk about CSMA-CD, or carrier sense multiple access with collision detection. CSMA-CD, of course, uses the carrier sense method of network transmission. Every device on the network uses feedback from a receiver to determine if a carrier channel is present. Every device connected to the network has an equal opportunity to place a transmission on the carrier channel. That's the multiple access part of the name. Before placing a transmission on the carrier channel, a device will listen to the channel to determine if another node is transmitting. If it detects a signal on the carrier channel, the node will wait before attempting to transmit. If no signal is detected, the node is free to send. If two devices send a transmission at the same time, a collision between the transmissions is possible. Sending devices will listen for transmission collisions. If a collision is detected, a jamming signal is sent informing all nodes that a collision has taken place. All devices that receive the jamming signal will wait for a random amount of time before attempting to transmit. Now let's talk about CSMA-CA, or carrier sense multiple access with collision avoidance. CSMA-CA operates in the same manner as CSMA-CD with one exception. It uses a collision avoidance scheme through the use of a controlling device. Before attempting to send data, a device will place a specific signal on the network called a request to send packet, or RTS packet. If no other device is utilizing the network, the controlling device will respond with another specific signal called a clear to send packet, or CTS packet. Once the sending device receives the CTS, it knows it can send a transmission without a collision occurring. CSMA-CD is better suited for high-speed, high-throughput networks and is the specified network transmission standard for the 802.3 Ethernet networking standard, as it has a low amount of network overhead. CSMA-CA is better suited for lower speed, lower throughput types of networks where the possibility of data collision is higher. It is the specified standard for 802.3 wireless networks or Wi-Fi networks. Now that concludes this session on Basic Network Concepts Part 2. I began with network transmission concepts and I concluded with a brief discussion on CSMA-CD and CSMA-CA. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Basic Network Concepts Part 3. Today we're going to be talking about numbering systems, and we will conclude with a very brief discussion on conversion tables. With that, let's go ahead and begin today's session. Of course, I'm going to begin by talking about numbering systems. While computer code and communication can get very complex, it can also be broken down to a basic bit level. A bit has one of two values. It either has a value of 0 or it has a value of 1. These values can be thought of as being either off, which is a 0, or on, a 1. These bit values are actually the only information that computing devices know. By combining and adding different bits together, computers can communicate with each other and programs can be created. Because of this, technicians need to know how to work with binary, or the base 2 numbering system. Binary is a base 2 numbering system where each position has one of two basic values. It is either a 0 or a 1. It is written from right to left with the potential value of digits being doubled with each additional digit that's added. If a 0 is the placeholder, it has a null value or no absolute value. And if a 1 is present, the actual value is double the potential value of the digit to the right. To derive the final value of a binary number, add all of the potential values together, and that will give you the decimal value of the binary number. The binary numbering system is very important when dealing with computers and networking. You should become comfortable with converting from decimal, or base 10 values, to binary, and from binary back to the decimal format. If you need help with that, there are multiple websites that can help. One website that I recommend is mathisfun.com. You can look on their website for their binary numbering lessons. Now let's talk about bit, byte, and nibble. A bit is a single 0 or 1. A byte is 8 bits, and it can also be referred to as an octet. A nibble is half of a byte, or 4 bits. And these terms are used quite frequently when dealing with binary. Now let's talk about hexadecimal. Hexadecimal is a base 16 numbering system that uses the numbers 0 through 9, and then it uses the letters A through F to represent the values 10 through 15. It functions in the same manner as binary, but with base 16. Each hexadecimal digit has a potential binary value of 1111 or 15, and it can be referred to as a nibble as it's half of a byte. A hexadecimal number can often be recognized by the notation prefix of 0 lowercase x, which directly precedes the hexadecimal number. Hexadecimal is widely used in programming and networking along with binary. Some examples of binary and hexadecimal use include IPv4 addresses, which can be represented by a 32-bit binary number that is divided into 4 8-bit sets. Each 8-bit set is equal to 1 byte and is often called an octet. An IPv6 address, which is a 128-bit binary number, is usually represented by hexadecimal, and it is divided into 8 2-byte sets, each set being separated by colons. And I recommend that you watch my presentations on IPv4 and IPv6 to get a better understanding of how binary and hexadecimal are used in networking. And now let's move on to conversion tables. When working with binary and hexadecimal numbers, I recommend creating a conversion table before doing the math. I find it to be very useful when I need to convert from decimal to binary or from hexadecimal to binary to decimal. Now that concludes this session on Basic Network Concepts Part 3. I began by talking about numbering systems, and I concluded with a very brief discussion on conversion tables. Hello, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to Wireless Standards. Today I'm going to talk about CSMA-CA, and then I'm going to conclude with a discussion on wireless standards. There's a fair amount of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about CSMA-CA. All wireless Ethernet standards employ an algorithm called Carrier Sense Multiple Access with Collision Avoidance. That's CSMA-CA. A CSMA-CA network involves a method of transmission that avoids packet collisions. Once a node wants to send a packet, it listens to the carrier wave. If no other node is transmitting, it will then transmit. If another node is transmitting, it will wait a random amount of time and then listen to the carrier wave again to see if it's free to send. This differs from a CSMA-CD, which stands for collision detection, type of network, which is all about how to transmit after a collision has occurred. Now let's talk about frequency modulation. Frequency modulation is the process used to encode data into a carrier wave. 802.11 uses two main frequency modulation methods. The first one is orthogonal frequency division multiplexing, or OFDM. OFDM is a frequency division multiplexing scheme that uses multiple subcarrier channels to carry data. It is used to mitigate against attenuation, which is loss of signal strength over distance, and multipath issues that exist in networking. The other frequency modulation method is direct sequence spread spectrum, or DSSS. DSSS is a modulation technique that uses spread spectrum technology to effect data transfer. It is used to mitigate the problem of multiple users on a channel and for effective timing between the transmitter and the receiver. Now let's move on to the wireless standards. Wireless networking standards are established by the 802.11 Committee of the Institute of Electrical and Electronics Engineers, or the IEEE. Quite often the term Wi-Fi is used to describe an 802.11 network, which is technically incorrect. Wi-Fi is actually a reference to the Wi-Fi Alliance, which is responsible for certifying that wireless networking equipment actually meets the 802.11 standards. Wi-Fi has become synonymous with the wireless local area network in the English language. So don't be surprised if you find yourself using the term Wi-Fi when you really mean 802.11. Now let's talk about the standards. And first up is 802.11a. It has a maximum speed of 54 megabits per second, and it operates on the 5 gigahertz frequency band. It uses OFDM as its form of modulation and has a maximum distance of 150 feet. 802.11a is compatible with 802.11ac. Then there's 802.11b. It has a maximum speed of 11 megabits per second, and it operates on the 2.4 gigahertz frequency band. 11b uses DSSS as its technique for modulation. It has a maximum distance of 300 feet, and it is compatible with 802.11g and 802.11n. Now let's move on to 802.11g. It has a maximum speed of 54 megabits per second, and it also operates on the 2.4 gigahertz frequency band. 11G can use OFDM and DSSS for its modulation techniques. It has a maximum distance of 300 feet. 802.11g is compatible with 802.11b and 802.11n. Now, talking about 802.11n, it has a maximum speed of up to 600 megabits per second, and it can operate on both the 2.4 and the 5 gigahertz frequency band. It does use OFDM as its form of modulation. It offers a maximum distance of 300 feet. 802.11n is compatible with 11b, 11g, and 11ac. With the introduction of 802.11n, we now find MIMO, multiple input, multiple output. It's a technology that allows for the increase in speed for the wireless network. With 11n, there can be up to 4 antennas, which allow for up to 4 separate spatial streams. And finally, we have 802.11ac. Now, 802.11ac offers speed anywhere from up to 433 megabits per second up to multiples of gigabits per second, and it operates on the 5 gigahertz frequency band. It uses OFDM as its method of modulation, but its implementation is an advanced form of OFDM. .11ac offers a theoretical maximum distance of 300 feet. .11ac can be compatible with .11a, g, or n. When 802.11ac was introduced, they improved the MIMO technology, which now allows for up to 8 antennas, which means that there can be up to 8 separate spatial streams of data. Now that concludes this session on the Introduction to Wireless Standards. I began this discussion by talking about CSMA-CA, and then I concluded with a brief discussion on the wireless standards. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Introduction to Wired Network Standards. Today I'm going to be discussing the TIA EIA 568A and TIA EIA 568B standards. Then I'm going to move on to Ethernet standards, and I'm going to conclude with some other standards. I have a whole lot of information to cover, but not a whole lot of time, so let's dive into today's session. Of course, I'm going to begin with the TIA EIA 568A and 568B wired standards. The TIA EIA 568A and 568B standards deal with twisted pair wires. These are the two cable pinout standards that are regulated by the TIA EIA. That's the Telecommunications Industry Association Electronic Industries Alliance. The pinout standards specify the ordering of the wires to ensure that proper networking communication can take place. The T568A standard is white green green, white orange blue, white blue orange, white brown brown. On the other hand, the T568B standard is white orange orange, white green blue, white blue green, white brown brown. All modern Ethernet networks that utilize unshielded twisted pair, UTP, or shielded twisted pair, STP, should use the TIA-EIA standards. As a quick refresher for twisted pair wiring, here are some common tools that you will need. There are wire strippers. These are used to remove the insulating jacket from the cable. Then there are crimping tools. These are used to secure the wires into modular connectors. Then there are punch-down tools. These are used to secure wires into punch-down blocks. And finally, there are cable testers. These are used to test the integrity of the network cables that you've just created. With that covered, let's move on to Ethernet standards. First up are distance limitations. Twisted pair copper wire is limited to 100 meters without a repeater unless otherwise stated. Coaxial LAN cabling is limited to either 185 or 500 meters depending upon the coaxial cable that is used. As an example, a 10-base-2 coaxial network uses RG58 and is limited to 185 meters in length. On the other hand, a 10-base-5 coaxial network using RG8 is limited to 500 meters. With fiber optics, LAN transmission is limited by the cable type that is used. The current maximum is over 40 kilometers over a single-mode optical fiber, or SMF fiber. Now let's talk about twisted pair cable standards. There's 10-base-T, that's 10 megabits per second, using UTP over a minimum of Cat3 cable. Then there's 100-base-T, that's 100 megabits per second, using a minimum of Cat5. You can also have 100-base-TX. This is 100 megabits per second networking using 2 pair over a minimum of Cat5. Then there's 1000-base-TX. This is 1 gigabits per second networking using 2 pair over a minimum of Cat5e cable. Then there's 10G-base-T, that is 10 gigabits per second networking using a minimum of Cat6, but it's only good for 40 meters. Finally, there's also 10G-base-T, that's 10 gigabits per second networking using a minimum of Cat6a cabling, but that's good for up to 100 meters. Now let's move on to the multi-cable standard, and that's 1000-base-X. Under this standard, there's 1000-base-SX, which is 1 gigabit per second networking over a short distance multi-mode fiber, and it's usually less than 2 kilometers. Then there's 1000-base-LX. This is 1 gigabits per second networking over long distance single mode fiber, and it's usually a greater span than 2 kilometers. And finally, there's 1000-CX. This is 1 gigabits per second networking over a coaxial cable that can be up to 25 meters long. Now let's talk about 10 gigabit networking. First up, there's 10G-base-SR over multi-mode fiber, and it's good for up to 300 meters. Then there's 10G-base-LR over single mode fiber, which is good for up to 10 kilometers. Then we have 10G-base-ER, which is over single mode fiber, and it's good for up to 40 kilometers. Then we have 10G-base-SW. This runs over MMF, and it's good for up to 300 meters, and it's used on a wide area network. Then there's 10G-base-LW, which runs over SMF up to 10 kilometers, and it's also used in a wide area network. And then there's 10G-base-EW, which runs over single mode fiber for up to 40 kilometers, and again on that SONET type WAN network. Then there's 10G-base-LX4, which runs over single mode fiber, and it's good for up to 300 meters. Then there is 10G-base-LX4 over multi-mode, which is over multi-mode fiber, which is good for up to 10 kilometers. And finally, there is 10G-base-CX4. This runs over InfiniBand copper cabling, and it's good for up to 15 meters. It's time to conclude with some other standards. First up is DOCSIS, or Data Over Cable Services Interface Specification. These are the standards that have been established to provide the interface requirements for data transmissions over a broadband cable network. To achieve the best performance when using broadband cable, the cable modem should meet the highest DOCSIS standard used by the cable provider. The most current DOCSIS standard is 3.1, which allows for up to a theoretical maximum download speed of 10 gigabits per second with a theoretical upload speed of 1 gigabit per second. Then there's the IEEE 1905.1-2013 standard. This is a standard that defines a network enabler or device that is used to create a convergent home networking environment that includes different types of wired and wireless networks. The standard also includes Ethernet over Powerline, which is using the existing electrical wiring in a structure as the media to transport data. The standard also includes Ethernet over HDMI, which is using an HDMI interface and cable to transport network traffic. Now that concludes this session on the Introduction to Wired Network Standards. I began by talking about the TIA EIA 568A and 568B standards. Then I moved on to the Ethernet standards, and I concluded with a brief discussion on some other standards. Good day, I'm Brian Farrell, and welcome to PACE IT's session on security policies and other documents. Today I'm going to be discussing some security policies, and then I will conclude with a brief discussion on other documents. There's a fair amount of ground to cover, but not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by discussing security policies. Policies are a set of guidelines established by management that are used to set the expected behavior in the workplace. Procedures are different than policies in that a procedure is a set of steps required to be taken in a given situation. Policies and procedures work hand in hand to create a safe and secure work environment in which employees know the guidelines and what is expected of them. Policies and procedures should be given to every person on the day they start, and periodic training should be conducted to ensure that they remain fresh in everyone's mind. One of the security policies to consider is the consent to monitoring. This is a policy that establishes an employer's right to monitor the employee's actions and communications. This can include monitoring emails. If they traverse company equipment in any way, then the emails are not considered private, but are actually company assets that they have a right to view and do with as they please. These consent to monitoring policies also include the monitoring or recording of phone conversations, also monitoring activities on computers, hard drives, and phones. In a highly secure work environment, it may also include the video monitoring and recording of normal work activities. Another security policy is a clean desk policy. This is a policy that is concerned about the handling of sensitive data. Sensitive data should not be left unattended in a workplace and should be put away when not in use, not left on a desktop. These policies also include the computer desktop. Sensitive data should not be left easily accessible on the PC. Then there are recording policies. This is a policy that restricts the use of cameras, tape recorders, portable storage devices, or any other device that may be used to record or copy sensitive workplace information. Then there are equipment access policies. They're a security policy that establishes who has access to which equipment and when. These could include access to server rooms, wiring closets, network racks, or any other area that is deemed to have a security risk. There are security policies that deal with the handling of user or customer information. They're used to establish how to secure sensitive employee and customer information. User and customer information is a major target of hackers when they breach computing systems. The loss of control of this data can severely damage a company. Any policy that is used to help secure the workplace or company data is, by default, a security policy. Approximately 80% of all network and data breaches occur from within the companies that are attempting to secure the data. Sometimes they occur by mistake. However, all too often they are intentional. All policies should have an enforcement aspect to them that details what employees should expect to happen if they violate the policy. The range of actions can be from retraining to termination and prosecution. Now let's conclude with a brief discussion on some other documents. First up is the AUP, or Acceptable Use Policy. These are a set of rules and guidelines established by the creator, owner, or administrator of information systems that detail what users may or may not do with that information system. It is considered to be part of the security policy. The AUP should be fairly detailed in what is allowed or not allowed to occur. All users should be required to sign the acceptable use policy, and these records should be kept on file. Then there are network policy documents. There are a broad range of policies that establish the guidelines for the network. They include policies that control the use and operation of the network, as well as policies on how to implement changes to it. Many security policies fall under the general network policies category. There are some standard business documents that you should be familiar with. The first one is the Memorandum of Understanding, or MOU. It's an agreement between two or more organizations that detail how those organizations are to undertake a common course of action. An MOU is often used before a legally binding agreement has been created. Sometimes the MOU is called a Letter of Intent, or LOI. Then there is the Statement of Work, or the SOW. It's a detailed document that specifies what work is to be performed, the expected outcome of the work or the deliverables of the work, and the timelines to perform that work. The SOW plays an important role in project management documentation. Then there is the Master License Agreement, or the MLA. It's a legal agreement between two entities in which one agrees to pay the other for the use of a specific piece of software or a software package for a specific period of time. So the person using the software doesn't actually own the software. The creator or the vendor retains the legal rights to that software or that software package. And finally, there's the Service Level Agreement, or the SLA. It's an agreement that details the allowable amount of response time the vendor has to resolve an issue or problem. The SLA is most commonly associated with a service contract. Now that concludes this session on security policies and other documents. I briefly talked about security policies, and then I concluded with a discussion on some other documents. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Introduction to Safety Practices, Part 1. Today I'm going to be talking about electrical safety, and then I'm going to move on to installation safety. I have a fair amount of ground to cover, but not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin with electrical safety. Electrical grounding is used to protect technicians and equipment in the case of electrical insulation failure. Electrical grounding provides an alternate path for the electricity. This is often referred to as a return to earth. All electrical systems should be connected to properly grounded circuits. This helps to protect both the technician and the equipment. Then there's ESD, or electrostatic discharge. ESD is caused when two electrically charged objects that have different amounts of electrical charge come into contact, creating a sudden flow of energy between the objects as they normalize the levels. This is a static discharge. ESD can damage sensitive components, particularly the CPU and/or your random access memory. Using an ESD mat helps to reduce the chances of ESD. Using an ESD strap will further reduce the chances for ESD. The strap goes around the wrist of the technician and then is clipped to a ground source, usually to an exposed metal surface inside of a piece of equipment's case. You should always practice self-grounding. Self-grounding is a normalization technique used to equalize the amount of electrical charge between the worker and the equipment being worked on. After the case has been opened and the ESD strap is attached to a ground source, touch an exposed metal surface inside the case before actually touching any of the components. This will normalize the electrical charge between you and the equipment that you're working on. In some cases, additional equipment grounding may be necessary. In case of an electrical fire, unplug the power source or turn off the circuit breaker. Always use a Class C or multi-class fire extinguisher on electrical fires. Never use water. You run the risk of electrocution and damaging that equipment even more than the fire is already doing. So let's talk about fire suppression systems. Building codes often call for the installation of fire suppression systems, and there are several different types of common systems. There's the wet pipe. The overhead pipes are pressurized and contain water all of the time. Then there's the dry pipe. The pipes are not pressurized. The water is contained in a holding tank until a fire breaks out, and then it is pumped to the area where it needs to be dispersed. There are pre-action types of fire suppression systems. They're similar to a dry pipe system, but the sprinkler head contains a thermal fusible link that must melt before the water is released. Then there's the deluge fire suppression system. These are designed to release a large amount of water in a short amount of time into a predefined space. The deluge system is the least desirable option for electrical components. On the other hand, a halon type system is the most desirable type of fire suppression system for electrical components. Halon is a non-conducting, volatile gaseous chemical. It works by chemically disrupting the combustion process. Halon does not leave a residue upon evaporation, and unlike water, halon will not ruin electrical components. It is safe for exposure to humans in limited amounts for a limited amount of time. Halon is also environmentally safe. It's also known as a clean agent. Now it's time to move on to installation safety. First up is using proper lifting techniques. Bend at the knees, not at the waist. Keep your head up when lifting. Avoid twisting when carrying items. If the item is heavy or awkward, request help in lifting it. Also remember, most companies establish weight limitations. So if you're going to lift something that is going to exceed that weight limitation, ask for help. More than likely, you are going to need to install equipment racks at some point in time or another. Racks are used to help create a clean, organized environment, especially when they're used with proper cable management techniques. Racks are designed to provide sufficient airflow for the electrical components that are placed in them. When assembling and installing racks, always follow the manufacturer's instructions. Always use the proper tools to prevent damaging the racks or the fasteners that hold them together. Many servers and networking components come rack ready. That means they're specifically designed to be placed into an equipment rack. Let's talk about rack placement. When designing a room that is going to hold multiple racks of computing systems, some thought needs to go into the placement of those racks. HVAC and rack placement should be done concurrently. Heating, ventilation, and air conditioning systems should be designed to control both heat and humidity levels. When multiple racks are going to be installed, creating a hot aisle, cold aisle design is recommended. The hot aisle is the side of the aisle that receives the exhaust airflow from the computing equipment. This aisle should face an HVAC air intake. The cold aisle is the side or aisle that the air intakes of the computing equipment face. This aisle should face an HVAC air vent. Also, whenever possible, a server room should be designed with a raised floor to help protect against water damage. The raised floor, like a drop ceiling, can also be utilized as part of the cable management system. Let's talk about tool safety. Always use the proper tool for the job. That is what it was designed for. Do not use pencils as a probe. It is possible for the pencil to conduct electricity, leading to an ESD situation or shock hazard. Do not use magnetized tools when working on electrical components, as the magnetic charge can be harmful to the magnetically kept data, and that magnetically charged tool may damage sensitive components. When using compressed air to blow out debris, maintain a minimum distance of 4 inches from the nozzle to the component. Always use isopropyl alcohol to clean products in place of rubbing alcohol. Rubbing alcohol contains a higher water content of approximately around 30%, whereas the water content in isopropyl alcohol is lower. Never use a standard vacuum cleaner when vacuuming electrical components is necessary. Due to the design of the standard vacuum, electrostatic discharges are a common occurrence. There are specifically designed vacuum cleaners that can be used on electrical components. Now that concludes this session on the Introduction to Safety Practices Part 1. I talked about electrical safety, and then I concluded with installation safety. Good day, I'm Brian Farrell, and welcome to PACE IT's session on the Introduction to Safety Practices Part 2. Today I'm going to talk about the MSDS, and then I'm going to conclude with some emergency preparations. There's a fair amount of ground to cover, so let's go ahead and begin this session. Of course, I'm going to begin with the MSDS. Part of any safety-first approach to a safe work environment includes knowing what hazards are present in the workplace. Material Safety Data Sheets, or MSDSs, contain safety information on materials and chemicals found in the workplace. An MSDS will contain all known health issues associated with a particular material. It also outlines what protective measures must be taken to reduce risks from exposure and what actions must be taken if the chemical is ingested. The MSDS will also detail the physical properties of the material, as in its flash point or boiling point, and the MSDS will outline the proper steps to take when disposing of it. Each workplace will have its own set of MSDSs, as each workplace is different. It is your responsibility to understand the hazards that are present, so you need to know where the MSDSs are kept for your workplace. It's time to move on to some emergency preparations. Part of any safety-first approach to a safe work environment includes preparing for various types of emergencies. These preparations should be detailed in a set of emergency procedure documents. The procedures should contain escape routes, including where employees will meet to ensure that all are accounted for, information on what type or types of fire suppression systems are present, as well as what steps have been taken to increase the day-to-day safety in the workplace. There are some building layout considerations that concern emergency preparations. All walls should have a minimum 2-hour fire rating. This is the amount of time it takes for the average fire to burn through the wall. Exterior doors and other secure doors must be designed to resist forcible entry, but the doorways should also be designed to be able to handle the amount of expected traffic in an emergency. Fire suppression systems should be appropriate for the type of asset that they are protecting. A wet pipe system is not appropriate for a server room or data center. However, a halon system may not be the correct fire suppression system for an open cubicle area. Backup power should also be incorporated into the building layout. Not all areas are going to require backup power, but for some areas it is going to be essential. Emergency preparations need to include escape plans. Each area or room should have an escape plan map posted in a prominent area, ideally by the main access doorway into that area. This map needs to show the preferred route out of the facility. The map should also include the meeting area outside of the danger zone. This allows for supervisors or managers to account for all personnel. Safety or emergency exits should be clearly marked. They should also be well lit with independent battery power sources. They should be wide enough to handle the expected traffic, and emergency exits should always be kept clear of obstructions. Talking about doors, there are some other considerations. Are they going to be fail open or fail close? So what happens to doors with electronic locks when the power is out needs to be considered. They could be fail close type doors. With this type of door, when the power is cut, the locks engage. These are suitable for keeping secure areas secure in an emergency. Then there are fail open type electronic locks. When the power is cut, the locks disengage. These are suitable for non-secure areas or for areas where two-way traffic is going to occur in an emergency. In many facilities, fail-close type fire doors are used. Usually they're kept open by electromagnetics. Once the fire alarm has been tripped, the power is cut to the magnets and the doors swing closed. They usually do not lock when closed, but are used to help slow the spread of fire or other dangers. Another emergency preparation that should be considered are emergency alert systems. All facilities should have an emergency alert system installed. It is usually required by local building codes. These are your fire alarms and whatnot. Combinations of sound and light have proven to be highly effective. In some situations, it may be advisable to connect the facility to the National Emergency Alert System. Now that concludes this session on Introduction to Safety Practices Part 2. I began with the MSDS, and then I concluded with emergency preparations. Good day, I'm Brian Farrell, and welcome to PACE IT's session on rack and power management. Today I'm going to talk about rack management, and then I'm going to conclude with a brief segment on power management. With that, let's go ahead and begin today's session. I'm going to begin by talking about rack management. Rack systems are specially designed racks used to hold networking and computing equipment. Sometimes they are referred to as server racks. These rack systems follow one of several different designs. However, they all follow the same height specification. That specification is the standard unit, and it's designated by the capital letter U. Now, the standard unit involves the amount of vertical space that can be used to hold equipment. A standard unit is equal to 1.75 inches. So a 15U rack has 26¼ inches of vertical storage space. Most rack servers and enterprise-level networking equipment are designed to fit within rack systems. There are several different types of racks. Racks are normally either 2-post or 4-post racks. They may be freestanding or they may be floor-mounted. Server rail racks have slide mounts to make it easy to pull out servers to perform necessary maintenance. Now let's talk about device placement. Devices that generate the most amount of heat or are not heat sensitive should be placed towards the top of the rack. Devices that generate the least amount of heat or are heat sensitive should be placed toward the bottom of the rack. All equipment cold air intakes should face the same direction. All equipment exhaust outlets should therefore also face the same direction. When mounting equipment in racks, vertical space should be left between the equipment to promote adequate airflow. When multiple rows of racks are implemented, a hot aisle cold aisle approach should be used to promote proper airflow and cooling. Racks should be monitored for environmental factors to help ensure the health of the servers and other equipment. Monitors should be in place for temperature, humidity, vibration, water leaks, smoke, and intrusion. And that brings us to rack security. Most rack systems do not come with rack security in mind, but it can be easily added after rack installation. Rack doors can be added that have either keyed or electronic locks. If the equipment is not secured, it can be easily stolen. Now let's have a brief discussion on power management. So before I begin talking about power management, let me give you a little bit of trivia. We're all familiar with the power symbol that you see there to the right. That's actually a binary symbol. What that is a 0 with a 1 poking through it. I know, not very relevant to today's discussion, but it's an interesting bit of trivia. Now, power is often overlooked when designing a network. However, without power management, the network may never work properly. Most people assume that when they plug a piece of equipment into a wall socket, that piece of equipment is going to power up just fine. In most cases, they are correct. However, if the circuit cannot provide enough amps to the equipment, damage may occur. It is important to know the power requirements and loads for all of the equipment that will be in place. This helps to ensure that the proper electrical circuits are installed so that sufficient power is delivered where it is needed, when it is needed. Power converters convert electrical energy from one form to another, as in from AC to DC, or from one voltage level to another. On the other hand, power inverters are a type of power converter that specifically converts voltages from DC to AC. Then we have the uninterruptible power supply, the UPS. It uses power converters to receive electrical current from an AC electrical source, and it passes that current to a battery or set of batteries for storage. It then uses a power inverter to receive DC current from the batteries and pass it to another device as a conditioned and well-regulated AC flow. They're used to provide a steady stream of conditioned electrical power to components. They help to protect sensitive electrical components from power anomalies, either from power spikes, power outs, or from power sags. In some cases, you may want to consider installing power redundancies. Critical components should include redundant power supplies. That means that if one power supply fails, the other one takes over immediately without any loss of service. Now that concludes this session on rack and power management. I began by talking briefly about rack management, and then I concluded with a brief discussion on power management. Good day, I'm Brian Farrell, and welcome to PACE IT's session on cable management. Today I'm going to be talking about cable distribution, and then I will conclude with some cable management components. We have a fair amount of ground to cover with not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin by talking about cable distribution. And the first item under cable distribution is the main distribution frame, or MDF. This is the location where the DMARC extension, main switch or router, and patch panel are placed. The MDF is where outside traffic enters a location and is then distributed to the internal network. It is possible to also have an intermediate distribution frame, or IDF. It's a location's solution for when a single MDF is not sufficient. They usually occur in multi-story buildings. The IDFs are connected to the MDF by vertical cross-connect cables, or VCC cables. It is common for an MDF to contain separate IDF panels for each floor of a building. A vertical cross-connect is the main patch panel for a location. It usually resides in the same location or very close to the DMARC and main switch or router. I mentioned patch panels earlier, so let's talk about those. They're used to terminate network cable runs, usually within a building, as in from the wall jacks to a central location. The network runs are called horizontal cabling. Patch panels are used to organize and administer the physical aspects of the network cables. Network runs are punched down to the back of the patch panel, which normally contains either a 66 or a 110 block, with an associated port on the front of the patch panel. Patch cables are used to connect the patch panel ports to networking gear, quite often a switch. Workstations connect to the patch panel using horizontal cabling. This location is called the Horizontal Cross Connect, or HCC, and is usually located in the IDF. Switches may or may not be present in this location. If a workstation needs to be relocated to a different switch or port, all that needs to be done is to make the change in the location of the patch panel. So you unplug the cable from one port and you plug it into a new port. With that covered, let's talk about cable management components. Labeling is an important part of cable management. It can cause stress when working with networks, but it doesn't have to. The key to proper labeling is to create a naming convention, which is a systematic and consistent method that makes sense for the situation. Proper labeling will ease the management of the physical aspects of the network, especially when dealing with cables. Labels should be placed on everything that deals with the network, beginning from the wall jacks all the way through to the patch panel, switches, and routers. The naming convention should be documented and kept with the network diagrams. Let me give you an example of a naming convention. Suppose Office 219 has network outlets on all four walls. The jacks could be labeled 219N, 219W, etc. And that would be for 219 North or 219 West, etc. The horizontal cabling from 219 feeds into a patch panel in an IDF located on the second floor that contains two 48-port switches that tie in all the horizontal cross connects. The cables coming in from Office 219 to the patch panel could be labeled 219W or 219S, etc., as it relates to their location in the office. The switches could be labeled SW2A and SW2B. Now suppose that the patch cables for Office 219 connect to switch 2B's ports 20 through 24. The patch cables could be labeled 219N-SW2B-21 or 219E-SW2B-22, etc. The key is to be consistent and to document everything. And finally, there are cable trays. Masses of cables can block airflow and act as an insulator that allows for excessive heat to build up. Cable trays are used to organize cabling and to keep it away from areas where cabling may cause heat to build up. Cable trays keep bundles of cables neat and fairly well organized. That concludes this session on cable management. I talked about cable distribution, and then I briefly covered some cable management components. Good day, I'm Brian Farrell, and welcome to PACE IT's session on the basics of change management. Today we're going to be talking about the reasons for change management, and then we're going to conclude with some different change management processes. I have a fair amount of ground to cover, but not a whole lot of time, so let's go ahead and begin this session. Of course, I'm going to begin with the reason for change management. In a fairly simple network, it is fairly easy to evaluate not only the necessity for a change, but also the possible impacts of that change. However, as the network system increases in size and complexity, it becomes more difficult to not only determine what changes are necessary, but also the possible impacts that the proposed changes will have on the system as a whole. It is quite possible, even highly probable, that a single change will have a ripple effect on the whole system. Change management processes are used to introduce changes to a system in a controlled manner to minimize possible disruption and potential pandemonium. With the reason for change management covered, let's move on to different change management processes. First up is document the reason for a change. Proposed changes should have a solid reason for occurring. A best practice is to include why the change is needed for IT reasons and also for business reasons. As the change proceeds through the process, more documentation may be added to the reason for a change. So let's talk about the change request. A formal change request procedure is used during the approval process and should include several other subdocuments that can be used to gain approval. One of those documents is the configuration procedures documents. These document the exact steps required to implement the change, including affected devices, applications, and processes. The change request should also include a rollback process. As all change carries risk, a plan to reverse changes is required in order to gain approval. Then there are potential impact documents. The potential impact documents are a good faith effort to identify all possible impacts to the overall system, both the positive and the negative. Then there is the notification procedures. After the potential impacts have been identified, the people responsible for the affected systems must receive notification of the proposed change. Keeping your stakeholders informed and involved will greatly increase the chances of a successful change. Let's talk about approval processes. Proposed changes should be vetted and approved, not only by management, but also by senior IT personnel, security experts, and by a selection of those affected by the change. Some companies create change control boards to not only evaluate proposed changes, but to also implement a means of approving changes. These boards also assure that all approved changes have been fully tested and documented. The change boards meet periodically to assess the status of an approved change. This helps to keep it on track for implementation. Change boards maintain responsibility for the change and verify that the process is proceeding according to the configuration procedure. And finally, change boards help to ensure that approved changes are implemented correctly. When planning out a change to an IT system, it's important to involve a maintenance window procedure. A maintenance window is the amount of time that a system will be down or unavailable during the proposed change. Before the final schedule is developed, an evaluation of all affected systems must be performed with particular attention paid to mission-critical systems. It is possible that the proposed maintenance window may exceed the allowable downtime for critical systems, which will affect when the maintenance window can be scheduled. A sub-procedure to the maintenance window procedure is authorized downtime. Once a maintenance window has been identified, it is then possible to determine the optimum time to implement the change. In many cases, system changes need to occur during off hours, as in after the close of business or during weekends when systems are not utilized as much. Then there's the notification of change procedure. After sufficient time has elapsed in which to evaluate any issues, all stakeholders, those are the people who approved the change and all others affected by the change, should be notified of the successful completion of the change. This allows the stakeholders to further monitor the systems for any unforeseen or residual issues relating to the change. And finally, there's final documentation. The change process should end with an update to the appropriate documentation, including network configurations, additions to the network, and physical location changes. A closing change report should also be created that summarizes the change to help refine the change procedures and processes even further. This closing report should include what went right and what went wrong during the approved change. That concludes this session on the basics of change management. I talked about the reasons for change management, and then I concluded with different change management processes. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Common Networking Protocols, Part 1. Today I'm going to briefly discuss TCP and UDP, and then I'm going to briefly run through some common ports and protocols. With that, let's go ahead and begin this session. Let's begin with a brief overview of TCP and UDP. Both Transmission Control Protocol and User Datagram Protocol are both Transport Layer or Layer 4 protocols. They're both responsible for the delivery of network data between nodes. While they are both Layer 4 protocols, they do have some differences. TCP uses a reliable delivery method. This ensures that all the packets that are sent are received. It uses acknowledgments as a means of error correction. TCP also establishes flow control to reduce the error rate and ensure proper delivery. On the other hand, UDP uses a best effort delivery method. It sends data but doesn't care if the packets are all received. There is no error correction, and with UDP, speed and low network overhead are the major concerns, not the reliable delivery of the information. Now let's discuss some common ports and protocols. First up is HTTP. That's Hypertext Transfer Protocol. It's the primary protocol used to transfer data over the internet. It is assigned to port 80. Then there's HTTPS, which is Hypertext Transfer Protocol Secure. It is the primary protocol to securely transfer data over the internet using SSL or TLS technology. That's Secure Socket Layer or Transport Layer Security technology. In actuality, SSL should no longer be used. You should only be using TLS. By default, HTTPS is assigned to port 443. Then there's NetBIOS. That's Network Basic Input Output System. This was originally developed to allow hosts to be able to communicate with servers. By default, it's assigned to ports 137 through 139. Then we have SMTP, or Simple Mail Transfer Protocol. This is the protocol that's used to transfer email from a client to an email server or to transfer email between different email servers. By default, it's assigned to port 25. Post Office Protocol version 3, or POP3, is the protocol used by clients to retrieve email from servers. Once engaged, POP3 downloads all the messages from the servers. The user cannot access email messages until they have been downloaded by the POP3 protocol. POP3 is assigned to port 110. In contrast to POP3 is IMAP. That's Internet Message Access Protocol. It's a protocol used by clients to access email on email servers. Allows the client to administer and organize email on the server into folders without having to download it first. By default, IMAP is assigned to port 143. Next up is SIP, or Session Initiation Protocol. It's a protocol that is most commonly used to set up and tear down multimedia communication sessions, as in Voice over IP. In a Voice over IP session, SIP is used to establish and to terminate the session. Session Initiation Protocol is commonly assigned to either port 560 or to port 561. Often used in conjunction with Session Initiation Protocol is RTP. That's Real-Time Transport Protocol. This is the protocol that is commonly used to format and deliver multimedia or streaming content. As an example, RTP handles the flow of packets in a voice over IP session after Session Initiation Protocol has established the connection. RTP is commonly assigned to ports 5004 and to port 5005. Then there's Media Gateway Control Protocol, or MGCP. It's a protocol that defines a means of communication between a packet-switched network and a circuit-switched network, as in the PSTN. It can be used to set up and maintain and terminate calls between multiple endpoints, as in teleconferencing. It's commonly assigned to ports 2427 and or to port 2727. Last up we have H323. This is a protocol that provides a standard for delivering video over IP networks. It defines how real-time audio, video, and data are to be transmitted. It provides signaling and bandwidth control. It's commonly assigned to port 1720. That concludes this session on Common Networking Protocols, Part 1. I did a brief summary of TCP and UDP, and then I briefly ran through some common ports and protocols. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Common Networking Protocols, Part 2. Today I'm going to be talking about the difference between ports and protocols, and then I'm going to conclude with a brief discussion on some common ports and protocols. With that, let's go ahead and jump into this session. Of course, I'm going to begin by talking about the difference between ports and protocols. Ports are a method of specifying what protocol or service to access. Many protocols and services use default ports so they are easy to locate. There are 65,536 ports available to be used for communication, but port 0 is reserved. The first 1,024 ports are specifically assigned and are called well-known ports. If you would like to learn more about those, you can check out the iana.org website. Ports can be thought of as a phone number extension. The IP address is the main number you are trying to reach. The port is the extension for the service or protocol that you want to access. Protocols can be thought of as the language that two applications on either side of the connection agree to speak. Protocols translate requests into services. Most protocols use predefined ports, but some protocols must be user configured for the ports that they use. Something to remember, ports are not protocols and protocols are not ports. Even though the two are closely associated, they are not the same. Ports are used to request or access services or applications. Protocols are the services or applications that are being requested. When a requester seeks to connect to a specific port, the requester is dynamically assigned a port number to listen to for the response. This also allows computers to have many concurrent connections at the same time. It's time to move on to a brief discussion on common ports and protocols. First up is the File Transfer Protocol, or FTP. It's a standard protocol for transferring files between computing systems, and it does require user authentication. FTP uses ports 20 and 21, although nowadays it mostly just uses port 20. Then there's TFTP, or Trivial File Transfer Protocol. This is used to transfer files between servers and clients, but no user authentication is required. By default, TFTP is assigned to port 69. Then there's SNMP, or Simple Network Management Protocol. It's a protocol used to monitor and manage local area networks. By default, it is assigned to port 161. Then we have Telnet, which is a protocol that is used for remote access to systems. It is unsecure, but it is also a bidirectional terminal service that comes in handy on occasion. By default, Telnet uses port 23. More secure than Telnet is SSH, or Secure Shell. It's a protocol that's used to encrypt data traffic on networks. It can be used in place of Telnet to provide a secure bidirectional terminal connection. By default, SSH uses port 22. A very useful protocol to have is DNS, or the Domain Name System Protocol. This is the protocol that's used to map computer names to their IP addresses. DNS is assigned to port 53 by default. Then there's DHCP, or Dynamic Host Configuration Protocol. This is the protocol used within networks to automatically configure computers with the correct IP configuration. There are two ports used with DHCP. Requests are assigned to port 67. Responses from the DHCP server are assigned to port 68. Remote Desktop Protocol, or RDP, is used in Microsoft networks by both the Remote Desktop Connection and Remote Assistance applications to make remote connections. RDP is assigned to port 3389. Last up, we have SMB, or Server Message Block. It's a protocol used to transfer files over a network. The process is transparent to the user. The user never sees SMB. SMB can be configured to run over NetBIOS on ports 137 through port 139. But by default, SMB is assigned to port 445. That concludes this session on Common Networking Protocols Part 2. Today I talked about the differences between ports and protocols, and then I briefly discussed some common ports and protocols. On behalf of PACE IT, thank you for watching this session, and I hope to do another one soon.